We've come a long way. This is the last lecture. Just as there is an arrow of time, there's an arrow of lectures. If you have followed them in order, then a certain amount of time has passed since you watched lecture 1 or listened to it to today. In a very real sense, you're a different person than you were when we started. At the very least, you are older. A certain number of moments have accumulated in your life. You have different memories than you had. You hopefully can remember some of the stuff that was in the previous lectures. Maybe you've thought about it. Maybe it has affected the ways that you've accumulated other memories when you were not listening to the lectures. It's even possible you are wiser. Maybe the things that we've talked about have made you look at the world in a different way. Going toward the future, it's possible that some of the things that you've heard about in these lectures will affect choices you make. It might affect which great courses you will listen to next. It might affect how you think about the nature of time. So again, the arrow of time makes us who we are. We reach a certain state at the present moment as an accumulation of different moments. We live in a universe that doesn't just happen randomly. It moves in a certain direction. And that's true for the whole universe. It's true for every one of us. It's because of the arrow of time that we remember yesterday, we don't remember tomorrow. You've heard the lectures, you don't know what's going to happen next. And yet, at the same time, you are made of individual pieces. You are made of atoms. Those atoms are made of particles. These individual pieces don't accumulate anything as time goes on. They cannot tell the difference between past and future. At the level of two particles interacting with each other, there is no arrow of time. The deep underlying laws of reality, as we understand them today, do not distinguish between one direction of time and the other. It's the task of connecting these two realities that has been our challenge. The deep underlying reality we believe is true, which says that there is no difference between past and future. There's no intrinsic arrow of time. You can make a movie of particles and atoms, play it backward, and no one would be able to notice, versus our obvious phenomenological reality around us at all moments, when it is obvious that there's an arrow of time. You make a movie of an egg breaking, or someone diving into a pool, or mixing milk into coffee, you play it backwards and everyone will notice. The reconciliation seems to be that we are not alone in the universe. We are a complicated system. We're embedded in an environment. Our environment is very, very far from equilibrium. In other words, there's something called entropy that characterizes how organized or disorganized we are and our environment is. High entropy is equilibrium. It's a configuration of stuff that will stay just like that. That's where it wants to be. That is the most natural place for a system to be in. But our universe is very, very far from equilibrium. We are experiencing an unmistakable arrow of time. Entropy is increasing through time, and that's why you remember the previous lectures. You don't remember what's going to happen next. We know why entropy increases. It's not because the fundamental laws of physics say it will. It's not because the microscopic laws that govern individual atoms and particles say that there's an arrow of time. It's because of our environment. There are just two very simple principles that completely explain why entropy is increasing. First, there are more ways to be high entropy than to be low entropy. That explains why starting today, going to the future, entropy is going to be increasing. Given whatever we're doing today, and no more information than that, the overwhelmingly high probability is that entropy will be higher tomorrow. You let a physical system evolve with time, it will tend to move towards higher and higher entropy. The second principle is that the universe started out with a very low entropy. That explains why the entropy was smaller yesterday, why it was lower in the past. The first principle, that there are more ways to be high entropy than to be low entropy, is absolutely symmetric with respect to time. There's no intrinsic arrow of time built into the definition of entropy. The second principle is the past hypothesis. The universe started in a low entropy state of the right form to create a universe like ours. That is manifestly asymmetric with respect to time. It's a past hypothesis, it's not a future hypothesis. The amazing fact about our world, one of the unifying triumphs of physics, is that all of the different manifestations of the arrow of time can be explained by the increasing entropy. I don't want to overclaim that seems to be true. The actual explanations are, in many cases, yet to be constructed. We are working hard to explain memory, prediction, causality, evolution, all of those other time-directed processes in terms of entropy, but our deep down theoretical understanding seems to say that that is the way it is going to work. The question is, why is the universe like this? Why did we start with such low entropy? It's not surprising, the first part, where we say there are more ways to be high entropy than to be low entropy. That doesn't seem to need to be explained. What needs to be explained is why the universe started in such a small subset of all the different configurations it could have started in. We don't know the final answers, but at least we know enough to talk about the different alternatives intelligently, to put them on the table and wonder which one is going to eventually turn out to be right. Essentially, there are three options when it comes to trying to figure out why the early universe started with a low entropy. So some of them are better than others, but we'll discuss all of them and you can decide for yourself. The first option is that despite everything we think we know about the fundamental laws of physics, maybe there is an intrinsic arrow of time there. Ever since Galileo and Newton, our attempts to develop deep down laws of physics have been time symmetric, have been reversible. They conserved information. They have the property that if you go from one state to the next, you know exactly where you came from if you keep track of exactly where you are. All of the information at one moment of time is preserved as you evolve through time. But maybe you could imagine that's just wrong. Maybe we have even better laws yet to be discovered that do not conserve information, that are not reversible. Maybe entropy is something that has an intrinsic arrow of time. This is obviously something to think about. We're trying to reconcile the fact that the deep down laws don't have an arrow and the manifest laws do. Well, maybe the deep down laws do too. That's just an obvious thing to consider. The problem is we need to think very, very carefully about what that would mean. Remember, it is easy to get entropy to increase with time. You don't need to come up with new laws of physics to get entropy to go up. What you would be trying to explain is the low entropy of the early universe. So what that means is if you have dynamical laws that pick out a direction of time, they need to be laws that make entropy spontaneously decrease. You need to start with a high entropy universe, apply the laws of physics to it, watch the entropy go down and down and down, and then imagine that we live in that universe, but we perceive it in the other direction. We remember the direction of time in which entropy was lower. We predict the direction of time in which entropy was higher. But in this hypothetical viewpoint, the laws of physics would work backwards from that. This is not hard to imagine laws of physics that are like that. For example, we talked about on a billiard table, it is low entropy when all the balls are sticking in one place. It is high entropy when all the billiard balls are scattered around the table. Imagine laws of physics which, instead of an absolutely perfect frictionless billiard table, we had one end of the billiard table be sticky. So we have four walls in a rectangular table. Imagine all the balls can bump into each other, but whenever they hit one of the walls, they just stick there. So in that case, it would naturally happen that as the balls move around the table, occasionally they would hit that wall and they would stop. You could start with a high entropy configuration where all the balls are scattered around the table. You would end with a low entropy configuration with all the balls stuck to one wall. That is a decrease of entropy. It is an irreversible process. Once you got to that wall, you wouldn't know where you came from. The thing is that it doesn't seem to be our world. There's nothing in the laws of physics that seems to act like that. And it seems just sort of implausible intuitively that you could start with an empty universe expanding with dark energy and form very, very gradually galaxies backward in time, undo everything that we know, have laws of physics that explain why scrambled eggs naturally turn into eggs, why glasses of water naturally form ice cubes, all the way to a reversed time Big Bang, and say that that is our universe. It's worth emphasizing that the past hypothesis, this idea that our early universe started with low entropy, is both necessary and sufficient for explaining the arrow of time. You will sometimes read papers in the physics journals or news articles that say a new theory explains why there is an arrow of time. And this new theory is based on quantum mechanics or gravity or something like that. You should not believe any of these purported explanations unless they tell you why our early universe was hot, dense, and smooth. Because that is sufficient. If you explain why our early universe is hot, dense, and smooth, then you have explained the arrow of time. After that, entropy increases, which is the most natural thing in the world. It is also necessary because our early universe really is hot, dense, and smooth. Therefore, it really does have low entropy. So the thing to be explained is the conditions that we think actually obtain in our early universe. That's the only thing you need to explain, as far as we know, to account for the arrow of time. The intrinsic arrow that you might try to build into the laws of physics, that doesn't seem to explain the past hypothesis. It might be possible to invent laws like that, but no one knows how to do it. There's no empirical evidence that that's the way physics works, so this is actually not a very popular approach to explaining the arrow of time. The second option is that maybe there's just a reason why the initial conditions were like that. All we need to do is to explain why conditions near the Big Bang had a very low entropy. Maybe it's just true. Maybe there's no bigger dynamical framework in which that comes to be like that. Maybe it's just a fact. Maybe even God made it that way. That could be true, but as physicists, we would like to do better. We want a physics-based explanation for why the early universe was in a certain configuration. And you can try to do that. You can say maybe the quantum state of the universe is the simplest possible. This is the approach favored by Stephen Hawking and other people. They want to understand the Big Bang from a quantum gravity point of view. They don't want to imagine there was something before the Big Bang. They want to say, yes, this was the beginning. Yes, the entropy was low. And there's some principle of nature that explains why that makes sense. That principle of nature can't be that most possible universes look like that. That is simply false. The actual configuration of stuff in our actual early universe is a very tiny fraction of all the different possible ways it could have been. So it might be simpler to start with a low entropy early universe, but we don't seem to have a principle that says the early universe had to be simple for that reason. It seems fairly arbitrary to simply say the early universe was just like that. Furthermore, it seems to not really fit to the universe that we see. Our universe has 100 billion galaxies with 100 billion stars per galaxy. It's much more extravagant than just us. If you want to believe that the early universe simply had a low entropy, that is one thing. But why did it have a low entropy with so many particles? Why such a big universe in such a hugely low entropy state compared to how high the entropy could have been? Again, this is very much on the table. You have to accept that this could be the way the universe is, but I think we need to think a little bit more deeply about why it would be like that. And there's some philosophy question as well as physics question. What counts as an explanation? At what point do we just say, this is how it is, versus at what point do we just say, we can do better? There needs to be some reason why it is like that rather than some other way. The third option, besides it is just like that or the laws of physics have an arrow of time, is that the arrow of time arises spontaneously out of the natural reversible evolution of the universe. In other words, the universe does not have an arrow of time in the laws of physics, but the solutions to the equations of the laws of physics always do have an arrow of time. This is actually a very common phenomenon in physics, where the symmetries of specific solutions to equations are not the same as the symmetries of the equations. As a very simple example, think of Newtonian mechanics. Newtonian mechanics is the paradigmatic example of no arrow of time built in. It's perfectly reversible. Laplace told us that if you know the state of the universe in Newtonian mechanics at one time, you know it at all other times. But it's not hard to think of examples of systems obeying the rules of Newtonian mechanics where you automatically get an arrow of time. Think, for example, of a ball rolling down a hill. But because this is a thought experiment, think of an infinite hill. Think of a hill that never has a bottom, it just goes on forever. So you imagine you see the ball at some point in time, it is rolling down the hill, and there's an arrow of time. It is moving from left to right. It has a direction in which it is moving. Now, if time is truly infinite, we can imagine tracing the past of that ball. So it's moving from left to right at the moment we see it, but we can go to the past. It's reversible according to Newtonian mechanics. It would go up the hill. But if it's moving at a finite speed, and the hill just grows higher and higher without bound, then it only has a certain amount of energy, this ball. So when we go backward in time, it slows down as it's climbing the hill, and we eventually reach a point where the ball was stationary. And then before that, the ball was actually moving in the opposite direction. So the whole history of this ball rolling on the hill, for all eternity, is that it spent an infinite amount of time rolling up the hill, it reaches a turning point, and then it spends an infinite amount of time rolling down the hill. The reason we know that must be what it's doing is because that is the only thing you can do in this system. There is only one kind of trajectory. If the hill always has a slope, the ball can never remain stationary. So this is a restless system. This is a physical system obeying Newton's laws, which are perfectly reversible, but one that doesn't have an equilibrium. It doesn't have a place it can sit. If you put the ball on the hill, it will start rolling. If you let the ball roll forever without disturbing it, it will roll forever except for that one moment when it was perfectly still. The question is, could the universe be like that? Could the entropy of our universe be like the position of the ball? It's just an analogy. It's not an exact physical equivalence. The question is, could we live in a universe where the fundamental laws of physics say that entropy doesn't have a maximum value? If entropy doesn't have a maximum value, it becomes much less mysterious why we are not in the maximum entropy configuration. There is no maximum entropy configuration. Entropy can always grow without bound. The key point of this way of thinking is that there is infinitely far for the ball to roll and an infinite time to do it. There is an infinite amount of entropy that can be generated in our universe, so this theory would say, and there's also infinite time to do it. That's easy to imagine in the context of a toy model. That toy model creates an arrow of time spontaneously because the ball is almost always rolling in one direction or the other. The difficult question is, can we really make a realistic cosmology that makes our universe be like that? Can we invent a theory of physics where the entropy of the universe can grow forever, there is no equilibrium state, but more importantly and trickier, the way that entropy grows is by creating universes like ours. In other words, by creating regions of space that look like our hot Big Bang in a low entropy configuration where it expands and cools. That's not easy to do. Even if entropy can grow forever and ever, that certainly doesn't automatically explain why our local region of universe once had such a low entropy. We need to do much more work to create a physical system where you naturally create regions where the entropy looked like a low value that we had at the Big Bang. This is where inflation and the multiverse might come in. One way of thinking about it is to say, what we really want to do is explain why we're not in equilibrium, why we don't already have the highest entropy we could possibly have. So we argued before, when we were talking about the evolution of the universe, that our entropy is increasing. It will continue to increase for quite a while. Our far future, a Google years from now, will be empty space. We're imagining that the dark energy is truly vacuum energy. It's truly constant. It's going to stay there. That might not be right, but it's the most plausible theory we have right now. So when we say high entropy, when we say thermal equilibrium, what that means is empty space, a universe that is expanded, emptied out, and cooled until there's nothing there. But we said that when you apply quantum mechanics to such a universe, there are fluctuations, there is radiation. Just like Hawking says black holes radiate, the whole universe radiates in the presence of vacuum energy. So there will be thermal fluctuations. Occasionally, very, very rarely, there will be so much thermal energy generated just as a random fluctuation that you can make an atom, or you can make a molecule, a DNA molecule, or you can make a person, or a planet, or a solar system, or a galaxy, or the universe. The bigger thing you want to make, the longer you need to wait for the random fluctuations, but they will all eventually happen. If you want to explain our reality, you want to have that kind of system that we said could be real, But instead of fluctuating into individual brains or individual solar systems, you want to fluctuate into the entire universe. Now that sounds difficult. We said that the universe has a much larger entropy than just a little planet or just a little person. And we also said that it's easier to fluctuate entropy a little bit than a lot. So how in the world would you think that it's easier to fluctuate a whole universe like we live in than just a person? It sounds like this scenario just gets us Boltzmann brains, not the universe in which we live. And the answer might be in inflation. Remember, the idea of inflation is that you can start with a very, very tiny region of space, 10 to the minus 30 centimeters or smaller. And if that region of space has just the right conditions, if it's dominated in energy by this temporary dark superenergy, then that tiny region will expand by an enormous amount. No matter how tiny it started, it can grow into a universe as big as we see. So the point is that maybe, even though it would be very, very rare to fluctuate 100 billion galaxies, maybe it's not that hard to fluctuate into this little bubble that is ready to inflate. It is true that the entropy in that region, we said that the entropy in the region ready to inflate is very, very low, but that's not a disadvantage in this particular situation. The point is that this little bubble is not the whole universe. We're not fluctuating from the whole huge entropy of the universe, all of it into that little bubble. We're just saying that this little bubble of space is a tiny fluctuation. The rest of the universe remains unchanged. So it's actually quite a small cost to fluctuate into this little bubble ready to inflate. Now, let's put this together. It's very, very speculative, so I don't want to say that it's all settled, but let's ask what this would look like. What we're saying is that we have empty space, nothing but vacuum energy, and the very, very cold thermal radiation, 10 to the minus 30 Kelvin, that you would expect just because of quantum mechanics. You get random thermal fluctuations all the time. Occasionally you fluctuate into Boltzmann brains and Boltzmann universes, etc. But we're saying that there is a new kind of fluctuation. We take advantage of the fact that space itself is flexible. So maybe you can fluctuate not just electrons and photons and quarks and so forth. Maybe you can fluctuate the shape of space. Maybe space itself can bend and pinch off a little bubble that is full of dark energy that is ready to inflate. And so that little bubble separates from the rest of the universe and it becomes what we call a baby universe. Through a fluctuation of space-time combined with the fluctuation of the fields that live in space-time, we can create a whole new universe in a very tiny region of space. The best thing about this theory is that it doesn't end. That little universe that we make, that little baby universe that is a bubble of space-time that pinches off and goes its own way, costs exactly zero energy. Inflation is the ultimate free lunch. So you have empty space. You evolved from empty space, which is in a pretty high entropy state, to a similar looking universe, again, empty space in a high entropy state, plus a little bubble. That little bubble can inflate, expand, reheat, and look exactly like our Big Bang. That is a way that what you thought was a high entropy state, what you thought was equilibrium, could be shown to really not be equilibrium. This is a new way to increase the entropy when you thought you were at the maximum entropy. You were not correct. You can always increase the entropy of the universe, according to this way of thinking, by creating new universes that split off and go their own way. So this little baby universe that you make can expand, make people like us cool off, and become high entropy itself. And then this process continues forever. The original universe we started with can create more and more baby universes. Every baby universe can expand, cool off, and become high entropy, then create more baby universes itself. This is a way to make real the hope that our universe could have a potentially infinite entropy, that there is no thermal equilibrium state. The universe never stops evolving because you can always create more universe. One of the interesting spins on this scenario is that you can play the same game backward in time. Imagine that there's one moment in the history of the universe when all you have is this big empty universe with high entropy. You evolve it, according to the laws of physics, forward in time. You make baby universes and make more entropy. You also evolve it backward in time according to the laws of physics. And because the laws of physics are reversible, you get the same answer. You make more universes toward the past as well as toward the future. Inside every one of those universes, there is an arrow of time that is pointing backwards compared to ours. Of course, our arrow of time is pointing backwards compared to them. The point is that just like the ball rolling down the hill comes from infinitely far away and goes to infinitely far away, it's doing the same thing in the far past as the far future. In this scenario, the universe is doing the same thing in the far past and the far future. It's growing, expanding, creating more and more entropy. Now, this is one of my favorite theories. I've worked on this kind of proposal myself. I don't want you to buy it. I think it is an example of the kind of thing we are looking for. There's much unknown physics lurking here. We don't know whether, in fact, you can make baby universes. There are some who have argued very strongly that baby universes simply don't exist. Even if you could make baby universes, this scenario very much has the measure problem. There's an infinite number of things happening. How do you compare the probability for one thing to the probability for something else? The answer is we just don't know. There is one question that it answers, which is, why do you get universes rather than brains? How do you solve the Boltzmann brain problem? The claim in this scenario is that it is actually easier to make a whole new universe than it is to make a brain. A brain, has a few kilograms worth of stuff, 10 to the 25 particles in it. But because of inflation, a universe doesn't need 10 to the 25 particles. It can have almost no particles at all, just a really tiny bubble of space filled with dark energy. That will expand and cool and create as many particles as you like. Entropy can always increase. The number of particles is not conserved. This kind of scenario tries to take advantage of the flexibility of the universe according to the laws of general relativity and quantum mechanics to escape the trap of thermal equilibrium. Given the flexibility of space and time, given the quantum mechanical freedom to fluctuate into different things, maybe there is no maximum entropy state the universe could be in. This relies on a whole bunch of assumptions that we don't know how to test, that entropy can always increase, that time goes on forever. There's other ways out, of course. If time is finite, if the Big Bang was really the beginning, if there's really an end at some point in the future, then there is no Boltzmann brain problem. We shouldn't be accepting that one or another of these proposals is right. We should be investigating all of them. The real question is, how will we know? How will we test whether one theory is right or another? The short answer is patience. It is absolutely true that ultimately science is always empirical. We will not decide which theory is right just on the basis of thinking about it. We will only ever decide which theory is right by comparing the different theories to data. But it might take a very long time to develop these theories before we can compare them to the data. People are trying right now. My personal belief is that we're just not there yet. Our understanding of the multiverse, inflation, and so forth isn't good enough to compare them to the data we actually have. We need to push on our understanding of cosmology, particle physics, gravity, not to mention how complexity and entropy evolve through time, and eventually we'll be able to really understand what our theories predict. Once we get there, we can compare them to the data and try to make a choice about which theory is right. So that's where we are. That is where we find ourselves in our quest to understand the mysteries of time. We personally are organized systems. We are very low entropy. We have a lot of complexity and a very low entropy. But we are not flouting the second law. We are not just ignoring the laws of physics. We are manifestations of the second law. We are side effects of the universe's increasing entropy. If the universe were in thermal equilibrium, intelligent life would not exist. Life, consciousness, processing information, metabolizing, thinking, feeling, existing, talking, communicating, all of these require a departure from thermal equilibrium. In that sense, we are very fortunate to live in a universe with such a pronounced arrow of time. The reason we have this arrow of time is because of the early universe. It's because of the conditions in the early universe that we have aging, metabolism, memory, causality, everything that to us distinguishes the past from the future. One way of thinking about it is we are surfers riding a wave of growing entropy. The wave started at the Big Bang 13.7 billion years ago. It's riding along and it will continue to do so for billions of years. Eventually it will peter out. Eventually, we'll crash upon the shore, and at least locally, we will be in equilibrium. We are riding that wave. We are side effects. We are parasitic upon the fact that entropy is increasing. Someday it will go away. In the meantime, we can enjoy the ride. Thank you for sharing some of the time you have with me. By this point, we're beginning to put together a comprehensive theory. Remember, our goal is to basically understand, why do I remember yesterday and not tomorrow? What's the origin of the difference between the past and the future? Well, we said that the origin is that the entropy was lower yesterday, and the reason the entropy was lower yesterday is because it started low near the Big Bang. That's the next question, and in the last lecture, we gave you 3 different ways of thinking about the Big Bang. One is that it could be the actual beginning to the whole universe. Another is that it could be a bounce. There could be a symmetric version of the universe on the other side of the Big Bang. And the third way is that the Big Bang could just be one of the things that happens from time to time in the history of the universe, and we could live in a very large multiverse. The problem with the first 2 ideas is that even if we have those theories of the Big Bang, making the entropy low at that point seems arbitrary. There seems to be no good reason why the entropy should be low at the moment we call the origin of our observable universe. The third scenario, the multiverse, it's at least possible to imagine explanations for why the entropy was so low. So in this lecture, we're going to dig a little bit deeper into that possibility of a multiverse. To do that, we have to start off with some sort of general philosophical statements. The idea of the multiverse, if you hang around with the kind of people I hang around with, gets people very worked up. You get an emotional response to the scientific hypothesis that the universe we see is not all there is. Some people love the idea. They think that it truly helps you understand all sorts of features of the universe we do see that would otherwise be mysterious. Other people think that the multiverse is a capitulation to the forces of anti-science, that because you're invoking all these things that can never be observed, this is not how true science should be done. I want to take a middle ground. I'm actually very willing to consider the multiverse as a serious possibility, but I don't think that we know that it's right. We're very, very far away from saying that the multiverse makes predictions that fit data we have. Nevertheless, it's also wrong to think of the multiverse as non-scientific. The ultimate goal of science is to find the truth. And according to the modern physics that we understand, the idea that there is a multiverse is very, very possible. It is something that could be the truth. So it's our duty to figure out what we can learn about what the multiverse would teach us, and if we can make any progress on it. If not, then we should abandon the idea, but we're nowhere near the point yet where that statement could be made. So to think about the multiverse and how it could be part of science, I like to tell a little parable. Imagine that there was a world that was much like ours. The conditions were very similar, except that it was always cloudy. It was always 100% completely overcast. And the temperature down on Earth was always exactly the same, on this planet, I should say. So what would the scientists on this planet think? If they were at a primitive stage of development, they were not able to develop yet satellites or ways to go above their atmosphere, they would think about the universe in terms that did not involve what we think of as the night sky. They wouldn't know there were other stars in the sky. So to them, their planet was the whole universe. That is all that they can see. And at some point in their intellectual development, one of their philosophers comes along and says, well, maybe there are lots of planets. Maybe we live in a universe that has many other planets just like ours. It's just that we can't see them because our atmosphere is opaque. And of course, his philosophical collaborators would say that is nonsense. You're invoking all of these parts of the universe that can't be seen. That's not how science or philosophy works. We should stick to observable things. The point is that when we talk about the multiverse, we're not invoking a new kind of thing. We're just saying that there is the universe that we live in. There's only part of it that we can see. Because there is a point past which we can't see, what is out there will never be directly observable to us. That is not what we're imagining, that someday we'll build a multiverse telescope. But there's still the question, is there only a finite amount of stuff out there? Is there an infinite amount of stuff out there that goes on exactly like the stuff inside? Or is there an infinite amount of stuff out there and conditions are very different from place to place? In some sense, assuming that the entire rest of the universe is infinitely big and just like the region we see, is just as presumptuous as assuming that there's an infinitely big universe where conditions are very different from place to place. Both options are absolutely on the table. The question is, does choosing one over the other matter to how we think about the universe that we do see? So the point is that imagining that there is a multiverse changes what we consider to be interesting questions to ask about the universe in which we live. Think about our foggy planet. Think about the planet where you can't see other parts of the universe. The scientists on that planet might have the question, why did we get lucky enough that the universe has exactly the right temperature and conditions for our civilization to arise? They live on a very temperate planet where the temperature is the same everywhere, and it is very hospitable to life arising. And they ask themselves the question, why is that the case? Why are the laws of the universe such that we can live here on our planet? How lucky, how finely tuned was that? Of course, we know better. We know that it's not lucky or weird or fortunate at all that they could live on their planet because there are many planets. There are 100 billion stars in our galaxy, and the best current estimates is that there are probably more planets than stars. There are billions and billions of planets just in our galaxy, and 100 billion galaxies in the universe. Eventually, you will get one where the conditions are just like that. So knowing that they lived in a universe where there are other planets changes our hypothetical scientists' way of thinking about what is an interesting question versus a not interesting question. If you live in an ensemble, if you live in a universe where conditions are very, very different from place to place, there are selection effects. You will only find yourself in the parts of that universe that are hospitable for you being there. If you live in a unique universe, then you have a challenge. How can you once and for all explain the conditions of this unique universe in which you live? Our universe could be either way. We don't know. The cosmic microwave background in our universe functions exactly like the opaque atmosphere in our hypothetical planet. It's a barrier past which we cannot see. We look out into the sky, we look with light, with visible light, with radio waves, etc. But the early universe was opaque. We will never be able to see beyond it using light. So there's literally a barrier past which we can't see. There is the rest of the universe that might be like ours or might not. We need to take both possibilities very, very seriously. Now, when we do that, we necessarily start invoking the anthropic principle. We already mentioned the anthropic principle. There's different versions of it, and some of them sound more profound than others. I like a sort of simple version of the anthropic principle that simply says if there are many different conditions throughout our universe, our multiverse, whatever you want to call it, intelligent beings like ourselves will only find ourselves in the middle of those conditions that are compatible with us existing. Now, we don't know what are the conditions for intelligent life generally. That's why applying the anthropic principle in practice is very, very hard. My personal opinion is that people assume way too much about what we know about life and intelligence and consciousness when they actually try to put the anthropic principle to work. I think there are many, many different ways that you could get complexity and intelligent life. Until we have a much more developed theory of complexity, consciousness, and intelligence, we can't use the anthropic principle in too quantitative a way. But we can still use it in a rough, qualitative way. The example that I gave before was, we're not surprised that we live on the surface of the Earth rather than the surface of the Sun, or in between the planets in the solar system. Even though there's a lot more area and volume outside the Earth is a very hospitable place to live. Nobody considers it a profound question, why are we living here rather than on the Sun? As a more specific cosmological question, it might be that the anthropic principle is the explanation for the vacuum energy that makes the universe accelerate. We talked about the idea that the universe is accelerating, there's an explanation for it, that empty space itself has an energy density, the vacuum energy, the cosmological constant. Now, you might be surprised that there can be vacuum energy at all, but it turns out that's the wrong direction for your surprise to go. Once you understand that there can be such a thing as vacuum energy, as a physicist, you sit down, you do a back-of-the-envelope calculation saying, well, how big should the vacuum energy be? It turns out that you can have a classical contribution to the vacuum energy that would be there as an unknown constant of nature, even in ordinary general relativity. That's what Einstein discovered. But there are also quantum mechanical contributions. All of the particles in the universe vibrate in hidden ways in the virtual particle sense. That is to say, even in empty space, these particles are there providing energy. These are contributions to the vacuum energy. You add them all up and you get a huge number. The real puzzle of the vacuum energy is not why there is vacuum energy, but why is it so small compared to its natural value? The answer might be the anthropic principle. Think about what the world would be like if the vacuum energy were huge. It would cause space to accelerate very, very quickly. In fact, you can easily do the calculation and say that if the vacuum energy had its natural value, you couldn't have atoms. You couldn't even have a nucleus of an atom. The vacuum energy would rip things apart so effectively, you couldn't make a single molecule. So we imagine that under those circumstances, you couldn't make life. This is not 100% because we don't know what life is. We don't know under what conditions it could exist. But if you can't make atoms, it's very plausible you can't make life. You could also have a large vacuum energy, but a negative vacuum energy. A lot of vacuum energy, but with a different sign. Instead of making the universe accelerate, it would make the universe recollapse. And then again, you can easily do the calculation, and you can show that if the magnitude were the natural value, the universe would recollapse in a tiny fraction of a second. Even if the local physics allowed for the existence of life, there wouldn't be time for it to evolve. Whereas, if the vacuum energy is small but not zero, then there's plenty of time for life to evolve, and there's nothing to stop molecules from forming. So Steven Weinberg, who won the Nobel Prize for particle physics a long time ago, in 1988 made a prediction. He said that if the vacuum energy is not a constant of nature, if we live in a multiverse where the vacuum energy takes on very different values from place to place, then it can't be too large, it can't be too negative. He predicted that if that were the universe, we should observe a non-zero vacuum energy with a certain typical value. In 1998, when we discovered that energy density, when we discovered that the universe was accelerating, it was exactly the same, to within the quite substantial error bars, as Weinberg's prediction. So in other words, under this huge set of assumptions that there is a multiverse, that we understand how life can form, etc., the anthropic principle made a prediction for the vacuum energy and it came out right. The question is, can we explain other things about the universe? People are trying. Can you explain the mass of the Higgs boson, for example? But what we can't do is explain the entropy of the early universe just using the anthropic principle. Remember, in Boltzmann's scenario, where you have an infinitely big universe with fluctuations, you can fluctuate to lower entropy and then bounce back. But we only need a very, very tiny fluctuation of entropy to make a person, or even to make the Earth, compared to the huge fluctuation of entropy that our actual universe represents. In other words, if you tried to do the same thing that Weinberg did, but with entropy rather than the cosmological constant, you would predict that the entropy of the early universe is much, much larger than it actually is. So even if the anthropic principle can explain the vacuum energy, it can't explain the entropy. We need to do better. Nevertheless, even if the anthropic principle is not by itself explaining the low entropy of the early universe, the multiverse might still be part of the explanation. It's important to emphasize that the multiverse is not a theory by itself. The multiverse is a prediction of other theories. It's not that a bunch of cosmologists sat around and start saying, well, wouldn't it be amazing if there were lots of different universes? That would change how we think about everything. That's not the way people became interested in the multiverse idea. It started from other theories that we believe for other reasons, and we realized that those theories predict the existence of a multiverse. The most basic of those theories is inflation. We thought that inflation is a good idea because inflation helps explain things we observe. It explains why the spatial geometry of the universe is flat. It explains why there are tiny ripples, but only tiny ones, in the universe from place to place. It starts with a very tiny region, expands it tremendously, and then you reheat. It's plausible physics. We think we understand how inflation works. But almost as soon as inflation was invented, people started investigating it a little bit more carefully. In particular, they started taking this story and putting it in the context of quantum mechanics. Quantum mechanics says that things fluctuate. You don't predict exactly what will happen. You predict different probability distributions. So in inflation, you have this super dark energy. It expands to make a big region of space, and then that dark energy decays into ordinary matter and radiation. That's the process called reheating. What happens if you add quantum mechanics to that process? What happens is space can expand and grow, but you don't predict that it certainly turns into matter and radiation at a certain place. You predict that there's a probability. You have this dark energy field that makes inflation go. It reheats with a certain probability. It's just like a decaying particle, remember. A muon decays, but we can't predict the exact lifetime of any one muon. We can predict the probability per second or per microsecond that the muon will decay. Likewise, for inflation, we can predict the probability that any one region of space converts from dark superenergy into ordinary matter and radiation. So maybe what happens is you take a little region of space, it expands to a big region, and perhaps 90% of that larger region reheats. Its dark energy converts into ordinary matter and radiation, and in the aftermath you get something that we would call the Big Bang. But that means that in 10% of the space, inflation does not stop. It does not reheat. It keeps on being dark superenergy. So that 10% keeps inflating. That is to say, even though the rest of the universe is still expanding, it is decelerating. It's slowing down because now it's ordinary. Now it's matter and radiation. In that 10%, where quantum mechanics says it did not turn into ordinary matter and radiation, inflation keeps going, so the size of that universe expands much more quickly. Then after a certain period of time, 90% of that region can reheat, turn into ordinary matter and radiation, and become a Big Bang. But 10% keeps inflating and then again keeps growing. What happens is you keep creating more and more regions of space where inflation is still going on. Even though in any one region, 90% of it will stop inflating pretty soon, the 10% that keeps inflating keeps growing in size by a tremendous amount. So in actual cubic centimeters, the region of space that is still inflating grows without bound. Inflation never ends in this scenario. This is called, for obvious reasons, eternal inflation. It's a very natural marriage between inflation and quantum mechanics. Remember, inflation is the ultimate free lunch. Once you start it, you get as big a universe as you want. The theory of eternal inflation, which is just quantum mechanics combined with inflation itself, says that you can get a very different universe from place to place. You get one little region where you've reheated and you've created a Big Bang, other regions where inflation keeps going. So that is the simplest way to get a multiverse. Remember, it didn't come out of a desire to get a multiverse. It just came out of taking inflation seriously. We think that quantum mechanics is the right way of thinking about the world. If you think that inflation is also the right way of thinking about the early universe, eternal inflation is very, very natural. Now, if it is the case that every time inflation ends, you create ordinary particles like ours, protons and neutrons and electrons and whatever the dark matter is, then what eternal inflation would give you is a big collection of universes just like our own. We call them universes. In fact, Guth calls them pocket universes, little regions of space that have their individual big bangs where inflation ended, but they're just separated in space itself. We call them different universes even though they're connected. They're in between the regions that are still inflating. But it could be that there are different kinds of regions. So this is another variation on the same theme. One way that eternal inflation can happen is to create many, many regions of universe just like ours. But another way eternal inflation can happen is to create many, many regions, each of which have different local laws of physics. This is not, again, completely made up. This is a consequence of other theories that we know and love. In particular, in this case, string theory, which is the leading candidate to reconcile quantum mechanics and gravity. Just like inflation, string theory is a theory that we don't know whether it's right or not. We don't have direct experimental evidence, but it seems to be on the right track. One of the major problems with string theory is that it says that space-time has at least 10 or 11 dimensions. That seems to be an obvious conflict with experiment because we only have 4 dimensions of space-time. But it turns out that in general relativity, it's not difficult to hide extra dimensions of space. You can curl them up into a little ball, a little geometry of some shape and size, so small that you and I would never notice them. Once you realize you can do this, it's actually very easy to do this. The problem is it's not unique. There's not one way to hide the extra dimensions of space. There are a gazillion ways of hiding the extra dimensions of space. We try to estimate how many ways there are. We get numbers something like 10 to the 500. That's obviously not a very precise number, but it gives you a feeling for the fact that there are many, many ways to hide all these extra dimensions that string theory predicts. The reason why that matters to our current discussion is that every different way of curling up the extra dimensions affects what we call particle physics, what we would call the mass of the elementary particles, the charges of the elementary particles, the different forces through which they interact, the ranges over which those forces stretch, and even the number of dimensions. Maybe you curl up 6 dimensions, but maybe you only curl up 5 or 4 or 3 of them. So basically, every one of these possibilities is a different way the universe can be. It's a different phase of the universe. Just like water can be liquid water, water vapor, solid ice, string theory says that space-time can have different phases. Corresponding to each different way, you can curl up the extra dimensions. If we combine string theory with eternal inflation, we bring a very wildly varying multiverse to life. Inflation says you can make different regions of space. String theory says that the local physics in all those regions can be very different. For example, you can have different kinds of elementary particles, so life could be different. Maybe in some of these regions, you can't have any kind of life at all. Maybe in other regions, you get exactly our kind of life. In still other regions, you get a very different kind of life. Another thing that can be different is the vacuum energy. Steven Weinberg just assumed that the vacuum energy was different from place to place when he made his prediction, but string theory brings that to life. String theory says, here is how you could actually get different amounts of vacuum energy in different regions of the universe. So it's by combining inflation with string theory that we get the multiverse. You could have a multiverse even without string theory, but the different regions of space would all be different. The important thing is that we didn't just invent the multiverse from the start. It is a prediction of other theories, inflation and string theory, that we like for other reasons. Still, what we'd love to do is to be able to test this prediction. It's one thing to have a prediction, it's another thing to know that it is right. The single biggest problem with the multiverse hypothesis is that it is difficult to test. We are never going to go visit one of these other regions, they're too far away. So if they're there, we need to look for some reason why we should believe them. And basically there's two possibilities. One possibility, which is the winning the lottery possibility, is that you directly look for evidence of other universes. Now, I just said we can't go there and we can't see them, so how can you directly look? The answer is that another universe with different local physics could literally bump into ours. In the early moments of our universe, as it stopped after inflating, if it stopped inflating, turned into ordinary matter and radiation, maybe nearby another universe came into existence because inflation stopped in another region. That universe also grew and literally bumps into ours. It would leave a tiny relic of the radiation and the energy from that universe heating up our cosmic microwave background. So what you look for in the data are little circles in the microwave background where other universes bumped into ours. People have looked for such evidence, and they have found that maybe they're there. In other words, the data that we have on the microwave background right now aren't good enough to rule out the idea, but it's also not good enough to say that these other universes really are there. To be very, very honest, this is a long shot. It's probably not going to happen, but it would be incredibly, amazingly exciting if you actually saw evidence for a different universe in the cosmic microwave background. The more likely scenario is that we get indirect evidence in favor of the multiverse. One thing to do is to make statistical predictions, just like Weinberg did for the cosmological constant, make predictions for other parameters of particle physics that we haven't yet measured. So we have, for example, dark matter. We know that there is dark matter. We see the evidence for it in astrophysics and cosmology, but we haven't detected it yet in the laboratory. Could we use the anthropic principle and the multiverse to explain that a certain kind of dark matter is more likely than another kind? Could we use the anthropic principle in the multiverse to make predictions for the Higgs boson that hasn't been discovered yet, for supersymmetry or other hypothetical aspects of particle physics? This is very, very difficult to do, but this is the more likely way that we'll think that the multiverse is on the right track, if we can use it to make predictions which then later come true. The problem with this hope is that the multiverse idea might be right, but that doesn't mean that we understand it. In particular, there is a puzzle associated with the multiverse called the measure problem. This is different than the measurement problem of quantum mechanics. The measure problem says that if you take the multiverse seriously, everything that can happen, and it will happen an infinite number of times. So what we want to know, for example, is how many observers would observe a small vacuum energy, how many observers would observe a large vacuum energy. So we can calculate some probability. You should probably observe the vacuum energy to be a certain number. The problem is, if you take the multiverse at face value, the answer is an infinite number of observers measure a certain value, and an infinite number of observers measure this other value. How can you compare them? How can you say that one infinite number is bigger than another one? This is not just annoying. This could be a really profound problem with the multiverse idea. It might be that even if the multiverse is real, we will never be able to use it to make predictions. This is an honest problem with the multiverse that even its advocates need to admit. Now, there are people trying. There are certainly many attempts, many models, many theoretical proposals on the market for how to make believable predictions in the context of the multiverse. But it's very hard to know whether you're on the right track. We don't have data that says, oh, one proposal is right or one proposal is wrong. So the real lesson here is not that the multiverse is useless or that it's a panacea. The lesson is that the multiverse is a speculative idea that is not yet developed well enough by theorists to make firm predictions. Maybe it will be developed well enough, or maybe it won't, but it just takes time to do it. So the reason we think about the multiverse is not that we know it's there. And it's not even that if we knew it was there, it would make a definite 100% prediction about the universe. It's that when we think about the puzzles we face in explaining the universe we do see, whether or not there is a multiverse changes the way we think about the universe that we actually do observe. If we are part of an ensemble, then the kinds of questions we ask and the kind of answers we would give are different than if we are a unique universe. Just like our planet with an atmosphere, knowing that they are just one of billions and trillions of planets would change the questions they ask about the conditions they find themselves in. In particular, we care about the past hypothesis. Why did the early universe have such a low entropy? The question is, could we address that by imagining that our universe is not unique? If the universe we see, if the local observable universe is the once and for all universe, then we have a real puzzle. Why, in this one appearance of the universe, did the entropy start out so small? If there is a multiverse, if there are many, many individual sub-universes, then we have a different kind of question. Can we make a model, can we make a theoretical understanding of the multiverse in which almost all universes have strong arrows of time? Is it natural for a universe to begin with very low entropy? That's the kind of idea that we can try to develop. The way that we're going to do this is not by waiting for the multiverse to show up. That would be great, but it's unlikely for it to happen. What we want to do is to have better ideas about fundamental physics. The real way to move forward with the multiverse idea is to understand how gravity and quantum mechanics and particle physics play well together. We need to develop at least one well-defined, unambiguous theory. The lack of data, the lack of direct experimental input, would be really a problem if we had more than one theory and we were trying to decide which one was right. But right now, when it comes to explaining the past hypothesis, we have 0 compelling theories. We have not even one theory that is absolutely clear and consistent and predicts the data that we see. Therefore, it's not a matter yet of deciding between different theories on the basis of experiments. It's a matter of understanding the questions we're asking and developing that kind of theory. That's work which we can in principle do even without experimental input. It's very, very hard, and we might fail. It might turn out that our human brains are just not quite large enough to figure out how the universe or the multiverse work without direct experimental input. We might have to wait 1,000 years for some brilliant insight to come along. But we might have to wait 6 months. We don't know until we try. It's a matter of the experimentalists and the theorists, and for that matter, philosophers and mathematicians working together to try to build a theory that will explain the universe we see. So far in these lectures, we have not shied away from speculating. We've talked about time travel, we've talked about Boltzmann brains, we've talked about some of the frontiers of neuroscience. But even when we've been speculating, they've been grounded speculations. In other words, we haven't ever seen a Boltzmann brain, but that's a prediction of a theory that we understand pretty well. We've been talking about speculations within the context of a theoretical framework that seemed to be right to us. When we talked about time machines, we asked, what does general relativity have to say about time machines? But for the next couple lectures, we're going to be doing speculative speculations. We're reaching a point now where what we know about the universe is not good enough. We've discussed what the universe is, how it has evolved, and we've come up against the fact that the entropy of the early universe was really, really tiny. We don't know why, and so we're going to have to imagine what the possibilities are. So from now on, for the next couple of lectures, we're going to be putting out scenarios, none of which are backed up by data or even fully fleshed out theories. That's okay, that's what life is like at the edge of research. We're trying to understand the universe and trying to ask the questions to which we don't yet have answers. In particular, in this lecture, we're going to talk about the Big Bang. Not the Big Bang model that says we began in a hot, dense early state, but the actual moment of time, the initial singularity. Sometimes people say the Big Bang and they mean the early universe. They mean that moment really early on when we think the entropy of the observable universe was about 10 to the 88th. It was very smooth, it was very hot, it was very dense, it was rapidly expanding. But today we want to go right down to time equals 0. If we extrapolate backward, Einstein's equation for general relativity, given the conditions in the universe as we understand them, we hit a singularity, a moment when the expansion rate was infinity, the density of the universe was infinity. That's what we call the Big Bang. Notice that it is a time, not a place. It is a moment in the history of the universe, not a location in a pre-existing universe. The Big Bang was not an explosion of stuff in an otherwise empty space-time. It was all of space-time as far as we know. The Big Bang is just like the singularity of a black hole, except backwards in time. The singularity of a black hole is a moment you reach in the future once you cross the event horizon, a singularity where the curvature of space-time is infinitely big. The Big Bang is a moment you hit as you go to the past. It's a singular moment, but it's not one that you could possibly avoid. If we imagine hypothetical travels backward in time, it's not like you can deviate from your path and miss the Big Bang. It's not a place, it's a time. It's a time when everything blows up and we need to do a better job of understanding what was really happening. So we know that in the early universe, it was very, very dense, it was very smooth. The matter in the early universe, the part that we understand about 1 second after the Big Bang, when there was nucleosynthesis that gives us data about what was going on, the matter was essentially in thermal equilibrium. It was as smooth as it could be, it was as hot as it could be, as long as we ignore gravity. We can't ignore gravity, of course. That's why we have this mystery in front of us. Maybe the answer to that mystery can be attained by going all the way back to time equals 0. So you will sometimes hear cosmologists talk as if they know what happened at time equals 0, at the moment of the Big Bang. You will hear them say that there is no such thing as time before the Big Bang, that that's the moment when the universe came into existence, that asking what is before the Big Bang is like asking what is north of the North Pole. It's not that we don't know yet, it's that there is no answer to that question. But that's a little bit misleading to talk that way. It is a prediction of Einstein's general relativity that as you go backward in time, you hit this singularity. But a singularity doesn't mean a boundary to space-time when you take it seriously. What it means is our equations blow up. If general relativity, as Einstein wrote it down in 1916, were the correct theory of reality, then the Big Bang would be the beginning. You cannot go past that singularity. But we know that general relativity is not right. We don't know it on the basis of data. Every experiment we've ever done, every astronomical observation we've ever made is perfectly compatible with general relativity. But we know that general relativity can't be right because as a theory, it is classical. It is not compatible with what we know to be quantum mechanics, the right theory of how the world works, as far as our experiments tell us. To reconcile general relativity with quantum mechanics, we need a theory of quantum gravity. Just like quantum mechanics says if you have an orange, it can be here or there. In fact, it truly is in a superposition of both possibilities until you look at it. Whereas a classical theory would say the orange is here or there whether you know. Classical general relativity says there is a geometry to spacetime. There's a certain amount of curvature, there is something spacetime is doing. Quantum gravity would say there's a wave function of spacetime. There's a set of possibilities for what spacetime would look like if we were to observe it. That is the theory we want to have, but we don't yet have it. And people say this over and over again, and it's true. We don't yet have a theory of quantum gravity, but I don't want you to think that we know nothing at all about quantum gravity. We know how quantum mechanics works. We know a lot about how classical gravity works. So it's not that we are completely clueless. We actually know what quantum gravity should be like in certain regimes, even though we don't have the right theory. We know that quantum gravity should reduce to classical general relativity in our solar system, for example. We know that 1 second after the Big Bang, the universe was doing more or less what classical general relativity says that it should do. So we are not completely without guidance. We can try to see what a full theory of quantum gravity would tell us and use that to understand the Big Bang. From the point of view of this course, we can also say we know the early universe had a low entropy. Maybe that fact about the universe is a clue that should help us understand how quantum gravity works. The right theory of quantum gravity is one that will help us understand why the early universe had a low entropy. So what does such a theory say about the Big Bang? Again, since we don't have it, we don't know the final answers. But what we can do is list the possibilities that people have thought of. We have more than one plausible scenario about what could have occurred at the Big Bang. One scenario was that the Big Bang really is the beginning, that our classical intuition from Einstein's general relativity, that there is no such thing as before the Big Bang, maybe that's just as true in quantum gravity as it is in classical gravity. Maybe time doesn't go forever. This would be a surprise from one point of view because in all of the ordinary quantum mechanical theories we understand, time does go forever. But gravity is not ordinary in this sense. We have to take seriously the possibility that gravity, added to quantum mechanics, makes time come to an end at the beginning of the universe, an end in our past. That would be a universe that essentially comes into existence out of nothing. It's very difficult to describe this accurately because our human vocabulary doesn't have the right words. We say the universe could be created from nothing. That sounds as if there was nothing, and for a little while, nothing sort of lingered on, and then the universe came into existence. That's not the right way to think about it. This nothingness we're talking about is not a way of existing. It's not an absence of anything. It is not even a thing, not even a state of the universe, not even a quantum mechanical possibility. When we say creation from nothing, that's really just a vocabulary term for saying time comes to an end. There is no moment before the Big Bang. This kind of scenario is what is favored by Stephen Hawking, for example. He talks about the wave function of the universe and tries to solve equations for the wave function of the universe that would describe a universe that looks like ours today and came into existence at the Big Bang. Not at a moment of time, but time itself came into existence along with the universe. That is an absolutely plausible scenario given what we understand today. The question is, does it help us explain the arrow of time? And the answer is it depends on what that wave function of the universe is. It could be just a new law of nature or a new feature of the world that the wave function of the universe says the universe is created, comes into existence at this moment, and when it comes into existence, the entropy was very low. That might be a way the universe works. In some sense, it would be disappointing if that were true, because we're not learning anything new over and above the fact that the early universe had a low entropy. This encourages some of us to try to think even a little bit closer about what the alternatives are. One alternative is a bouncing universe. So maybe there was a universe before the Big Bang that essentially was the time reverse of what we call the Big Bang. At least some sort of universe that was contracting. There was matter and energy that was getting closer and closer, more and more dense. And somehow the magic of quantum gravity, rather than collapsing it to a true singularity, caused it to bounce back and create what we call the Big Bang. So there's different ways to play this game. The question from our point of view is, in the pre-existing universe, in the universe that was contracting and getting more dense, was entropy going up or going down? In some sense, the most natural thing would be for the entropy to be going down as it approached this bounce. After all, it goes up after the bounce. So if the bounce, that we now call the Big Bang, is a moment of symmetry in the history of the universe, then the entropy goes up in both directions away from the bounce, both toward the past and the future. In some sense, that's an aesthetically appealing universe. It looks symmetric. The far, far past of that universe would look like the far, far future. And this Big Bang moment is the one special time. This big bounce is the one time in the history of the universe when entropy was low. On the other hand, it's a little bit disappointing because we still have the question, why was the entropy so low at that point? What is the principle of nature that says that when the universe bounces, the entropy should be low? There could be some principle. It could be that we need to look for it. We need to do a better job, so that is absolutely on the table, but we're still trying to do even better to try to find a dynamical reason why the entropy had to be low at the earliest times. So the third possibility on the table is what we call the multiverse. The multiverse is not the same as a bounce, where the whole universe was contracting, bounces, and then creates our Big Bang. The multiverse says that our Big Bang was just some kind of event that is really quite tiny in the history of a much larger universe. The multiverse theory says that, look, we only see a finite bit of universe. What right do we have to extrapolate what we see infinitely far? Maybe further away, much, much further than what we can actually see, the universe looks very, very different in different places. So what cosmologists call the multiverse is really a mundane thing in some sense. It's just the idea that far away from us, things look very different. It's not truly separated universes disconnected from us. It's just regions of space that we don't see because light can't get to us from them. That is a way of thinking about how our Big Bang could have come into existence. Clearly, to make it more sensible, we're going to need some physics that would bring the multiverse into existence. There is a theory on the market that was not invented because of the multiverse, but sort of gives some credibility to the multiverse idea. That theory is called inflation. Inflationary cosmology was a scenario invented by Alan Guth, a physicist at MIT, back in 1980, which purports to explain why the Big Bang looked the way it did. We are dealing with the past hypothesis, the idea that the early universe had a very, very low entropy. The low entropy of the early universe is only one of the interesting features of the early time. Inflation was invented not to explain why the entropy was low, but to explain certain other curious features of our universe on very large scales that can be traced back to the beginning. The nice thing about inflation is that it is based on sensible physics. In other words, even though we don't yet know whether inflation is true or false, the physics underlying it seems very, very plausible. We don't know that it's right, but it doesn't require great leaps of faith. Maybe physics works in a certain way. Given the way that we do know physics works, it seems natural for something like inflation to happen. To understand how inflation works, you can go back to the idea of dark energy. Remember, dark energy is something that doesn't dilute away as the universe expands. Einstein tells us that the rate at which the universe expands depends on the energy density of stuff. If you have a universe full of ordinary matter and radiation, stuff dilutes away as the universe expands, and the expansion rate slows down as time goes by. If you have a universe that is dominated by dark energy, something that doesn't dilute away or dilutes away only very, very slowly, then the expansion of the universe actually accelerates because space gets bigger and bigger, but every cubic centimeter of space has the same amount of energy. So that pushes on the universe a little bit, and we observe that as an accelerated expansion. So the idea behind inflation is to basically play exactly that game, but play it at much higher energies at the much earlier time when the universe began. So imagine a temporary phase of super dark energy. Not energy that is super dark, but dark super energy. Dark energy with a really, really high energy density. Remember, at early times in the history of the universe, matter was compacted to a much greater density. So to start the universe, inflation says maybe there's dark energy that has an enormous amount of energy in every cubic centimeter. So what would you have if instead of ordinary matter and radiation, the early universe had nothing but this dark super energy filling it? Well, what would happen is you get an accelerated expansion, and the universe would grow by an enormous amount. The rate at which you expand depends on the energy density. So if the energy density is very high, the universe expands very, very quickly. Now, while that happens, unlike ordinary evolution with matter in it, where perturbations grow, where small variations in density get increased by the force of gravity, if the universe is filled with dark energy, the universe smooths out. So if you have an initial universe with super dark energy in it and variations from place to place, as inflation occurs, as this expansion and acceleration with the super dark energy happens, any perturbations get smoothed out. It's like you're pulling on the edges of a sheet, smoothing out the wrinkles inside it. So after just a very, very short while, the universe goes from whatever state it was in to a much larger configuration, very smooth over very large distances, full of this dark super energy. What you need to have happen then is this dark energy needs to go away. We don't live in a universe full of this kind of dark energy. You need to convert that dark energy into ordinary matter and radiation. That's a process known as reheating. It is something we know how to do. In other words, this is not just words. We write down theories with equations. We invent fields that would have given us this dark superenergy in the early universe. And the physics of these fields is like that of a particle that decays. Remember, we talked about muons, or for that matter, neutrons, particles that don't last forever. They last for a little while and then they decay into other particles. Likewise, the quantum field that was responsible for inflation could decay after a certain amount of time. And when it decays, it basically turns into other particles. They decay and interact, and they turn into a hot, dense gas. So what inflation gives you is you start wherever you start, but with a universe dominated by this dark energy, you expand by a huge amount, you smooth everything out, and then suddenly, all throughout the universe, you convert all of that energy into ordinary matter and radiation. What are you left with? A universe that is very hot, very dense, very smooth, and very rapidly expanding. In other words, something that looks exactly like our Big Bang. So the wonderful thing about inflation is it starts with a very specific initial point, but one that is not implausible. You can imagine that for some reason the universe had this dark energy in it. And after that, very, very plausible physics leads you to something that looks exactly like our early universe. Looks like the Big Bang with small deviations in density from place to place, but basically a hot, dense, rapidly expanding universe. When inflation came along in 1980, people were initially a little bit surprised and skeptical, especially astronomers who liked to see data, and this seemed like a very wild, far-out idea. But more and more over time, inflation has become to be accepted. Even though we still don't know for sure whether it happened, it is the predominant theory among early universe cosmologists. In modern cosmology, all discussions of the early universe begin by imagining that there is inflation. You can still imagine alternatives, and people talk about them a lot, but inflation is the dominant paradigm right now. There are a lot of benefits to believing that inflation happened. Let me just name one of them, namely that the universe can start very tiny. Now, you might not imagine that that is something necessary. After all, the universe was smaller at earlier times, so it was tiny whether or not there was inflation. But there's a quantitative difference. If you imagine the good old Big Bang cosmology, a universe filled with matter, radiation, dark matter, and so forth, if you take our current observable universe, so the 100 billion galaxies that we see with the 100 billion stars inside them, no dark energy, no inflation or anything like that. Just play the movie backwards and ask, when does the density of matter become so high that we would call that the Big Bang? And ask, how big is the physical size that expanded into our universe? The answer is about 1 centimeter across. So the actual size of the whole observable universe when the universe started in conventional cosmology is about 1 centimeter. Now, that's very small from one point of view. It's something that we need to try to imagine stuffing 100 billion galaxies worth of stuff into that 1 centimeter across. But by particle physics standards, 1 centimeter is huge. It's much, much bigger than an atom or an elementary particle. The question is, why would the universe be so incredibly smooth over this 1 centimeter size? That's basically a restatement of the past hypothesis. Why was the entropy of that 1 centimeter region so small compared to all the fluctuations, all the ripples and inhomogeneities that we could have fit into that little 1 centimeter sphere? In inflation, on the other hand, if you trace our currently observable universe backward in time, it can start with a region that is in size about 10 to the minus 30 centimeters across. In other words, the same amount of stuff that we see today, when you trace it back in time to the Big Bang, could have all began in a region 10 to the minus 30 centimeters across. That's much, much smaller than 1 centimeter across. It is much, much more plausible to many people that there is some particle physics reason why a 10 to the minus 30th centimeter universe started in exactly that state. We don't know what that would be, but that's one of the benefits of inflation to start the universe going, you need a much smaller region than in conventional cosmology. There are other benefits of inflation that are sort of more popular, the actual benefits that people talked about when Guth invented the idea. One is it explains the spatial geometry of the universe. Remember, we talked about the fact that there's Euclidean geometry. When you have parallel lines that are initially parallel, they remain exactly the same distance apart. When you take a triangle and add up the angles inside, they always add up to 180 degrees. That is a flat geometry. That's the geometry of the tabletop. But there's also spherical geometries with positive curvature, where initially parallel lines come together. There is saddle-like geometry, where initially parallel lines move apart from each other. So you might ask, when you look at the universe on very, very large scales, if you drew a triangle between three galaxies billions of light years apart, would the angles inside add up to 180 degrees? Is the large-scale spatial geometry of the universe flat or curved? The answer is it seems to be flat. We have observations that say that the overall geometry of the uniform universe on very large scales is indistinguishable from Euclidean geometry. We don't see any obvious deviations, any spatial curvature, either positive or negative. Why is that? We don't know exactly, but if you believe in inflation, you could have had quite a substantial curvature at early times, and that process of inflating would have flattened it out. So inflation predicted the universe would be flat, and it predicted it back in 1980. It was not observed to be flat until the 1990s. So this was a prediction that was made before the observation. Inflation helps explain the spatial geometry of the universe. It also explains the fact that the universe is smooth over great distances. When we look at the radiation from the cosmic microwave background, it's more or less the same temperature in every direction. We're looking, when we do that, at radiation that came to us from different ends of the universe. So there's a question you can ask, how does it know to be the same temperature, even though it's millions of light years away, at a time when the universe was only hundreds of thousands of years old? Well, inflation explains that, because this process of inflating smooths everything out, both the overall spatial geometry and the small-scale perturbations. But at the same time, because of quantum mechanics, inflation says that you can't make it perfectly smooth. If there was just inflation in a classical universe, there would be no way of understanding why there was any deviation in density from place to place in the early universe. But you add quantum mechanics to the mix and you predict that there will in fact be perturbations, that some regions are slightly more dense than others. And the pattern of perturbations predicted by inflation is exactly what we observe in the cosmic microwave background. This is why, even though we're not sure that inflation is happening, it's a very good theory that a lot of people like to think about. It made predictions that fit the data. There is a conceptual question that inflation raises, which is, where does all that energy come from? You start with a tiny little region, and you expand it into 100 billion galaxies. The short answer is, energy is not conserved. I know that we've said in other contexts that energy is conserved, but the expanding universe is different. One way of thinking about it is that in the expanding universe, there's energy in stuff. That means dark energy, matter, radiation, dark matter, whatever. There's also energy in space-time itself, the energy of the curvature of space-time. The energy of stuff is positive. Real particles weigh a certain positive number. The energy of space-time is negative. In a compact universe, or a universe that is perfectly smooth everywhere, the total energy is exactly zero. This is just a remarkable fact about general relativity. The total energy of the whole universe is zero, because the energy of the stuff, of the matter and radiation, even including dark energy, is exactly matched by the negative energy of the curvature of space-time. So what that means is, as this universe expands, you create a tremendous amount of more energy in stuff, which is why I said energy is not conserved. That's because it's compensated by the energy of space-time itself. The moral here is that it costs nothing to make a universe. Alan Guth calls inflation the ultimate free lunch. You can get a whole universe by starting with essentially nothing. This is a feature of dark energy, but it was always a feature of general relativity. It's not something that is new to inflation or dark energy or any newfangled modern theory. Think about radiation. If you have a universe full of photons, every photon loses energy as the universe expands. the total energy density in a bunch of photons, like the cosmic microwave background, decreases as the universe grows. So decreasing is just as much not being conserved as increasing is. The simple statement is that the energy in stuff does not remain the same as the universe expands. You can get as much universe as you like from an arbitrarily small amount of energy. So inflation is a good theory. It's a very promising theory. It's the predominant way of thinking among modern theoretical and observational cosmologists. It says you can start with a tiny universe. It can grow to exactly the kind of universe that we see. For our purposes, what we want to know is, does it help explain why the early universe had a low entropy? That's what inflation is trying to do. It's trying to account for why our early universe looks the way it does. Remember, you don't need inflation to explain any feature of the universe whatsoever. It's not that the universe disagrees with a theory. It's just that our early universe seems finely tuned to us. Why was the universe spatially flat? Why were the density ripples so small? Why is the density approximately the same in different parts of the universe? These are all facts that simply could be true. The answer might just be, well, that's the way it is. What inflation tries to do is give a natural explanation for these features. It says you shouldn't be surprised at all these facts because if you begin with a little region ready to inflate, that is what you will get. However, the question is, why did you begin with that little region ready to inflate? So one way of attacking that question is to think about entropy. Just like we could calculate the entropy of the hot, dense universe at the time of nucleosynthesis, we can calculate the entropy of that little patch ready to inflate. The answer is about 10 to the 10th. We don't have an exact number. It depends on when inflation started and what the energy density was. The point is that the entropy of that little region, that little proto-inflationary region of space, is much, much lower than the density after reheating, than the entropy, after reheating once you convert it into matter and radiation. Remember, we said the entropy of the early universe, our observable part of it, was something like 10 to the 88th. And now we're saying that the entropy of the inflating region is something like 10 to the 10. So on the one hand, it follows the second law of thermodynamics. If you start with inflation and end with the conventional early universe, entropy goes up. On the other hand, you haven't explained why the entropy is low. You've simply started in an even lower entropy configuration. So this is the puzzle that inflation leaves us with. It does not explain why the entropy of the early universe was low. It pushes that problem further into the past. It says the entropy of the early universe was low because it used to be even lower. Just like the past hypothesis says, the entropy of yesterday was lower than the entropy today because the entropy was even lower the day before yesterday. Inflation says the entropy of the early universe was low because it was even lower before that. Now, we want to do better. We don't want to simply say that's the way it was, inflation started and everything happened. We want to know why inflation started. So that means we need to go beyond this more or less well-defined theory of inflation and ask why the universe started like that at all. By this point, you're probably tired of hearing me say that the entropy of the early universe was small. In this lecture, I'm going to say that again and again, but we're also going to follow the evolution of the entropy through the history of the universe. We're going to start near the Big Bang, 13.7 billion years ago, and follow the physical processes that occurred as the universe expanded and cooled. And then we're going to track what the entropy was at each stage along the way. Unsurprisingly, we will learn that the entropy has been going up. The second law of thermodynamics is correct. And then we will follow the evolution of the universe past the present moment into the future. Most discussions of the evolution of the universe talk about between the Big Bang and today, but we know that that's just a prejudice. There's nothing special about the past versus the future. If you're going to talk about the whole history of the universe, you need to do the future just as well as the past. We can begin with the present. We look outside into the universe and we see galaxies. If you go out on a clear night, the first thing you see are stars. Galaxies are just collections of stars that are orbiting each other under their own mutual gravitational field. We live in a galaxy, the Milky Way galaxy. If you're blessed enough to have very clear skies and dark nights, then you can see the Milky Way stretching at nighttime from one horizon to the other. We're embedded in the disk-like structure of the Milky Way. It's a galaxy with about 100 billion stars. We're not getting exact numbers here. We're just trying to give you orders of magnitude. It's a good number to remember. 100 billion is about the number of stars in the Milky Way or any other typical galaxy. There are smaller galaxies and larger ones, but 100 billion stars is about the average. If we look out at the whole universe, we see that it is filled with many galaxies. In fact, there are about 100 billion galaxies in the observable universe, a similar number as there are stars per galaxy. Now, you might wonder about that observable universe a bit. You might say, well, as our observations become better and better, will we discover more galaxies? But when I talk about the observable universe, I'm not referring to our present technological capabilities. I'm talking about a matter of principle. Because the Big Bang was a finite amount of time in the past, and because the speed of light is a finite number, there's only so much universe that we can possibly see. There's a finite part of the universe outside of which, to get to us, light would need to go faster than the speed of light. So the observable universe is what we call the part of the universe that we can, in principle, ever observe. It's not that our technological capabilities are not better. It's just that that's all the universe that we can possibly see. We haven't seen anything like it yet. So when I say there are 100 billion galaxies, I'm not trying to imply we've counted 100 billion galaxies. We count very tiny slices of the universe and then we extrapolate to the whole thing. The nice thing about our universe on very, very large scales is that it seems to be uniform. If you look at large enough sizes of the universe, what you see is the same as if you looked at any other equivalent size somewhere else. So what NASA has done with its space telescope is to basically take the telescope and point it at a blank region of the sky, a region where it doesn't look like there's anything. It left the shutter open on the telescope for quite a while and just let the photons accumulate in the camera. And what you see when you do that is what they call the Hubble Ultra Deep Field. The Hubble Space Telescope has taken an image of the furthest reaches of the universe, and even though we didn't know there was anything there, we predicted that we would see lots of galaxies, and that's exactly what you do. When you look at this image, you see a tremendous number of little splotches. Each one of them is a galaxy in its own right, comparable in size to the Milky Way. So our present universe is an essentially uniform collection of galaxies, 100 billion of them, spread out amongst the universe with about 100 billion stars each. The most important other fact about the universe is that not only is it big, it is getting bigger. The universe is expanding. When we say the universe is expanding, what we mean operationally is that distant galaxies are moving away from us, and the further they are away, the faster they are receding. That's known as Hubble's law, named after Edwin Hubble, the astronomer who worked at Mount Wilson Observatory in California, who discovered this in the 1920s. It's interesting to think about the history of this discovery. It wasn't Hubble who found that distant galaxies are moving away from us. That was actually a different astronomer, Vesto Slipher. But what Hubble was able to do was to measure the distances to the galaxies. So before Hubble came along, people weren't even sure that what we now call galaxies are in fact separate collections of stars. They thought that they might be fuzzy nebulae here inside our galaxy. Hubble first showed that galaxies truly are distant, and then he was able to plot the speed at which they were moving away versus the distance to the galaxy. And what he found was that nearby galaxies are moving away slowly, further away galaxies are moving away more quickly. That is what we mean by the expanding universe. It's not just that all galaxies are moving away from us, it's as if space itself is expanding. And that's exactly, of course, what general relativity predicts. Space-time is dynamical. It's space itself that is getting bigger. When the galaxies move away, it's not that the galaxies are moving through space. It's that the amount of space between us and the galaxies is actually growing. So even though we see all the galaxies moving away from us, it's not because we're special. It's not because we're sitting at the center. If there's another galaxy you pick out far away, We are moving away from them, and the galaxies on the other side of us are moving away from them even faster, so they see the same thing we do. They see all the galaxies in the universe moving away from them. Every person in every galaxy thinks the universe is expanding, thinks that everything is moving away. That's the expansion of the universe. It's also interesting that Hubble never won the Nobel Prize. He really wanted to win the Nobel Prize, but back in the 20s when he made his discoveries and afterward, astronomy was not really counted among physics, which is what the Nobel Prize is given for. In fact, it wasn't until 2011 that the first Nobel Prize in physics was given for work in optical astronomy. Once we know that the universe is expanding, we can play the movie backwards. If galaxies are moving away from each other now, in the past they were closer together. So it's not right to say the universe was smaller. We often say that, but if you do say that the universe was smaller in the past or will be bigger in the future, just be careful to understand what exactly you mean. What you really mean is that galaxies were closer together in the past and they will be further apart in the future. The point is that we don't know the size of the universe. We know the relative size of different parts of the universe, and we know how that size changes over time. If you pick some fixed collection of galaxies, the region that is drawn by those galaxies was smaller in the past and will be larger in the future. But the universe itself might very well be infinitely big. It could be finite, it could be infinite. We don't know because we can only see a finite part of it. But even if the universe is infinitely big, if the spatial extent of the universe goes forever, we can still say it's expanding or contracting, because what we mean by that is that the galaxies were closer together or further apart. Now, if you keep tracing backwards in time, of course, 13.7 billion years ago, you hit a point where all the galaxies were on top of each other. That's the Big Bang. That's the point where the density of matter was infinitely big, and we need to think about what that means. Of course, this extrapolation isn't done naively. It's not just, well, the galaxies are moving away now, we naively extrapolate them back at the same speed. We use the general theory of relativity. Einstein gave us an equation that relates the rate at which the universe expands to the amount of stuff in the universe. So we have a very quantitative theoretical understanding of what the universe should have done in the past, and we can actually compare that to the data. Remarkably, the data that we have goes all the way back to the first 3 minutes in the history of the universe. From about a few seconds after the Big Bang to a few minutes after the Big Bang, the universe was a nuclear reactor. When all the matter in the universe was much more densely packed, it kept banging into each other, and the universe was a lot hotter. The temperature was extremely high. If you go far enough back, it was so hot that atoms could not exist, electrons could not stick to the atomic nuclei inside, and if you go more than a few seconds after the Big Bang, even nuclei could not exist. Protons and neutrons could not stick together. So as the universe expands and cools, it's the period between a few seconds and a few minutes where the protons and neutrons can finally stick together. In fact, there's a race. What the protons and neutrons want to do is fuse together to make heavier and heavier elements. But because the universe is expanding so quickly, they don't have time to do it. The density of the universe goes down very rapidly. Instead, a certain fraction of the protons and the neutrons get turned into helium, lithium, and deuterium. Deuterium is just hydrogen, one proton with an extra neutron. Deuterium is basically heavy hydrogen. So these three other elements, helium, lithium, and deuterium, are produced in the first seconds after the Big Bang. And if you have a theoretical understanding for what the density was, what the nuclear physics is, how fast the universe was expanding, you can make a prediction. You can say there should be this much hydrogen, this much helium, this much lithium, this much deuterium. And then you can try to check that against observations. It's not easy, of course, because in the later universe where we live, stars and other processes in the universe have changed the elemental abundances. But you can look for regions of the universe where that change has been minimal. You can look for regions of the universe where the abundances of different elements are close to primordial. The wonderful fact is that we've done that, we've made the observations, they match the predictions beautifully. In other words, we have data that tells us we know what the universe was doing just a few seconds after the Big Bang. We can, of course, go further than that. The That process, called Big Bang nucleosynthesis, was when the universe cooled down enough to let nuclei form. It wasn't until hundreds of thousands of years after the Big Bang that it cooled down enough to let atoms form. That's about 380,000 years after the universe got started. This process is called recombination, when electrons can finally stick to atomic nuclei to make atoms. After recombination, it's atoms that are in the universe, hydrogen and helium. Before recombination, it's nuclei and electrons. The reason why that's important is because when electrons are free to roam, when they're not stuck to atoms, the universe is opaque. The light that is in the universe, the light is filling the universe because everything is so hot that it is glowing, but you can't see your hand in front of your face if you were living during that period of the universe's history, because the light keeps bumping into the electrons. Once recombination happens, once the electrons get together with the nuclei to form atoms, the universe becomes transparent, and the photons from that period can move all the way across the universe to be detected in our telescopes. That was done in 1964 by Arno Penzias and Robert Wilson. They had a radio telescope at Bell Labs. They were trying to see how quiet the universe was because they were interested in communications. They were working for Bell Labs. What they found was there was some noise they could not get rid of in their radio telescope. Other physicists eventually let them know that what they had discovered was the relic radiation from the Big Bang, from just a few 100,000 years after the universe started. This is now known as the cosmic microwave background radiation because the wavelength is in the microwave regime. It's basically a snapshot of what the universe looked like at that moment in time when atoms were first formed. And what we see is a universe that is pretty smooth. It's not a universe that has galaxies, stars, planets, or anything like that. There are tiny fluctuations in the density of the universe from place to place. Basically, the early universe was much, much smoother than our current universe. Our current universe seems uniform on very, very large scales, but at the moment that the microwave background was formed, the universe was uniform on all scales. In fact, when Penzias and Wilson discovered it, and for decades thereafter, we couldn't detect any variation in the density of the microwave background from place to place. It wasn't until the Cosmic Background Explorer satellite, which was launched in 1989, that we finally were able to detect very tiny fluctuations in the temperature of the microwave radiation, just 1 part in 100,000. 1 in 10 to the 5 is the difference in temperature in the microwave background from point to point. This got the Nobel Prize for George Smoot and John Mather in 2006, the masterminds behind the Cosmic Background Explorer satellite. Later, in 2001, NASA launched the WMAP satellite, which gave us a much better view of this cosmic microwave background, basically the highly focused image of what the universe was like, the snapshot just 380,000 years after the Big Bang. So the early universe was fairly smooth, but there were tiny differences. In one region of space, there might be 100,000 atoms. In the region right next to it, there's 100,001. And in the region next to that, there's 99,999. There's fluctuations of about 1 part in 10 to the 5. But as the universe expands and cools, gravity turns up the contrast knob on the universe. If you have a region with a little bit more matter, that region has a slightly stronger gravitational field, so it pulls atoms that are nearby toward it. If you have a region that is slightly less dense than average, then it loses atoms to the rest of the universe, which is more dense. So as the universe expands and cools, you go from a very, very smooth universe to one where structure is forming. This is called the formation of large-scale structure in the universe. Some of those perturbations are fairly tiny. They grow into planets and stars and black holes. Larger ones form galaxies, and even larger ones form large-scale structure in the universe. As this process happens, as the initially smooth early universe forms structure, entropy increases. Remember, we talked about the fact that when gravity is important, high entropy does not mean smooth. High entropy can be very, very lumpy. The highest entropy of all would be to take all the matter you have and put it in one big black hole. So there is a misapprehension that sometimes gets passed around that I want to undo just in case you've been exposed to it, which says that in the early universe, because it was smaller, there was less room for entropy, and as the universe expanded, there was more and more entropy you could have. That way of thinking is just false. It's assuming that the early universe had to be smooth, but that's not true. The early universe could have been wild, roiling chaos. It could have been much more dense in one region than in another region. That would have been a much higher entropy configuration. If you took a high entropy version of the current universe and played the movie backward, there's no reason why the entropy would have had to go down. So the early universe having a low entropy is a fact that needs to be explained. It is not at all automatic. Of course, if the entropy had been higher, if the entropy had been as high as it could possibly be, we would not live in a universe with the second law of thermodynamics. The reason why there's a second law is because of the past hypothesis, the fact that the early universe had such a tiny entropy. That is what we would like to explain. Recently, relatively recently, we've learned a little bit about the future of the universe. In 1998, astronomers discovered that not only is the universe expanding, but the expansion is accelerating. What we mean by that is that if you look at one galaxy today, it looks like it is moving away from you, as Hubble discovered. What was discovered in 1998 was that if you came back 1 billion years from now and measured the velocity of that galaxy again, it would be moving away from you faster. Individual galaxies are moving away faster and faster as the universe expands. This was a complete surprise to everyone who tried to do these measurements. They thought they were going to be measuring the deceleration of the universe. What they actually discovered was the acceleration of the universe. The reason why this was a surprise is because if the universe is full of ordinary stuff, matter, radiation, atoms, dark matter, even dark matter counts as ordinary for these purposes, as the universe expands, everything pulls on everything else. You would naturally expect the expansion rate to slow down. Ordinary stuff does not speed up the expansion of the universe. So to account for the fact that the universe is accelerating, you need some non-ordinary stuff. The astronomers who discovered this are the ones who won that 2011 Nobel Prize for the acceleration of the universe. The question is, what is the non-ordinary stuff that is doing it, that is pushing things apart? Well, we have a name for it. We call it dark energy. And we even know some of the features of dark energy. The most important feature is that it doesn't dilute away as the universe expands. If you had a universe with nothing but matter and radiation in it, then as the universe expands, the number of particles, either matter particles or photons in radiation, doesn't really change in any one volume of the universe that is expanding. It's not that particles are being created or destroyed. So in any fixed cubic centimeter, the density of particles is going down. There's the same number of particles, but an increasing volume of space. That's why, in the ordinary way of doing things, the expansion of the universe slows down. There's less and less stuff in it to drive the expansion. But dark energy hypothesizes that in every cubic centimeter, there's some energy that doesn't dilute away, some amount of energy that is just stuck there that provides a perpetual impulse to the expansion of the universe. That impulse actually builds up as space itself gets bigger, and that's what makes the universe seem to accelerate. The best candidate for dark energy is called vacuum energy. So dark energy is just whatever it is that doesn't dilute away that makes the universe accelerate. Vacuum energy is a specific example of dark energy where the dilution is exactly zero and the density of energy is exactly the same in every point in space. It's also called the cosmological constant. It's what Einstein invented to make the universe static way back when. Now we think that the cosmological constant could be the best explanation for why the universe is accelerating. It's not the only explanation, of course. We can also have kinds of dark energy that are slowly varying so gently that we haven't yet detected it yet. And even better than that, we could have no energy at all, but a modification of general relativity. After all, our expectation that the universe should be decelerating is because that's what general relativity says. But maybe, in the late universe, on very, very large scales, general relativity isn't right. Maybe we need a modification of gravity. It is unlikely that that's true. It's a long-shot idea, but it's well worth considering. That's what theoretical cosmologists like myself do for a living. We try to propose models that explain why the universe is accelerating, and then we compare them against the data. But we have to admit that the simplest model is the one that is most likely to be right. Vacuum energy, the cosmological constant, a strictly constant amount of energy in every cubic centimeter of space. If that's the right answer, it has a profound implication for the future of the universe, namely that the expansion of the universe will continue forever. We're not going to recollapse because there's nothing pulling the universe back together. We'll just expand and expand and expand, and the future history of the universe will last forever. So this idea gives us a plausible future scenario for the universe. We don't know as much about the future as we know about the past because of the asymmetry of epistemic access. We can't see the future yet, but we can at least extrapolate our current theories. Right now, the age of the universe is roughly speaking 10 to the 10 years. 10 to the 10 years would be 10 billion years. The real age is 13.7, but roughly speaking, let's call it 10 to the 10 years since the Big Bang. What will happen in the future if the universe does not recollapse? We have stars that live in galaxies that light up the universe, but they are burning their fuel. There's only a finite amount of fuel per star. If you look at the smallest stars, which are the ones that last the longest, they will last about 10 to the 15 years before they finally burn out. So we have 100,000 times the current age of the universe before it becomes completely dark, but that will eventually happen. Even after the universe becomes dark, that's not the end of the story. These dead stars will not be radiating, but they will still exist, and they're going to gradually fall into black holes. Remember, the centers of galaxies have giant black holes in them. If you wait long enough, all of the dead stars in the galaxy will fall into that black hole. But even that black hole doesn't last forever. Black holes, remember, evaporate. So you can calculate how long will it take before all the mass of the galaxies falls into the black holes, and then those black holes radiate it all into empty space. The answer is about 1 googol years. In the old-fashioned sense of the word googol, 10 to the 100. So 10 to the 100 years after the Big Bang, there will be nothing left but empty space. The black holes will have radiated, but that radiation is diluted away as the universe expands and accelerates. So it is imperceptibly different from having nothing at all. And that, if the actual dark energy is completely constant, is the end of the story. After a googol years from now, we will have empty space, and that empty space will last forever. In other words, the highest entropy state the universe can be in is nothing but empty space. The universe is right now not high entropy. The entropy is growing. What happens when the entropy hits its maximum value? You reach equilibrium and evolution stops. In our case, that's when all of the black holes have evaporated away and you're left with nothing but empty space. Empty space is simple. Remember our cup of coffee example that starts simple before you mix it with the milk, becomes complicated, and then becomes simple again when it hits equilibrium. The universe does the same thing. It was simple at early times. It was very smooth. It's complicated now. Here we are, complicated beings. The future of the universe is empty space, nothing going on, simple again, and very high entropy. That would be the heat death of the universe. Rather than recollapsing and having a big crunch, the universe just calms down and becomes colder and colder and colder until it reaches equilibrium. However, there's a fascinating little extra fact that is forced on us by the idea of vacuum energy. If the universe is truly accelerating and that vacuum energy never goes away, it turns out that the accelerating universe is like living inside an inside-out black hole. What I mean by that is, a black hole is defined by the fact that there's a horizon. If you go inside, you can never escape to the outside. So there's a region of the universe where information can never reach us from. Likewise, if we live in an accelerating universe, think about a galaxy that is very far away. It's moving away from us faster and faster, eventually be moving away from us so fast that it's moving faster than the speed of light. This does not violate relativity. What relativity says is that two galaxies cannot pass by each other faster than the speed of light. But when space is expanding, the rules are a little bit different. A very, very distant galaxy can appear to be moving faster than the speed of light. What that really means is that the galaxy is moving away from us so fast that any light it emits never gets to us. The space in between us and that galaxy is just expanding so quickly that the light will never reach us. In other words, that galaxy is past a horizon. We live inside the horizon and we see it all around us. And just like Hawking says that black hole horizons give off radiation, they have a temperature and a black body radiation, likewise our universe, which has a horizon around us, has a temperature and gives off radiation. So when you live in this purportedly empty universe, the far, far future where all the stars have died and all the black holes have radiated away, you don't live at absolute zero. There's still a non-zero temperature. If you had a thermometer or a particle detector, usually it would be perfectly quiet, but every now and then, a very, very low energy photon would come along and hit it. You would measure a non-zero temperature. Now that temperature is very, very tiny. In numbers, it's about 10 to the minus 30 degrees Kelvin. Our current microwave background, which is pretty cold, is about 3 degrees Kelvin. So 10 to the minus 30 is an incredibly tiny temperature. But it's still not zero. So what the scenario means is that we have an eternal universe that lasts forever. There's a fixed volume that you can see inside our horizon, and inside that volume there is a temperature that never changes, a temperature that is just constant forever. If this reminds you of something, it's Boltzmann's scenario for the understanding why the early universe had a low entropy. Remember, Boltzmann, who didn't know anything about the Big Bang, dark energy, or quantum mechanics, imagined an eternal universe that had some fluctuations, had some particles that were just moving around with some temperature, and every once in a while those particles would form a low entropy configuration. They would form a planet, or if you wait long enough, they would form a galaxy, or even longer than that, they would form the whole universe. We said that that can't be right, but if it were right, you could have all of these things happening. It turns out that our real world seems headed for exactly that situation. If you take seriously the idea that we have a vacuum energy that will not evaporate away, we will live in an eternal universe with a temperature, and in that universe there will be fluctuations. And those fluctuations will make planets and people and galaxies. It might take an enormously long time to fluctuate back into the whole universe. You would need 10 to the 10 to the 120 years to fluctuate back into a situation where you had 100 billion galaxies. But you have forever to wait. Compared to forever, 10 to the 10 to the 120 years is really not that long. So here's the depressing aspect of that story. If this is the right cosmological scenario, we should be Boltzmann brains, or the universe around us should have just fluctuated randomly into existence. We don't believe that is true, and therefore there must be something wrong with our current best understanding of cosmology. This idea that I've been talking about, the universe expanding under the influence of vacuum energy, this isn't wild and speculative, this is our best fit to the current data. But if it's right, something goes terribly wrong in the far, far future. There is an escape hatch if that vacuum energy isn't truly permanent. If the vacuum energy at some point in the future goes away, then you can avoid these disastrous consequences. But that's telling us something very, very interesting about how vacuum energy works. So in the long run, what we will get is not just a universe with vacuum energy. Something has to happen. The vacuum energy has to decay or change into something else. Otherwise, we would be Boltzmann brains. So we can now put numbers on what the entropy of the universe does. Remember, we have an observable universe that is only so big. It's a finite-sized thing, so the entropy of it is not infinite. At very, very early times, when there was no structure, no planets, no black holes, that entropy was about 10 to the 88th. Basically what we're doing is we're ignoring the effects of gravity simply because the self-gravity of the particles was not that important. The universe was smooth. There weren't any structures formed by gravity. You can just plug in 19th century formulas for what the entropy is, and you get about 10 to the 88th. Today, on the other hand, we have black holes in the universe. Most of the universe has black holes at the centers of galaxies, and most of the entropy of the universe is in those black holes. So even though we don't have a perfect formula for the total entropy, we can add up all the entropy in black holes and get a good answer. It's about 10 to the 103, much larger than 10 to the 88th. In the future, you can get the maximum entropy that you could possibly imagine from all of the stuff that we see in the universe today. The answer is about 10 to the 120. It's a much larger number yet than the 10 to the 103 that we have today. That would be the equilibrium version of the universe, the configuration we could be in where the entropy was maximal. We argued that it looks like empty space. So the real challenge for cosmology is simply, why aren't we in equilibrium? Why don't we live in empty space? Why aren't we a random fluctuation in the thermal atmosphere that an empty universe would have? We clearly need to change our cosmological theories to explain why we see what is around us. The last lecture on time travel was a bit of fun, something of a palate cleanser. It did not actually address our main concern, which is the arrow of time. What it did really is to say that we're on the right track in asking that kind of question. We said that time travel to the future is possible. Time travel to the past doesn't happen. We don't think that there are any closed time-like curves in our universe. The good news for us with our concern for the arrow of time is that the question is therefore well posed. If there were closed time-like curves in the universe, then there is no division of space-time into past, present, future. So how could the past and the future be different if they get all mixed up? But in a world without closed time-like curves, we know which is the past, which is the future. We can ask why they're different. So from now on, for the rest of the course, we're focused more or less like laser beams on this question of why the early universe had a low entropy. Why is the past hypothesis true and useful in our universe? And we're given both an opportunity and a bit of a puzzle. Both come from the fact that gravity is of crucial importance in the early universe. We said that we live in a universe that it is expanding. If you go backwards in time, all the galaxies, all the stuff in the universe were crunched together. And if you go 13.7 billion years into the past, you hit the Big Bang, the moment of infinite curvature, infinite density. That's the place when our equations break down and we don't know what to talk about. So the opportunity that is presented is that the Big Bang clearly plays some crucially important role. If we were to understand it better, we would have a chance of knowing why it has such a low entropy. Before there was any such thing as the Big Bang, if in Boltzmann's time, before Einstein came along, there was no special moment in the history of the universe. Newton said that time just goes on forever and any moment should be predictable from any other moment. It might be that what we call the Big Bang is truly special for some reason. Either it was the real beginning of the universe, or it came out of some very different process. Either way, it makes sense to us that there's something there to be explained. If we understood the Big Bang better, maybe we would understand why the entropy of the universe was so low at that time. The puzzling aspect to us is that we don't understand the Big Bang very well. The Big Bang is clearly a moment in the history of the universe where gravity is of fundamental importance. All that matter so close together, space-time expanding so quickly, you can't ignore gravity when you get to the Big Bang. But as we mentioned, gravity and quantum mechanics don't play well together. We don't have a sensible, definitive theory of quantum gravity. Gravity is the only force of nature for which that's the case. We have all the other forces put into a framework of quantum field theory, which is based on quantum mechanics. So gravity is the only force of nature where we don't understand what is going on at the microscopic level. And that's exactly what we do need to understand when it comes to the Big Bang and entropy. We want to be able to calculate what the entropy was in order to explain why it was so small. And that's hard to do if we don't understand how general relativity and quantum mechanics are ultimately reconciled. One way to think about this is to go back to Boltzmann's understanding of entropy. The equation engraved on Boltzmann's tombstone is S equals K log W. The entropy is a constant, K, times the logarithm of the number of microstates that are macroscopically indistinguishable. Our problem as cosmologists, as people who are trying to understand the Big Bang, is that we don't know what W is. We don't know the whole space of possible states because we don't understand that until we understand the quantum basis for gravity. So if we don't understand the whole set of states, we don't certainly understand how to chunk up those states into macro states that look the same to us. From some point of view, it's like we are Clausius before Boltzmann came along. We understand something about entropy, but we're not dealing with the fundamental theory. Boltzmann had atoms. Clausius just had the phenomenological theory of thermodynamics. Our present understanding of gravity comes from the classical theory of general relativity. That's kind of like thermodynamics. It's a very, very good theory within its domain of applicability. But in the domain we care about, when gravity becomes very, very strong and quantum mechanics becomes important, it's not good enough. We need to do a little bit better. We need to understand how entropy works, what the formula for entropy is when gravity is very important, and right now we don't understand that. Except for one shining counterexample, and that is black holes. We talked about black holes and what they are. The great news for us in our quest to understand entropy is that black holes are places where gravity is incredibly important. They're the places where gravity is more important than anywhere else in the universe, and we do know what their entropy is. So it turns out that if you have some complicated, messy situation like the solar system, where you have the sun made of gas and the earth and the other planets made of different things, and they have a gravitational field and the gravity can change and maybe there's gravitational waves and radiation, we don't have a formula that tells us what the entropy is in that situation. But in the black hole situation, where everything is maximally simple, we actually have a formula that was given to us by Stephen Hawking. To get to that formula, we should start thinking about classical black holes. Black holes as Einstein would have thought about them, even though the name black hole was not invented until long after Einstein had passed away. It turns out that black holes in classical general relativity are actually very simple things. It might be hard to understand what's going on, but they're not difficult to characterize which black hole we're talking about. Once you tell me the mass of a black hole, the electric charge that it has, and how fast it's spinning, there is nothing more to tell me about it. You have completely specified the black hole. This is completely unlike a planet. If you tell me the mass of a planet, the electrical charge of the planet, and the spin of a planet, you're nowhere close. You need to tell me what it's made of, what the atmosphere is, what kind of mountains and oceans it might have. Black holes have none of those things. This is called the no-hair theorem. All black holes are bald. They all look the same. Once you tell me the mass, charge, and spin, there's nothing more to tell me about it. So we think of such a black hole as a place from which nothing can emerge. You go into the black hole, you can never come out. It was therefore extremely surprising when, back around 1970, Roger Penrose, who we talked about earlier because he has been emphasizing the need for a cosmological explanation for the past hypothesis, Penrose showed that you can actually extract energy from a black hole. Not any old black hole, but some black holes are spinning very rapidly, some are not spinning at all. And Penrose showed that if a black hole is spinning rapidly, there's something we can do to slow it down and in the process extract some of its energy. The mass of the black hole actually decreases as it spins more and more slowly. But of course, there's only a finite amount of energy that you can get out. The black hole is spinning at some rate. You can get energy out of it, but you slow it down in the process. Once you're done, once it's no longer spinning, there's no more useful work you can extract from that black hole. So those words should sound familiar. You have a situation where you can extract useful work from a system. Once you extract a certain amount of useful work, it reaches a stage where there's no more useful work to get out. This is exactly the situation when we're talking about a thermodynamic system approaching thermal equilibrium. Just like the gas in our piston, if it's in a low entropy state, we can extract useful work from it. But once you reach equilibrium, there's nothing more we can do. Penrose is saying that there's a black hole that you can extract useful work from, extract energy that you can use to do things, but there's a point of no return where the black hole stops being useful to us. This idea was developed over the early 1970s into a whole little subfield of study called black hole mechanics. The idea was there was an analogy between how black holes behave and thermodynamics. In thermodynamics, we have the energy of a system. For a black hole, we have its mass. E equals mc squared tells us that mass is just a type of energy, so that's an obvious analogy. In thermodynamics, we have a temperature. In black holes, we have the surface gravity. Now, you might think that the surface gravity of a black hole should be infinitely big. Once you go inside, isn't it true that the force is so strong you can never come out? And that's true. But surface gravity is a technical term, which means if you were very, very, very far away from the black hole, and you got a little weight and you lowered it into the black hole on a string, when the weight approaches the event horizon, how strongly is it tugging on you? It's true that if you were standing next to the weight, the tug would be infinitely strong, but it sort of dilutes as you go up the string. And so from a point infinitely far away, there's a finite strength of force that the black hole exerts on you. That's called the surface gravity. That is analogous to temperature in the rules of black hole mechanics. And finally, in thermodynamics, we have the idea of entropy, of course. In a black hole, the idea is that this is the area of the event horizon. Even though as you extract energy from a spinning black hole, its mass goes down, you're extracting useful work from it, the area of the event horizon goes up. That's because a spinning black hole is kind of squashed. It becomes more spherical as you spin it down. So the entropy keeps going up, just like in a thermodynamic system, entropy keeps going up. In fact, there's a whole set of rules that are completely analogous between thermodynamics and black hole mechanics. In thermo, we have the zeroth law that says that if you put two systems together in another system, and they're all in thermal equilibrium, they will all have the same temperature. Likewise, the zeroth law of black hole mechanics says that the surface gravity is the same everywhere on the horizon of a black hole, whether it's spinning or charged or what have you. You can measure a surface gravity, it's going to be the same everywhere, just like the temperature is the same everywhere in equilibrium. The first law of thermodynamics says that energy is conserved, and so does the first law of black hole mechanics. It says that mass is conserved. There's different ways to give the black hole energy with spin and charge, but it doesn't change over time. It's the second law, of course, that is most interesting. The second law of thermodynamics says that the entropy of a closed system only increases. So the analogy in black holes is that the area of the event horizon only ever increases. And in fact, this is a theorem that was proven by Stephen Hawking, the famous area theorem of black holes. The area of the event horizon only goes up. You can change its shape, but you cannot ever make it smaller. The third law of thermodynamics says that you cannot reach zero temperature. The third law of black hole mechanics says that you cannot reach zero surface gravity. So you have a whole set of rules that are spookily analogous in the thermodynamics regime and the black hole mechanics regime. The question is this an accident? Does this mean something? Is it deep and profound, or is it just a nice little analogy between two very, very different ways of thinking about the universe? There was actually a graduate student named Jacob Bekenstein who was working with John Wheeler, the Princeton physicist who coined the term black hole, and Bekenstein actually made the radical suggestion that these laws of thermodynamics and these laws of black hole mechanics aren't separate, that there is one form of generalized thermodynamics that includes black holes in it, and there what we call the area of the event horizon isn't just like the entropy or analogous to entropy, it is the entropy. Bekenstein says that the entropy of a black hole is proportional to the area of its event horizon. This suggestion did not go easy among the people who think about black holes at the time. Remember, Boltzmann said that the entropy is counting the number of microstates that are macroscopically indistinguishable. If you have a box of gas, the number of ways we can rearrange the atoms of that gas so that it looks the same macroscopically. If Bekenstein was right, black holes must have many, many indistinguishable microstates because they have a large amount of entropy. In the classical general relativistic description, those microstates are nowhere to be found, just like they're nowhere to be found in thermodynamics. A black hole is specified by its mass, charge, and spin, and that's it. Every mass, charge, and spin equal black hole should be the same as every other one with the same values. So how can it be that secretly these black holes have a huge number of states to accommodate all the entropy they have? What's even worse is that we know from thermodynamics that if you have a system with a temperature, it will radiate, it will give off light. This is black body radiation. You are a thermodynamic system yourself, you have a body temperature, you give off infrared light. You can't help it. any object with a temperature gives off radiation. That is a consequence of how we think about thermodynamics. You heat up an oven, and you see it begin to glow. So if you really took seriously the idea that black holes are ordinary thermodynamic systems, and you thought that the surface gravity of the black hole was like the temperature in thermodynamics, then black holes should radiate. That seems to be the implication of Bekenstein's claim that black holes really are part of thermodynamics, not just an amusing analogy. So this bugged a lot of people. People thought it is clearly not true that black holes are just part of thermodynamics because they would radiate, and black holes are black. They don't radiate. In particular, Stephen Hawking got very annoyed. Hawking is a very opinionated guy. He was a little irked that this young, ambitious graduate student in Princeton was saying that black holes are real thermodynamic systems. So, like any good scientist, Hawking didn't just insult him or ignore him. Hawking set about proving Bekenstein wrong. He thought about what it would mean for a black hole to give off radiation, and he set about showing that a black hole can't give off radiation. What this means is that you have to apply quantum mechanics to black holes. Now, we've already said why this is difficult, because we don't have a theory of quantum gravity. But there is a little nice in-between regime where you can hope to make progress. You treat the black hole as classical. The black hole is just sitting there. You're not quantizing the black hole itself. It's a classical object. But you look at the behavior of other fields in the vicinity of the black hole. So you have photons and gravitons and electrons that are near the black hole, and those can still obey the rules of quantum mechanics. Basically, what you're studying is the field of quantum field theory in curved spacetime, and that is actually perfectly well defined, even if true quantum gravity is not. So everyone knows how this story ends. Hawking sat down very carefully to think about quantum field theory in the vicinity of a black hole. It wasn't, by the way, his specialty. Hawking was the world's expert in classical general relativity. He proved the area theorem. He proved different singularity theorems along with Penrose and so forth. But he's also a brilliant guy, so he studied quantum field theory. He would sit silently. Other people would have to prop up the textbook for him, and he would read about quantum field theory. And then he studied that quantum field theory in the vicinity of a black hole. And what he found was that quantum field theory says there are virtual particles. Just like in ordinary quantum mechanics, if you have a single particle, you can't pin it down to where exactly it is located. In quantum field theory, you can't pin down the number of particles in a certain region of space. Virtual particles keep popping in and out of existence. So when Hawking took this idea and applied it to black holes, of course, he's not just waving his hands and talking about virtual particles. He has equations. He's solving the equations of quantum field theory in the vicinity of a black hole, and what he found was that virtual pairs of particles could be created. One of them could fall into the black hole, and another one could escape. From the point of view of someone standing very far outside, the one that falls into the black hole is irrelevant. You don't see it. The one that escapes, you see. What it looks like to you is that the black hole is giving off radiation. The black hole is actually losing mass to its environment because those virtual particles carry away mass. And you might say, well, wait a minute, doesn't the virtual particle that falls into the black hole increase its mass? It turns out, miracle of general relativity, the particle that falls into the black hole has a negative mass. So the black hole gradually shrinks. Black holes ain't completely black, as Hawking himself put it. They radiate, and eventually they will evaporate. They lose energy to the radiation around them, and so even black holes aren't forever. So like I said, Hawking had equations to back this up. We don't need to know all the details of the equations, but it's useful to get the results in terms of how the properties of a black hole are affected by how big it is, how much the mass of the black hole is. In particular, Hawking got a formula for the temperature of a black hole. T equals x divided by m. X is just a constant, so all we're saying is that the temperature is inversely proportional to the mass of the black hole. That constant of proportionality, if you must know, is h bar, Planck's constant, which tells us how important quantum mechanics is, since this is fundamentally a quantum effect. h bar times c cubed, c is the speed of light, divided by 8 pi g k. G is Newton's constant of gravity. Gravity is clearly important. And K, we know, is Boltzmann's constant. You're connecting energy and temperature, so Boltzmann's constant makes an appearance. The important thing is that Hawking showed that the temperature of a black hole is not 0, but it's smaller for large black holes. The temperature goes as 1 over the mass. So a tiny black hole is giving off a furious amount of radiation. A large black hole, a macroscopic one, like we would make in the center of the galaxy or after a star died, is actually very, very cold. A black hole with 1 solar mass has a temperature about 1/1000th of the background radiation that suffuses the universe. So for real-sized black holes, you're never going to observe the Hawking radiation, as it is now called. This is too bad for Hawking. It makes it very hard for him to win the Nobel Prize. It's very hard to test his theory. But most people believe that he's right. Black holes do give off radiation, even if ordinary black holes are just too cold for us to observe it. If they do give off radiation, then they lose mass, and they get smaller. Their mass goes down, and when they get smaller, a black hole gets hotter. So it's a runaway cycle. The black hole gives off energy, it shrinks, and then it gives off more energy faster, and in a finite period of time, the black hole completely evaporates and disappears. This lifetime is given by T equals ym cubed. The lifetime of the black hole is some constant times its mass cubed. Obviously, the black hole lives longer. If it's bigger, it goes as the cube of its total mass. That constant, again, if you need to know it, it's 5,120 pi g squared over h bar c to the 4th. You don't need to know the constant. All you need to know is that the bigger black holes last forever, last longer, even though they're colder. This was a big surprise, of course, when Hawking showed that black holes give off radiation. But it only became more surprising with time. Remember, one of our most precious principles is Laplacian determinism. Information is conserved. We think that if you know the state of the world at one point in time, and if you were Laplace's demon, in principle you could predict the future with perfect fidelity. So for example, if I have a book and I throw it into a fire and it burns, ordinarily you would say, well, now I can't read the book anymore. That information is gone. But if you were Laplace's demon, you would keep track of every little particle of soot, every little photon of light that came out of the fire, and in principle, you would know exactly what the words in the book were before you burned them. It's obviously a thought experiment, but we think that's how physics works at a deep level. So now the question becomes, what about a black hole? We used to think, before we knew that black holes radiated, you would throw a book into a black hole and it's just lost. It's not that the information has disappeared, it's just that you can't get it anymore. But now Hawking says that the black holes radiate, that they give off their mass to the surrounding environment. And therefore, if we wait long enough, all the information that was in the book should come out in the Hawking radiation. Still to this day, we don't know how that happens. In fact, there are debates. Some people think it doesn't happen. You can argue about how difficult it would be to make it happen. Hawking himself was a skeptic. Hawking himself strongly believed that the information is truly lost, that Laplace is defeated by evaporating black holes. But more recent developments in our half-hearted attempts to understand quantum gravity have convinced Hawking that he was wrong. So he had made a bet with John Preskill and Kip Thorne, two physicists at Caltech, and Hawking bet that information was really destroyed. Preskill and Thorne bet that it was preserved. Hawking has conceded his bet. He has given up. And the funny thing is that neither John Preskill nor Kip Thorne agreed that he should have conceded the bet. They still think that information does get out, but they don't think that the issue is completely settled. Most importantly for us, if black holes radiate, if the analogy between thermodynamics and black hole mechanics is good, that means that black holes have entropy. This is our single most important handle on how entropy works when gravity is relevant. And you can calculate what the entropy is. Just like Bekenstein predicted, the entropy of the black hole is proportional to the area of its event horizon. The proportionality constant is c cubed k over 4h bar g, but the point is a bigger black hole has a bigger entropy. The area goes like the size squared, an area goes like a radius squared. and the size goes like the mass. So the entropy of a black hole goes up as its mass squared. It gets to be a very, very big number. But even before we plug in the numbers, we're puzzled by the fact that the entropy goes like the area. Remember, way back in Boltzmann's time, one of the crucial features of entropy is that if you take one box that has a certain entropy and another box with a certain entropy, you add them together, their entropies add. It's as if entropy is proportional to the volume that you're dealing with. But in a black hole, according to Hawking, the entropy goes like the area, not the volume. This is a big puzzle. This opens up a whole can of worms that we don't have time to talk about in this course, but it inspired something that we call the holographic principle. The idea that when quantum gravity is important, physics is no longer strictly local, in the sense that in ordinary physics, in special relativity and quantum field theory, to describe what happens in the world, you describe what happens here, and then what happens there, and then what happens somewhere else. Different places in the universe have different things going on, and if you describe them everywhere, you would describe the whole world. And you can describe them everywhere separately. To know what happens here, I don't need to know what happens somewhere else. The holographic principle says there are secret correlations, secret connections between what happens in the world at different places, exactly in the right way that the entropy of a black hole goes like the area of its horizon. That is to say, the states, those secret unknown quantum states that all macroscopically look alike, to give us Boltzmann's formula for the entropy of a black hole, those states don't live inside the black hole. In some sense, they actually live on the horizon. This is a dramatic idea, the holographic principle. Basically, it's saying that three-dimensional space can be described by a two-dimensional theory. But since it was proposed, we've gotten more examples of how it works in different contexts outside black holes. So the holographic principle is an absolute guiding principle in future developments of quantum gravity. It doesn't really help us understand the arrow of time. So let's plug in some numbers. Hawking gave us a formula for the black hole entropy, and the short story is, it is huge. If you take a 1 million solar mass black hole, we think we have a 4 million solar mass black hole at the center of our galaxy. Let's just take a 1 million solar mass black hole. It has an entropy, according to Hawking, of 10 to the 90th. For comparison purposes, let's take all of the non-black hole particles in the observable universe. Every galaxy, every atom, every star, every bit of dark matter, every photon, every neutrino, and so forth. Add them all up, ignore gravity, and calculate the entropy. The answer we get is 10 to the 88th. So the entropy of all the non-black hole stuff in the observable universe is 10 to the 88th. The entropy of a single million solar mass black hole is 10 to the 90. And we think there's something like 10 to the 12 or 10 to the 13 million solar mass black holes in our observable universe. What this is telling us is that the entropy in our universe today is overwhelmingly in the form of black holes. Most of the entropy is black hole entropy. It's not photons, stars, burning pieces of paper, or anything like that. This is a crucial clue to us when we talk about the evolution of entropy through time. When you think about it, in the early universe, there were no black holes. As far as we know, the early universe was smooth. So there were not only no black holes, there were no stars or planets. There was just plasma and gas spread uniformly throughout the universe. Ordinarily, we think of that as a high entropy state. When everything is smooth, the entropy is high. But when gravity is important, things change. In the early universe, gravity was very important. There was a huge amount of stuff. It was all pulling on all the other stuff. It could easily have been in the form of black holes. Had it been in the form of black holes, the entropy would have been much, much, much higher. So this is a reminder that the entropy of the early universe was actually very low. It's difficult to keep so much stuff in a perfectly smooth configuration. You also see this in the real evolution of the universe. The universe expands and cools. Gravity pulls things together and makes the universe lumpier. That perfectly smooth configuration was not stable. The entropy goes up as structure forms in the universe. So this is our task now. Gravity wants to make things not smooth. Gravity is very important in cosmology, and yet when we look back at the early universe, we see a very smooth configuration. We'll talk about this in more detail, but we have data. We look with our telescopes at the early universe, and we see that it is very smooth. That's a reflection of the fact that it had a very low entropy. Black holes give us the one clue we have about how to relate gravity and entropy. We'll have to see if we can use that clue to explain why the early universe was so smooth. In a previous lecture, when we were talking about the perception of time, I mentioned that the first question people have when you start talking about the mysteries of time is, why am I always late? The second question people always have is, can I travel through time? Is time travel possible? So this is the lecture in which we finally answer that question. You wouldn't actually be addressing the mysteries of time unless you at least talked about time travel a little bit. And like many of our issues, there will be a good news, bad news situation. The good news is that general relativity, Einstein's theory of gravity that says that space and time are flexible, allows us to talk about the possibility of time travel in a scientific way. It's not just fantasizing, we can actually think about what time travel would really be like. The bad news, as you might guess, is that it is probably not possible. It's interesting that we can't say it's definitely not possible. We actually, as scientists, don't know the final answer. Time travel is on the table as something it's respectable to think about. But the evidence is pointing against it, so we probably don't need to worry about the paradoxes that time travel brings up. The first obvious point is that, of course, we travel through time every day, but we travel to the future. 24 hours ago, I started traveling through time, and a day later, here I am. You can't help traveling through time in that very simple way. Again, as we talked about way back when, it's debatable whether the word travel is the right way to think about this. I am now, I was yesterday, I will be tomorrow. That is all true. But if we want to think about a little me that is taking a journey through space and time, I am traveling to the future. That is what people do. A little bit more sophisticated says that special relativity allows us to talk about changing the rate at which we travel to the future. Because special relativity tells us that the amount of time that passes depends on our trajectory through the world, we can actually get to the future faster. We can hop in a spaceship, we can zoom around in circles if you want, near the speed of light, because this is a thought experiment, this is not legitimately possible right now. But if you were to do that, to you, let's say a week passes, back here on Earth, an arbitrarily long amount of time can pass, a year, a century, a millennium. If you travel close enough to the speed of light, your personal clock can read much less than the clocks of the people who stayed back here on Earth. On the other hand, this is not crucially fascinating. If you just went into suspended animation, the same thing would happen. It is probably easier to put a human being in suspended animation than it is to build a spaceship that can go in circles close to the speed of light for a long time. But still, going into the future is something we do, and something we can do at different rates of time. We cannot go into the future more slowly. Remember, if you zoom off and zoom back, you always experience less time than if you just stayed still. So going into the future is something we are going to be forced to do. The real question is, can we travel to the past? Going to the future sounds like fun, but only if we can then come back and tell our friends what we saw. When it comes to traveling to the past, the answer whether you can do that depends on your theoretical background. We haven't built a time machine yet, so it's still a theoretical question. If Newton had been right, if Newtonian absolute space and time were the way that we lived our lives, the answer would be simple. It's no. The laws, according to Newton, are that you move forward in time. There are separate moments in the history of the universe which are moments of individual times, and you march forward through them. You can't help but do that. In special relativity, the answer is also no. Special relativity replaces the division of space and time that Newton gave space-time into light cones, the idea that from any one event, there point out all of these hypothetical trajectories that light would travel on, and that tells you how fast you can move through space-time. So you are forced to move into the interior of your light cone. That's the same as saying that you must move slower than light, and the light cones point into the future. They don't turn around and go into the past. So in special relativity, you cannot ever visit the past. In general relativity, the answer becomes maybe, or probably not, to be more honest. But it at least lets you wonder whether we could tilt the light cones enough to travel into our personal futures and nevertheless end up in the past. That's what a time machine would be like in general relativity. It would be a twisting of light cones, a focusing back on themselves, so that as far as your personal wristwatch is concerned, you are moving forward in time, but as far as the universe is concerned, you have gone into the past. That is a very different idea of what time travel would be than we get from cheap science fiction stories. And even the cheap science fiction stories can be very intellectually challenging, but they rarely take time travel seriously. What we're used to seeing in science fiction stories and movies is some sort of machine that we get into. This is our time machine. It could look like H.G. Wells, or in Doctor Who, it looks like a telephone box, or it could look like a DeLorean in Back to the Future. The point is that you climb into the time machine, you push some buttons, lights flash, and your time machine disappears. It dematerializes, and then it rematerializes at some other time. It pops back into existence in the past or the future. That is completely crazy. That is not what time travel would be like. It's still more respectable than the even crazier science fiction stories just have your consciousness travel. So you personally inhabit the body of your former self or your future self. That's right out of bounds. But even the dematerializing and rematerializing is not how time travel would work. To understand why this is true, let's think of a simple analogy. Think of a very primitive tribe that lives on an island. So they have no technology whatsoever. They hunt and gather, but they cannot even build a boat. They see, however, in the distance, there is another island across the ocean. They can still see it. They would like to visit, but they don't even have the materials or the know-how to build a boat to get there. So they think about getting to this other island. What would it be like to travel through space to get to this other island? And in their thought experiments, they imagine it would be like teleportation. They would somehow disappear from where they are now, and they would reappear on the other island. Now, you and I know that traveling from one island to another is possible. It does not involve teleportation. The reality is much more mundane. The reality involves you get in a boat and you actually traverse all of the points in between the island where you start and the island where you end up. The point is that if time travel were possible, it would be like that. It would not involve some weird kind of dematerialization, which is a whole nother next to impossible technological challenge. Real-time travel doesn't skip over the intervening part of space-time. Real-time travel is a journey through space-time. A true time machine would not be a telephone box with flashing lights and funny noises. It would be a spaceship. It would be some vehicle that moves you through space and time, but in a space-time that allowed you to go visit your past. So in the most realistic version of time travel we can imagine, it's not about building the machine, it's about building the space-time. That's our goal as potential time travelers, to warp space-time so much that you can personally be moving forward in time and nevertheless visit yourself in the past. And you might wonder, how is this possible? Remember, my advice in thinking about space-time was to think locally, to not try to compare what's going on here to what's going on far away at the same time. Relativity says that's not the right way to think. Think about what is happening to you. So what's happening to you is that you are growing older, your clock is ticking, you are moving locally forward in time. And the translation of that into jargon is you are staying inside your light cone. At any one event, you have a place you can go which is slower than the speed of light. But general relativity says that light cones can tilt, they can be twisted, that energy and momentum and mass can bend space-time itself. So we can imagine that light cones actually twist around on themselves so that you can locally move forward in the light cone. You're always moving slower than the speed of light, and nevertheless you can come visit your past self because the light cones themselves have closed in on each other. The jargon term for this is a closed time-like curve. A time-like curve is just a path through space-time that is moving slower than the speed of light. So you and I move on time-like curves. We ordinarily move on open time-like curves, just going to the future. A time machine is a closed time-like curve. We locally travel slower than light, but our path through the universe eventually visits itself in the past. The only reason I'm even introducing this jargon is because, as a physicist, I use this jargon all the time. I cannot help but use those words, so it'll be more helpful for the rest of the lecture to think about closed time-like curves. Can we build them? Can we make a space-time that has closed time-like curves in it? The short answer is probably not, as I alluded to before. But we're not sure. There's a process we go through in our theories to ask the question, are there solutions to general relativity? Are there space-times that fit into Einstein's equation that tells us how matter and energy bend space and time that have closed time-like curves, that have the possibility of time travel inherent in them? The simple answer is yes, there absolutely are solutions to Einstein's equation which have time machines in them, which would let you go backward in time. So then the next level question is that our universe? If we started in a universe that didn't have closed time-like curves, could we create them? Could we essentially build a time machine? Could we warp space and time so much that we were able to visit our own past? This is the open question. We don't know whether or not that's possible or not. We try, and when we try, we seem to run into obstacles. There always seem to be problems when we try to create a closed time-like curve, to build a time machine. And interestingly, there are two different types of time machines we can imagine building and two different types of obstacles that get in our way. One kind of time machine is what you might call built into the universe. Essentially, this kind of closed time-like curve takes advantage of the whole universe all at once. You can write down on your piece of paper a solution to Einstein's equation, a particular kind of space-time with a certain kind of curvature of space-time that has the possibility of time travel built in from the start. It was not created, it was just always there. The most famous example comes from Kurt Gödel, a mathematician and logician, who is from Germany, but he lived for a long time in Princeton at the Institute for Advanced Study, where he was a colleague of Einstein's. Gödel is most famous for his incompleteness theorem that says that no sufficiently powerful logical system has statements that are only provable and true. There are always some statements that are either unprovable and true or provable but not true. But in his spare time, Gödel dabbled in general relativity. And he was very curious about this question of Laplacian determinism, just like we are. Can you start with one moment in time, evolve it forward, and then evolve it backward? So we said that quantum mechanics did not get in the way of doing that. We said that special relativity did not get in the way of doing that. But what about general relativity? So Gödel came up with a solution that is very astonishing. He was one of those geniuses just like Einstein. It's hard to know how he thought of this, but he came up with a cosmological solution, but one in which the universe is not expanding. Instead of getting bigger, the universe is rotating. The stuff that sits inside Gödel's hypothetical universe is vacuum energy, the cosmological constant, energy that is inherent in space itself, and matter particles that are swirling, that are like vortices rotating around each other. And what they cause the curvature of space-time to be is light cones that are tilting gradually as you travel through the universe. It turns out that in Gödel's solution to general relativity, every event sits on a closed time-like curve. Everywhere you start, you can travel through some trajectory in space-time and eventually visit your past. Gödel was fascinated by this solution, as was Einstein. He shared it with his pal Einstein. They were both a little bit worried about it. Many, many years later, when the physicists Kip Thorne, John Wheeler, and Charles Misner were writing a giant textbook on general relativity, they went to talk to Gödel, and what Gödel wanted to know was there any evidence that galaxies have some uniform rotation in the universe. He was worried that our real universe might have time machines built into it. Another idea along similar lines is a rotating cylinder. So not a finite cylinder, an infinitely long cylinder, and you start it rotating, except of course, you can't start it rotating. It would take an infinite amount of energy to rotate an infinite cylinder. But if you just happen to have an infinite cylinder lying around, which is rotating, and it has enough energy and a fast enough rotation, then long ago it was showed that as you get very, very close to the cylinder, there are closed time-like curves. You can actually spiral around into the past as far as you want. A similar scheme come up with more recently is from Richard Gott, an astrophysicist at Princeton, who talked about cosmic strings. These are much more plausible, but still similar sounding, infinitely long, straight tubes of energy. We think that non-infinite cosmic strings could actually be created in the early universe, but infinitely long ones are easier to solve the equations for. What Gott showed was that two cosmic strings can pass by each other, and if they're passing by each other fast enough, you can do a loop in the opposite sense and go backwards in time. So it's not hard to write down solutions to Einstein's equation in general relativity that look like time machines. But all of these examples, Gödel's universe, the infinite rotating cylinder, Richard Gott's cosmic strings, have the property they're infinitely big. If you ask, can you make any of these? Can you start with a universe that doesn't have time travel built in and create a situation that resembles any of these? For example, could you have a finite cylinder that you start spinning faster and faster? Would something go wrong to stop that? The answer seems to be yes. The naive solutions require an infinite amount of energy. If you try to make finite ones with a finite cylinder or finite cosmic strings or a finite amount of dust rotating, you don't seem to get the closed time-like curves. It seems that these solutions are curiosities, but they're not realistic ways to go about engineering a time machine. The other option people look at are trying to make a time machine in a finite region of space. The most famous way to do this is to use wormholes. I'm not sure how famous it is. In the circles I move, this is a very famous way to try to make a time machine. A wormhole, remember, it sounds like a black hole, but it's a very different thing. A black hole, you enter and you will eventually hit the singularity and be crushed. A wormhole is a tube through space-time. It's as if you enter some sphere locally and you're spit out somewhere else arbitrarily far away. The nice thing about wormholes is they can connect different regions of space-time, and you can use them to travel in much shorter time periods than if you just went the ordinary route. So it's like a super fast space-time subway. You go in and then you pop out very, very far away, but it doesn't take you any time to do it, or at least it takes very little time to do it. The distance from one end of the wormhole to the other through the wormhole can be much, much less than the distance from one end to the other outside the wormhole. So this is a very straightforward way to make a time machine because, remember, the different ends of the wormhole don't just connect different points in space, they connect different events in space-time. If it is possible to build a wormhole, a curved tube through space that connects two different regions of space, it is also possible to build a wormhole that connects two different moments in time. So you can just climb in the wormhole one side, you pop out the other side, but it's many years in the past or in the future. That is, again, something where it's easy to write down the equations to qualify this as a solution to Einstein's theory of relativity. The problem with this is that it involves physics that we don't think works in our real world. In particular, wormholes don't want to exist in the first place. They instantly collapse and you can't get through them. You can prove that with ordinary conventional kinds of matter and energy, there cannot be a wormhole that takes longer to collapse than to travel through. In other words, there's the wormhole, you try to get through it, but it collapses into a black hole before you can get to the other side. There is a loophole there, you can get around that, but you need non-conventional matter and energy. And by that I mean not just forms of matter and energy we haven't yet found, but you need negative energy. You need something that would supply you with a repulsive gravitational force. Everything we know about in the universe has the gravitational effect of pulling things toward it, positive energy. You are pulled toward the Earth. You are pulled toward the sun. To keep that wormhole from collapsing, you need negative energy to push it apart. We don't know how to do that, so the simple answer is maybe you just can't build a wormhole. There's a more subtle answer, which says that even if you tried to build a wormhole, even if you had negative energy, you would still fail. There's actually a theorem due to Frank Tipler and an update of it from Stephen Hawking that says that if you try to make a time machine in a local region of space, so if you start in a universe that has no time machines in it, no closed time-like curves, and you push around matter and energy in just the right way to create any form of closed time-like curve at all, whether it's with a wormhole or without, you will inevitably create some sort of singularity. The density of curvature and energy in the universe would go to infinity somewhere. Now, it's not quite enough to say, therefore, you can't do it. We have a belief that if you make a singularity, you make a black hole. It is inside an event horizon and you can't get there. But that's not a proof. We can't quite make it into a theorem. And we don't understand gravity perfectly well. Einstein's theory of general relativity is the best idea we have. But as we'll discuss, it doesn't play well with quantum mechanics. Who knows whether or not in quantum gravity you might actually be able to build the time machine. That is why it is difficult for us to right now say for sure whether or not time travel is truly possible. But let's put aside the technical, the engineering difficulties with time machines. We don't think we know how to build one from scratch, but let's imagine that we did. The real worry is not that we don't know how to build it, it's that if you built it, trouble would follow. Paradoxes in particular. The famous one is the grandfather paradox. What stops me from traveling backward in time, killing my grandparents before they ever met, so that my parents are not born and therefore I am not born? In that case, who did the killing? If you actually had a wormhole that you could go back to that would send you 100 years in the past, how would that really work? Well, there's a couple things to note about how it might work. One is that you don't get to pick when you go back to. If you have a wormhole, you have an entrance, it's like a portal, you go in one end, you come out somewhere else and somewhen else at some particular point in time. It's not like H.G. Wells where you dial the dials on your time machine and decide where you want to go. If your wormhole sends you back 100 years in time and you go through it in 2012, you will come out in 1912. If you go through that same wormhole in 2013, you will come out in 1913. There's nothing you can do to go in 2012 and come out in 1950 or in 2035. The wormhole tells you where you're going to go. Another thing is, of course, if you can go, then someone else can come the other way. If you can go backwards 100 years, someone else can go forwards 100 years. So if people can go into the past, they can also come to the future. That's helpful in some sense. If you go backward in time through this wormhole, you will eventually get to come home. So the way to think about a possible wormhole, once we figured out how to build it, is as a portal, a subway, as we said, that connects to moments in time rather than to places in space. If that existed, could you use it to change the past? Could you use it to kill Hitler or stop JFK from being assassinated, or for some reason you want to kill your grandparents and not let yourself exist? The honest answer is, of course, that we don't know, because we don't have any experimental data about what time travel would be like. We don't even think that it is possible. But we do still have logic and physics on our side. We can ask ourselves the question, could there be a version of reality where you could travel into the past and change it to somehow make it better? If you're not quite so ambitious as to kill Hitler or save JFK, maybe you want to stop that embarrassing incident that happened to you at the senior prom. There's one thing that we know, that even with time travel, there cannot be paradoxes. There cannot be A and not A. This is the thing that gets you into trouble when you're thinking about how time travel would work. How can you kill your grandparents and then be born to go back in time and kill your grandparents? We know for sure that logic still works, even if there is time travel. You can't change the present moment because you're in the present moment. You know what the present moment has. It has you, for example. So nothing you can do can truly prevent you from coming into existence. So if time travel were possible, the best way to think about it, again, we don't have data, we don't know for sure, the most likely scenario is you go into the past, you attempt to kill your grandparents, And even if you make it into the past, something prevents you. This is the scenario that all the good time travel movies have. In 12 Monkeys, for example, the time travel is perfectly consistent. As they said in the TV show Lost, whatever happened, happened. If something occurred at some particular event, some particular location in space, at some particular date and time, then that thing really happened. JFK really was assassinated. You really were born. So you go back, you try to change the past, you will fail. What stops you? We don't know. You trip on a banana, you get sick, someone gets in your way. We don't know what will stop you, but we know you will be stopped because physics and logic are still consistent even in the presence of time travel. Now, this tells us what is really bugging us about time travel, and the answer is the arrow of time. The reason why we're talking about time travel in this lecture is not because time travel helps illuminate the question of the arrow of time. It's because the arrow of time helps illuminate the question of time travel. The arrow of time is absolutely built in to how we think about past, present, future. We discussed how we have this strong feeling that we can make choices that affect the future, that we have free will. Neuroscientists and philosophers can debate about the reality of free will, but one way or the other, we have a feeling that we can make choices. We are not predestined. We can choose to have one kind of food for dinner tonight or some other kind of food. We don't think that we can make choices that affect the past. The past is something that is tied down in our epistemic knowledge because of the past hypothesis. If you have a memory of something happening and your memory is valid, then that's what happened and you can't change it. So, what happens if you put into this situation the possibility of time travel? Then your personal future becomes mixed up with the past of the universe. You personally always age into your future light cone. Your clock keeps ticking in the future direction. But you go off in a spaceship, zoom around a closed time light curve, and come to the past. The point is that now something that you thought was fixed, namely the past, gets mixed up with something you thought was alterable, namely your personal future. But the simplest way of making time travel work is to just say that the past really is fixed. Just like our future really is fixed, if we were Laplace's demon, if we knew the state of the universe and all the laws of physics, we would know what happens in the future. Time travel makes that real. If we have a memory that is reliable of what happened at our senior prom, then that really happened. And if you go back and try to change it, there is predestination. You will fail. We don't know how you will fail, but we know you will not change your senior prom because we know that whatever happened, happened. We don't like that. It violates our sense of free will, but that's the price you pay when you try to mess with the arrow of time. Your personal arrow of time is doing something different than the arrow of time of the universe. If this bugs you, if you don't like the idea that your free will is being compromised, the simplest way out is just to say that time travel probably isn't possible. You probably can't get into the past and do anything about it. If you live in a universe that doesn't have closed time-like curves, then the arrow of time is universal. You can slice the universe into moments of time. Einstein says that it's not universal, but you can still do it, and then the arrow of time moves in the same direction for everyone. Now, I have to say, there's a loophole, a very tiny loophole, called quantum mechanics. Remember, quantum mechanics has this problem of interpretation. We don't really know what happens when you make a quantum observation. And one of the possibilities on the table is the many worlds interpretation that says that every time I observe a quantum system, there is one universe, one world in which I get one answer, another universe, another world in which I get another answer. So it is conceivable that you could combine that theory with time travel. If you had a closed time-like curve, you could imagine going back into the past, truly changing the past, and by doing that, bringing into existence a new world, a new branch of the wave function of quantum mechanics. So in other words, you could kill your grandparents and stop yourself from being born. But the interpretation of that would be that you had traveled from one branch of the wave function in which your grandparents did exist and you were born, into another branch of the wave function in which your grandparents were killed and you were never born. But the point is that the other branch doesn't go away. If you bring into existence a new reality in which the only you in that reality is the time traveler from the future, there's no you that is ever born, then that reality exists, and the old one in which your grandparents were fine and you were born also exists. So have you really improved anything by changing the sum total of all branches of the wave function? This is an ethics and morality question, not a physics question. I cannot provide you with the answer. But this is the kind of conundrum that you get into when you try to make time travel respectable. So, for our purposes, the important feature of time travel is not whether it is possible, but what its conceptual implications would be. And the biggest one would be that, as we mentioned, it destroys the universality of the arrow of time. When you have the possibility of time travel, you do not have Laplace's demon anymore. You cannot slice the universe, not only absolutely, but even arbitrarily. You cannot slice the universe into moments of time. The moments of time intersect with each other in complicated ways. So you cannot put down the data of the universe at any one moment and imagine running it forward and backward in a reversible way. So the question of the arrow of time would be a much harder question to answer if time travel were possible. Since it's probably not, we're going to go back to thinking about the real world and explaining the arrow of time there. In the last lecture, we talked about special relativity, the theory that replaces Newtonian absolute space and absolute time with a single four-dimensional space-time. But still, that space-time is there. It's rigid. It's not changing. Even though it's not absolute space and absolute time, in some sense, it's a fixed space-time. In this lecture, we're going to talk about general relativity. This is Einstein's theory of gravity, where space-time can actually change. It can move, it can bend and twist. And that's what gives rise to the force that we call gravity. It's interesting to think about the different ways in which special relativity and general relativity came about. Special relativity was completed in 1905, and it's certainly Einstein who gets the credit for putting the capstone on special relativity, for putting it in its place to understand how it really worked. But it was not a single person's effort. It was actually the culmination of a group effort that took many, many years. People like Poincaré, Fitzgerald, Lorentz, Minkowski, many different physicists put their ideas together to invent what we now call special relativity. On the other hand, general relativity, the theory of gravity, is really Einstein's alone. General relativity is the reason that Einstein is Einstein. That was his tremendous achievement that was more or less singular. Historians debate whether or not we would even have general relativity if Einstein hadn't come along. We probably would, but it might have taken a lot longer to get there. Unlike special relativity, general relativity is actually a specific theory. It's a little bit tricky to get the names right, because special relativity allows for many, many different theoretical ways of thinking. General relativity is a particular implementation of how gravity works. Special relativity is basically not a theory of physics itself. It's a backdrop. It's a meta-theory. Special relativity is a way of constructing, in particular, physical theories. So, for example, quantum field theory, which is the way that we think nature works in a fundamental level, is based on special relativity. Quantum field theory is what you get when you take quantum mechanics and try to marry it to special relativity. So special relativity is the stage on which other theories play, whether it's electromagnetism or the strong and weak nuclear force or whatever new theories you would like to invent. General relativity, on the other hand, comes from the fact that there is a force of nature that we all know about called gravity. And certainly whatever framework you have for talking about your other theories, gravity better fit into it. So Einstein knew this. He was actually inspired by electromagnetism when he invented special relativity, because the symmetries of electromagnetism are the symmetries that make special relativity go. After he completed that, he was fascinated by gravity. He knew that gravity existed. He knew that the thing to do in special relativity is to take a theory and make it special relativistic, to take a theory that already exists and make it compatible with the ground rules of special relativity. So he tried to do that with gravity. He tried to make a theory of gravity that would fit in with special relativity. But it didn't work. What he found was that you could write things down, but none of them fit what we know gravity to do. We have a very successful theory of gravity in Newtonian gravity. To try to recapture that success in the context of special relativity turned out to be very, very difficult. That's what ultimately led Einstein to a dramatic departure from special relativity. The idea of general relativity, the theory of gravity that Einstein completed in 1916, is that gravity is not a force sitting on top of space-time. In electromagnetism, which was the paradigm for how to work in physics at the time, there are fields. There's the electric field, the magnetic field, and they move through space-time. It was Einstein who figured out that gravity should be different, that gravity would be the stage itself, not just an actor on the stage. So Einstein's point of view changed how we think about space-time. Even though special relativity replaced Newtonian absolute space and absolute time, space-time itself was still fixed. General relativity, according to Einstein, says that space-time itself can evolve, it can change. And that's going to be extremely important for our purposes, where we want to understand the past hypothesis. We want to understand gravity and cosmology, what was going on near the Big Bang. If space-time itself can change, that will be crucial to understanding why the Big Bang was the way it was. The crucial insight that made Einstein go that Newtonian gravity was not supposed to be built into special relativity, but we needed something completely different, is something called the principle of equivalence. This is one of Einstein's famous thought experiments. Without going outside, Einstein is able to come up with some great truth of nature. What Einstein realized was that gravity was different than all the other forces of nature because it is universal. If you have electromagnetism, for example, if I have an electron in an electric field, it gets pushed in some direction. If I have a proton in the same magnetic field, the electron has a negative charge, the proton has a positive charge, the proton gets pushed in the other direction. If I have a neutron that doesn't have charge at all, it doesn't get pushed at all by the electromagnetic field. So electromagnetism is not universal. It acts on different particles in different ways. But gravity is universal. Put that electron, that proton, that neutron in a gravitational field, and they will all fall down. And they will all fall down at the same rate. That was shown by Galileo many, many years ago. So the principle of equivalence is Einstein's way of formalizing this idea. The equivalence is between gravity and acceleration. Imagine that you're in a sealed room where you cannot see outside. You feel a gravitational force holding you to the ground, and you do some physics experiments. You will notice that if you drop different objects, they fall at different rates. You can also do non-gravitational physics experiments. You can measure the frequency of some radiation from an atom, or you can measure the charge on the electron. What Einstein says is that if you also imagine doing those same experiments in zero gravitational field, but in a rocket ship that is accelerating, you will get exactly the same answers. Think about an accelerating rocket ship. It pushes you in the direction in which it's accelerating. So you are pulled to the ground, effectively, just like you are when there's a gravitational field beneath you. Einstein says that it's not just a similarity, it's an equivalence. You can do all of those experiments in the rocket ship that is accelerating. You will get exactly the same answers as if you did them in a gravitational field. So gravity is impossible to detect in a local region of space-time. There's no experiment you can do to say whether or not you're in the field of gravity or whether or not you're in a rocket. This is completely different than electromagnetism. Just put an electron and a proton there, you can immediately tell whether there is an electrical field. So what does this mean? It's one thing to do the thought experiment. Anyone can do that. It takes Einstein to figure out what the consequences of this thought experiment really are. What are the implications of this idea? And what Einstein says was that if gravity is universal, if you can't really do an experiment to tell that there is gravity, then maybe gravity isn't a field on top of space-time. Maybe it is a feature of space-time itself. That's one little leap that he made. The next leap was, yes, it is a feature of space-time. In particular, it is the curvature of space-time. Einstein imagined that space-time, just like space, can have a geometry. It doesn't need to be flat. It doesn't need to be Euclidean. It doesn't need to be the case that if you have a triangle and add up the angles in between, all of the angles inside the triangle add up to 180 degrees. That doesn't need to be the case. Einstein says that matter and energy can bend space-time, and that bending is what we call gravity. Think about regular geometry. This is Euclidean geometry. It's the same geometry that we're taught in high school and was taught by the ancient Greeks. There are various principles of Euclidean geometry. For example, if you have parallel lines, you start them out parallel, you follow them for an infinite distance, they will always stay precisely the same distance apart. That is what it means to be parallel. But as mathematicians thought about the nature of geometry over the years, they realized that that was actually not sort of an unavoidable part of geometry. This idea that parallel lines stay the same distance apart is an assumption, and we can make other assumptions. And it's not even sort of that dramatic. We can do it in a very down-to-earth way. Think about our lives here on the surface of the Earth. We live on a sphere. A sphere is not a plane. Here on a sphere, if you start two parallel lines, they will eventually come together. That's a different kind of geometry. It's not violating the rules, it's just a different set of rules. There can also be geometries that are shaped like a saddle, where if you start parallel lines, they will move apart from each other. So there are actually different ways to do geometry. There's Euclid, which is kind of flat geometry. It's the geometry of a tabletop or ordinary three-dimensional space. There is also curved geometry. So Einstein said, maybe space-time doesn't obey the rules of Euclid. And to be honest, I have no idea what sort of inspired him to say that. This is just one of those brilliant moments in the history of science where someone comes up with a really killer idea. Einstein saying maybe the geometry of space-time is curved is one of those killer moments. So Einstein's way of thinking about gravity is usually illustrated by a rubber sheet. Imagine you have a rubber sheet that you put a bowling ball in the middle of. So the bowling ball distorts the shape of the rubber. It pulls it down. Now, I have to say, because people always complain about this is just an analogy. This is not how gravity really works, because of course the bowling ball is pulled because it is sitting in a gravitational field. But the analogy is trying to tell you that the effect of this bending of the rubber sheet is analogous to the effect of gravity. So once you put that bowling ball in the rubber sheet, it bends it in a certain way. And now if you imagine rolling a marble on the sheet, without the bowling ball, the marble would just roll in a straight line because the sheet would be flat. It would be Euclidean geometry. With the bowling ball, now the marble goes around the ball. It is distorted by the distorting twist in the rubber sheet. The fact is that the geometry of space-time can give rise to what we call gravity. In general relativity, just like in special relativity, there are light cones at every point. If you take an event in space-time and you follow the paths of all hypothetical light rays that could leave that event or could come into that event from the past, that still forms a light cone. But because space-time is curved, because it has a non-trivial geometry, those light cones can bend and twist. It's not quite as simple as the examples that are often given of parallel lines moving apart or coming together, because those are examples where the curvature is constant throughout the world. On the surface of the Earth, in the idealization where the Earth is a perfect sphere, there's just one kind of curvature everywhere on the surface of the globe. But in general relativity, the curvature can be big some places, small other places. It can be positive some places, negative other places. It could even be positive in some directions, negative in some directions. So initially parallel lines can do all sorts of crazy things. The point is that these light cones that formed the structure of space-time in special relativity still do that in general relativity, but now they can move around. They can change, they can twist, they can bend. It's literally that distortion of the light cones here in the solar system caused by the gravitational field of the sun that makes the Earth orbit around rather than just moving on a straight line. One way of thinking about general relativity is to think that particles, and that includes like the Earth, anything that is not affected by forces other than gravity, are doing their best to move on straight lines. That's what objects want to do. They want to move on straight lines. But because space-time itself is curved, there are no straight lines in the curved geometry of the world. That's what gives rise to what we call gravity. That's why the moon goes around the Earth goes around the sun. They're trying their best to move on straight lines, but space-time itself is curved. This curvature can obviously get very dramatic. If what we call the gravitational field becomes very, very strong, the light cones can tilt so much, the space-time can be affected so much by gravity that you make what we call black holes. Black holes, I'm sure you've heard of, they're regions of the universe where gravity is so strong that light itself cannot escape. But now that we know what a light cone is, we know a little bit about gravity and general relativity, we can understand that a little bit better. The conventional way of thinking would be, well, just like the gravitational field is stronger on Jupiter or the sun than it is here on Earth because they're more massive, if you have a lot of mass, the force that is pulling on you becomes so strong that light cannot escape. That's kind of true. It's good enough to give you a perfectly acceptable way of thinking about black holes, but you can do better if you think about the light cones. Remember, the light cones are telling you where light can go, and because you can't travel faster than the speed of light, the light cones are telling you where you can go. At any one point in your lifetime, you are an event, there's a light cone moving forward into space-time away from you, and the rules of relativity say that you need to stay inside that light cone. That is your future. So a way of thinking about a black hole is that the gravity is so strong that space-time has become curved in such a way that the light cones tilt over, and the only thing that you can do while moving slower than the speed of light is to move into the black hole. The light cones are tilted toward the center of the black hole. You can't escape from the black hole without actually moving faster than light. And since you can't do that, the black hole is a place you can go in, but you can never come out. Inside the black hole, of course, is a place where the curvature of space-time becomes infinite. This is what we call the singularity. You probably heard about a singularity as well. The gravitational field is so strong that everything shrinks to an infinite density. The curvature of space-time is infinite. Our equations blow up, and we call that a singularity. There's one subtle feature that isn't usually gotten across, which is that the singularity is not a place. We talk about it and we draw pictures of it as if the singularity is at the center of a black hole, but really the singularity is a moment in time. It is in the future. When you enter the black hole, when you're staying inside your light cones, you are forced to hit the singularity because everything inside your light cone becomes focused onto that singularity. You can no more avoid hitting the singularity than you can avoid hitting tomorrow. In fact, remember we talked about the fact that the more you move in fast trajectories through the world, the less time elapses on your clock. So if you're inside a black hole and you try to escape, if you try to fire your rocket engines to move away from the singularity, guess what? You will hit the singularity faster because less time will elapse for you as you age forward in time. You don't travel toward the singularity, you age into it. And at that singularity, at that moment of time, time comes to an end. Past that, we can't say what happens. In general relativity, all we can say is that it is a boundary. It is the edge of space-time itself. Now, general relativity might not be the final word when you're inside a black hole, but right now that's the best we can do. A singularity is a place that time ends. So the singularities are really the parts of general relativity that are the most dramatic. It's general relativity predicting its own downfall. The theory says there's a place you can go where the theory breaks down. But when you fall into the black hole, when you cross the boundary between outside the black hole and inside, general relativity works perfectly well. That boundary is called the event horizon. It's called a horizon because it's the place where once you go in, you can't come out. You can never escape back to the rest of the world. The light cones won't let you. They're all forcing you into the singularity. However, the horizon itself is just space and time. It's nothing there. There's no wall. It's not like the surface of the Earth or the surface of another planet where there's a boundary that says here is outside the planet, there is inside the planet. A black hole is just a region of space. It is not a solid object. If you fall into the black hole, If you pass by the event horizon, you don't even notice. If it's a big enough black hole, you wouldn't even be aware that your future is doomed, that you are going to hit that singularity and you can never get out. There's no signpost at the event horizon saying that it is a one-way trip. Depending on how big the black hole is, the actual events of your voyage can be different. If the black hole has the same mass of the sun, if it's a solar mass black hole, the time it takes you to go from the event horizon to the singularity is about 1/1,000,000th of a second. So you won't get a lot of time to enjoy the ride. Along the way, remember, you're entering a region of very strong gravitational fields. And those gravitational fields pull you in some directions and push you in other directions. As you're falling in, if you fall feet first, your feet are a little bit closer to the black hole than your head is. So your feet feel a stronger gravitational field. The transverse directions, your sideways size, is actually squeezed together. So your feet are pulled apart from your head. You're made thinner and thinner in the other direction. The technical term for this is called spaghettification. That's what happens if you fall into a black hole. It's that you are ripped to pieces by the tidal forces of gravity according to the rules of spaghettification. It's not a pretty sight. No one should fall into a black hole. In particular, don't believe what Star Trek and other science fiction movies tell you, that you go into the black hole and you come out somewhere else in the universe. That is not a black hole, that's a wormhole. We'll be talking about the possibility of a wormhole. In a wormhole, maybe you can travel through it. In a black hole, you will just cease to exist, so it's not a good idea. These black holes are not completely hypothetical. We believe that we have extremely strong evidence for real black holes in the real universe. You can't see the black hole itself, it's more or less black, but the black hole affects the gravitational field around it so strongly that other forms of matter near the black hole react in very noticeable ways. So gas and dust falls into the black hole, it heats up because it keeps banging into other particles, and that hot gas and dust gives off X-rays and gamma rays and other forms of radiation. We can detect that and infer that there is a black hole there. So it turns out that in the real world, there seem to be several different kinds of black holes. Not kinds intrinsically, but coming from different places and therefore having slightly different properties. The most famous kind of black hole comes from the collapse of a massive star. So a star is actually held up by the heat energy inside. At the center of the sun, there's nuclear fusion going on that is emitting radiation. This radiation heats up the gas and plasma around it, and the pressure of that plasma is what keeps the sun in its shape. The Earth is kept in its shape because the atoms and molecules of the Earth take up space, but that's not true in a star. In a star, it's just the atoms are moving around but bumping into each other. Someday, that fuel will be exhausted. You will use up all the nuclear energy you had, and then the star will collapse. It will typically collapse to a white dwarf, where again, the individual electrons and protons and neutrons take up space. But if it's heavy enough, it collapses past that. The electrons and protons join together to make neutrons, and you're left with nothing but neutrons. Now you have a neutron star. We think that if you have an even more massive situation, if you have a very, very heavy neutron star, it will continue to collapse all the way to a black hole. So if you have a star that, let's say, has 20 times the mass of the sun, it will collapse and make a black hole that is about 3 times the mass of the sun. That's because in those processes of collapsing, it ejects a whole bunch of matter into the surrounding space. We think that we have seen these massive star black holes because they often have binary companions. You have the black hole, you have another star next to it, and that other star can leak onto the black hole, give off X-rays, and we can detect it. Even better is the supermassive black hole at the center of our galaxy. Cosmologists believe that most galaxies in the universe have giant black holes at the center, whereas a stellar black hole might be 3 or 5 or 10 times the mass of the sun. A supermassive black hole is 1,000,000 times the mass of the sun or more, all the way up to 1,000,000,000 times the mass of the sun. We think that the early form of these black holes are what power quasars in the distant universe. And we think that our Milky Way galaxy, the center of which is in the constellation of Sagittarius, has a giant black hole in it. This is not just speculation. We can see stars move around an invisible object in the center of the galaxy. You can take movies of them over the courses of several years. You discover that there must be something incredibly massive and incredibly tiny, relatively speaking, to make the stars move in these very tight, fast orbits. You can infer that our black hole in the Milky Way has 4.1 times the mass of the Sun, and it's spinning extremely rapidly. There's other kinds of black holes you can get. There are middleweight black holes that might be thousands or hundreds of thousands times the mass of the Sun. There are primordial black holes that maybe weigh grams from the very, very early universe. And you can even imagine making black holes yourself at the Large Hadron Collider. There are physicists who have speculated that if you smash protons together at these very, very high energies, gravity might be stronger than we think, and you can actually make a little black hole. If you did, the world would not end, the universe or the Earth would not be destroyed. In fact, what would happen is that black hole would evaporate very, very quickly. The kinds of collisions that you make at the Large Hadron Collider are made all the time in outer space, so we're not doing anything the universe hasn't done already. It's a very speculative idea. The odds are small that it's actually true, but it's fascinating to think that we could actually make a black hole in the lab. As a completely separate consequence of general relativity, because space and time are curved, space itself can expand. What you call the size of the universe can change over time. Einstein realized this in the very early days of general relativity when his mind turned to cosmology and he was trying to model the universe as a uniform distribution of matter. Again, thinking like a physicist, Einstein asked, what is the simplest possible universe I could have? It's one where there's the same density of stuff throughout. And he thought this would be a good model for what the astronomers told him the real universe was like. Back in these days, in the early part of the 20th century, we thought that our Milky Way galaxy was the universe. When you look at the Milky Way, it's not changing very much. Over human timescales, it's essentially static. So Einstein tried to describe a static universe. If he had done that in Newtonian gravity, it could have worked. The answer is actually a little ambiguous. It's sort of a mathematical puzzle, what would happen. But in general relativity, the answer was completely unambiguous. If you had a uniform distribution of stuff filling the universe must either be expanding or contracting. It could not be static. So to Einstein, this was a puzzle. He had what his astronomer friends said were data, that the universe was static. He had his theory, which he loved very much, that said the universe should either be expanding or contracting. So he had a chance to write a paper saying, I don't believe the astronomers, I predict the universe is either expanding or contracting, but he didn't. Instead, he blinked and he tried to change his theory to find a static solution. He ended up introducing the idea that there is energy filling empty space itself, what he called the cosmological constant, or what we would call vacuum energy. Turns out that he was right to think that that is a possibility. We think that it's very possible there is a cosmological constant in the real world, but he was wrong to think that it balanced the force of matter and gave you a static solution to cosmology. He was very regretful later in life that he missed the chance to predict that we live in an expanding universe. Back in the 1920s, Edwin Hubble actually discovered that the universe is expanding, which we'll talk about in a later lecture. That was the prediction that Einstein should have made, but he missed his chance. If the universe is expanding, which it is, we can run the movie forward. The universe will get more and more dilute. Galaxies will move away from each other. But we can also play the movie backward. General relativity is a reversible theory. We can ask where we came from. And what we find is that in the past, things were closer together, and therefore the gravitational fields were stronger. And if you keep going back into the past, the gravitational field just gets very, very strong. Winding the movie of the universe backward in time is very, very similar to following the formation of a black hole forward in time. The universe is like the time reverse of a black hole. Inside the black hole, there's a singularity in your future because all the matter collects in one place. In the universe, there is a singularity in our past. That is what we call the Big Bang. This was something that was theoretically predicted. People didn't like it. There was a small number of people who took it seriously and asked what are the consequences of this idea called the Big Bang. It took many decades before we actually collected enough data to say that that idea was on the right track. What this means is that there could be a beginning to the universe. That just like time ends inside a black hole at the singularity in the future, time ends at the Big Bang in a singularity in our past. Now, we don't know for sure that that is right, and we'll talk about this in great detail. General relativity doesn't predict that there's a Big Bang. General relativity predicts its own downfall. It predicts that there's a singularity, but singularities aren't real. They're places where the equations fail to give us an answer. Nevertheless, something is going on at that moment that we call the Big Bang. Either it is something like the Big Bang, or it's something else that we need to discover. For our purposes, the relevant fact is that it completely changes the question of the past hypothesis. Remember that Boltzmann, when he struggled to explain the past hypothesis, thought about an eternal universe with random fluctuations. It turned out not to work. That makes predictions that turn out not to be true. But once general relativity comes on the scene, there's a different option. You can simply say the universe doesn't last forever. Maybe there's a true initial condition at the Big Bang, a moment that we now know to be 13.7 billion years ago. So that opens up a different door that we didn't have available before. Now that there's general relativity, now that space and time are on the table as things that can change, it might be that the Big Bang is a true initial condition with a very low entropy. So there's still the question, why was the entropy very, very low at that moment? But it's a different kind of question. It's not why did the universe go through a phase where the entropy was very, very low. It's why did the universe begin with low entropy? That may or may not be the answer. It's certainly one of the alternatives we will have to take very seriously. By now we're 2/3 of the way through the lectures, and the 3 sections actually fall into a certain kind of pattern, almost as if I had planned it that way from the start. The first third was setting the stage. We talked about what time is, how the arrow of time is the most important mystery, how certain things do not explain the arrow of time. In the second third, we sort of took very seriously the problem of entropy. Entropy is why there's an arrow of time. Boltzmann explained to us what entropy is. And we still have puzzles about why the entropy was so low in the past. But we also made the case that if we were to understand that, we would understand lots of other things. Why we remember the past and not the future. Why we can make choices about the future and not the past. So now in the last third of the lectures, we're going to really try to explain why the early universe had such a low entropy. The bad news is that we're not going to succeed. Cosmologists don't actually know why the early universe had a low entropy, but we will think about what the plausible explanations are. And what that means is we need to understand cosmology, the study of the whole universe. And when we need to understand cosmology, that means we need to understand gravity. Gravity is the force in the universe that is the most important and influential one when it comes to cosmology. And when we need to understand gravity in the modern world, that means we need to understand relativity. Relativity is Albert Einstein's theory of space and time, and especially gravity. So once we dig into that, we can understand not only cosmology and the expansion of the universe and the Big Bang, but also interesting questions like how time began. Can you travel backwards in time? This makes sense because Einstein's theory is a theory of space and time. So even if we weren't interested in the past hypothesis and the low entropy of the early universe, we would still want to talk about relativity anyway. To really understand relativity, the secret is to take a truly four-dimensional viewpoint. We can say that the universe is made of 4 dimensions. There is 3 dimensions of space and 1 dimension of time. What we mean by that is that to locate something, you need to give me those 4 pieces of information. Where are you in 3-dimensional space? And when are you in 1-dimensional time? So if you want to meet somebody at 5 p.m. at a certain location, you need to say where that location is and give the time. Nevertheless, we tend to think in terms that say that time and space are very different. We tend to think of the universe as a 3-dimensional universe with stuff in it. We tend to think that reality is a 3-dimensional thing, and that 3-dimensional thing happens over and over again as a function of time. As time passes, 3-dimensional reality evolves. But the 4-dimensional point of view, which is optional in a Newtonian viewpoint becomes absolutely necessary when relativity comes along. So let's think about what that means. In 3 dimensions, we have points. We say here's a particular point in space. It's different than all these other points. In 4 dimensions, in what we call space-time, instead of points, we have events. So if you say this particular point at 6 p.m. on October 25, that one moment of time, that is an event. So event is not a place, nor is an event a specific time. It's both. It's a specific point at a specific time. It's crucial that we mean, not that there's an important event. An event is not a happening, either a glamorous event or a non-glamorous event. It's not something that occurs. It's just a location in space-time. Just like we have locations in space, if you have a location in space at a specific time, that's what an event is. And then space-time, the 4-dimensional reality of our universe, is just the collection of every event. Just like space is a collection of an infinite number of points indexed by the 3 dimensions of space, space-time is a collection of an infinite number of events. What we want to do is to understand those events and internalize it so well that we can throw away the division of space-time into space and time, to treat it as one truly 4-dimensional thing. This is a very difficult trick to pull off intuitively. We're not used to thinking 4-dimensionally, but we can train ourselves to do better and better. The real difference here is the difference between the Newtonian view of the universe and the Einsteinian view of the universe. They both have a 4-dimensional space-time. In both Newton and Einstein, you need 3 dimensions of space, 1 dimension of time. The difference is that they divide space-time up into space and time in very, very different ways. If you were Isaac Newton or any of Newton's followers, you thought that space and time are separate and they're both absolute. So when we say that space and time are absolute, we mean that they're given, we know what they are. There are no choices to be made. It's not up to us. Different people don't have different kinds of space or different kinds of time. So in a Newtonian point of view, you would say, here's an event, here's a point in space at a moment in time, and for any one event, there's something called the present moment. That is to say, to any one event, there's a whole 3-dimensional slice through reality, and that moment is the same time as this event. It is all of space at one moment in time. It is a notion of simultaneity. What set of events happen at the same time as this particular one event? So the picture in your mind is of a 4-dimensional universe, and time slices the universe into moments of time. In a Newtonian point of view, both time and space are there given to us. Any one moment has a present, everything before it is its past, everything in front of it is its future. Now, whenever we get to these confusing issues of space and time, it is very helpful to ground ourselves by thinking operationally. In other words, by thinking about clocks. One way of thinking about time is that time is what clocks measure. So when we say that in a Newtonian space-time, any one event has this 3-dimensional slice associated with it, the whole universe at one moment of time, what you should be asking yourself is, how would I construct that using clocks? What would I actually do to measure this concept? Rather than taking this God's eye view of the whole universe, what would I build and what would I write down in my notebook? There's a great book by Peter Gallison, who's a historian of science, called Einstein's Clocks and Poincaré's Maps. Einstein, of course, you know of. He is the founder of relativity. Poincaré you've heard of in the context of the recurrence theorem. Poincaré is the French mathematician and physicist who invented chaos theory, showed that if you have a finite number of things that can happen, things would eventually recur. He was one of Europe's leading thinkers at the turn of the century, around the year 1900. And he did a lot of work that was prior to Einstein, basically laying the groundwork for what we currently call relativity. Poincaré was very interested in the symmetries that underlie the theory of relativity. The symmetries that say, no matter where I am, physics is the same. No matter how fast I am moving, physics is the same. And no matter what direction I am pointing in, physics is the same. It was Poincaré who put all those symmetries together. And in Gallison's book, Einstein's Clock and Poincaré's Maps, he makes the point that we think about Einstein and Poincaré as these very abstract thinkers, people who are concerned with the very essence of space and time and reality far removed from our everyday lives. But in fact, Einstein worked in the Swiss patent office, and Poincaré worked as the president of the French Bureau of Longitude. Remember, the problem of longitude, one of the leading issues in the nature of time, tried to make people build better clocks to figure out where we are on the surface of the Earth. Poincaré played a big role in helping people try to figure out what longitude they were on, how to draw maps. And Einstein, in his patent office, he wasn't just looking at any old gizmo. At the time, in the early years of the 1900s, one of the most important kinds of gizmos to patent were clocks. The point is that that was a time when transportation between cities became easier and easier. It used to be that every different city had its own time zone. You would just have the actual time that was associated with where the sun is above you in the sky. But once transportation and communication became easier, it became interesting to sort of relate the times in one city to other locations. Even within one town, it was important to synchronize your clocks. So many of the patents that Einstein actually looked at were for better and better clocks and methods for synchronizing the clocks. Gallison's argument is that despite the reputations of Einstein and Poincaré as very, very abstract, deep thinkers, they were both heavily influenced by their down-to-earth day jobs, by the need to understand maps, pictures of space, and clocks, measurements of time. When you want to think about space-time, you should think about what the maps do and what the clocks do. So to make sense of Newtonian space-time, imagine actually constructing that slice through the universe that we call the present moment. What you might imagine doing is building a large robot army. Each robot has a little clock on it, and they all have spaceships. So even though we're being practical, this is certainly a thought experiment, but that's okay. Imagine you have a lot of robots and you can send them anywhere in the universe. So your trick to constructing what you mean by a single moment at one moment in time throughout the universe is to synchronize the clocks. So you bring your robots together, you set their clocks to read the same amount, and then you send them throughout the universe. Imagine we could put a robot with a clock at every point throughout space. We know that the clocks read the same thing because when they were here next to us, we synchronized them. So now you basically have a label at every point, at every event in space-time. You know where the robot is, so you know where it is in space. And it has a clock, so you know when it is in time. So basically, through this thought experiment, you can try to make real Newton's absolute space and time. You can say, what I mean by the universe at one moment is simply the set of events where all of my robot clocks read the same time. When they all say 6 p.m. November 5th, that is a moment in the history of the universe. The problem is that Einstein figured out that this technique doesn't work. That even as a thought experiment, you can't take robots, synchronize their clocks, and send them all throughout the universe. In relativity, in Einstein's point of view, there is no such thing as one moment of time all throughout the universe that everybody agrees on. To Einstein, space and time are combined into space-time, but space by itself and time by itself are not absolute. They are relative. That's why that word is attached to this theory. What you call space and what you call time will be different for different observers. So why is this true? What happens to our robot army? It's not that we have another army that fights our robot army. It's that the way that we send our robots equipped with clocks throughout the universe affects the answer we get. Different observers with different sets of robots that were sent through the universe using different rocket ships would get different notions of simultaneity. They would divide the universe up into space and time in different ways. One very, very simple way of seeing this is just take one robot. Here, I synchronize it with my clock. I send it off, so now I know that when it says 3 p.m. on my watch, it says 3 p.m. on the robot's watch. But I worry that, that robot has had a hard time. I bring it back. Its spaceship brings it back here. And I notice that when the robot comes back, it is no longer synchronized. The clock doesn't read the same anymore. That's not a fault of my robot, Einstein says. That's a fault of space-time itself. This is the best way, I think, to conceptualize the difference between relativity, Einstein space-time, and Newtonian space-time. If you send out clocks following different paths through the universe and bring them back, they will have measured different amounts of elapsed time. If you're on a spaceship yourself and you're not firing your rockets or anything, you're just floating through space on some constant trajectory, either standing still or moving. Einstein says it doesn't matter whether you're standing still or moving. There's no absolute way you measure that. But you send out little probes. You send out little satellite robots, satellite spaceships. They both have clocks on them. They started synchronized. They go out exploring. They come back. Einstein says they will always be out of sync. It's not optional. It's not that your robots aren't good enough. It's not that there's a technology failure. It's that the amount of time elapsed on a different trajectory through the universe depends on how you move through the universe. And it works in a very consistent way. Namely, anytime that you're moving on a crazy path through the universe, a curved path where you're firing the rockets, going at high velocities, and then coming back, when you come back, you will always have measured less elapsed time. The way, Einstein says, to maximize the amount of time spent in between two events in space-time is to do your best not to move, or to equivalently move at a constant velocity. Acceleration, curved paths through space-time always decrease the amount of time that your clocks measure. Now, this is not just abstract nonsense. This is not just some theoretical speculation. It's a deep, profound idea. We're saying that there is no such thing as one moment spread throughout the universe that everyone can agree on. We're saying that what time it is at one point depends on who does the measuring. That's a deep fact. But it's also experimentally verified. One of the most dramatic and immediate experimental verifications comes from the idea of a muon. A muon is an elementary particle. It's like a heavier cousin of the electron. The electron, of course, plays a crucial role in atoms. Muons don't play a crucial role in anything because they're heavier than electrons. They decay very, very quickly. The lifetime of a muon is about 2 microseconds, 2 millionths of a second. So if you had a muon right here, it would decay into pions, pions decay into muons, which then decay into electrons and other particles. So muons, in some sense, are a clock. They're not a very good clock, but if you have a large collection of muons, over half of them decay every 2 millionths of a second. So by looking at how your collection of muons diminishes over time, you're essentially measuring how much time has passed. From measurements in the laboratory, we know that the lifetime is about 2 millionths of a second. Nevertheless, we find that we can discover muons here on Earth that came from cosmic rays in the sky. In fact, this was the way that muons were first discovered by Carl Anderson at Caltech. He was measuring cosmic rays, and he measured the existence of this particle that looked like an electron but was much heavier. So all that sounds fine until you plug in the numbers. How do you make these muons from cosmic rays? It's not that muons are traveling through interstellar space. If they were, they would decay very quickly. What travels through interstellar space in the form of cosmic rays are protons and sometimes heavier atomic nuclei. But those protons smash into atoms in our upper atmosphere here on Earth. They create pions and other elementary particles, and those quickly decay into muons. So you might want to ask yourself, do the muons have enough time to reach the ground and be detected? Well, their lifetime is 2 microseconds. You know how fast they're moving. It's almost at the speed of light. So you plug in, and you figure out that the muons should decay after traveling about 1 kilometer. The problem is, the upper atmosphere where the muons were created is 15 to 20 kilometers in the air. It is a surprise, if we didn't know relativity, which of course we did, it would be a surprise to realize that muons are able to reach the ground. If their clocks were ticking at the same rate that our clocks are ticking here on Earth, they would have decayed long before they reached our detectors here at sea level. But they don't. Why do the muons reach us before decaying? Because their clocks are not ticking in the same way ours are. They don't have like a literal wristwatch, but the lifetime of a muon is a kind of a clock. It's a predictable thing. Because they're moving so fast with respect to us down here on Earth, essentially they feel less elapsed time. To them, it is less than 2 microseconds to go from the Earth's upper atmosphere to us down here, so they are able to make it before they decay. This sounds a little bit crazy, or at least a little bit hard to swallow, that how much time passes for you depends on how you're moving through the universe. What's going on is that, as we mentioned way back when, there are different notions of time when we talk about what time is at a fundamental level. Sometimes these notions coincide. They're the same, but sometimes they don't. In particular, we can define one idea of time as the time that is measured by an observer, the time that is elapsed by a clock. The nice thing about a clock is it's a small thing. It's not spread all throughout the universe. It's a localized object, a mechanical or electronic machine, and it measures a certain amount of time. There's another notion of time, which is a little bit more abstract, time used as a label to measure what moment of the universe we're talking about. So if we're Newton or even if we're Einstein, we can slice up the universe into moments of time, and then we say, oh, it's 6 p.m. here and everywhere throughout the universe. The reason we thought that everyone would agree when we did that is that to Isaac Newton, these two notions of time were the same. Time was absolute. The time that you measure in the universe, passing everywhere and for everybody, was the same as the time that a clock would measure. But Einstein says they're not. Einstein says that time is personal, that how much time passes depends on how you move through the universe. The time that you feel depends on your trajectory through the world. Again, this sounds a little weird, but in fact, once you really internalize this idea that time is like space, then it begins to make sense. Think of a football game or a football field with a running back trying to avoid being tackled. A football field is nice because there are markers that tell you what yard line you're on. You're on the 10-yard line, the 20-yard line, the 30-yard line. And what you want to do as the running back is you want to gain yardage. You want to go from the 10-yard line to the 20-yard line. So one way of measuring how much distance the running back has traveled is to say what yard line they get to. That's like the Newtonian idea of absolute time. It measures where you are in the universe. Now the universe is this football field. But the actual distance the running back travels involves a lot of going back and forth and of trying to avoid tacklers. So to get from the 10-yard line to the 20-yard line, the actual amount of distance the running back has to go is usually much more than 10 yards. This is very, very natural. Just to get from one place to another, we don't always move in straight lines. We often travel a lot more distance than the actual distance between two different places. In space, this is no surprise to us. This just sounds perfectly obvious. Einstein is saying that the same thing is true in time, that the amount of time that is elapsed for us as measured by our clocks depends on how we connect to different events in the universe via our motions through space-time. So what Einstein is doing is replacing the idea of space at any one moment in time with a much more subtle way of thinking about space-time. The short answer to how Einstein divides up space-time comes in the concept of a light cone. This is a somewhat difficult to visualize idea, but once you get it, it's extremely helpful in thinking about relativity. So we're going to spend just a little time trying to understand what light cones are. A light cone is not something that exists in space. It's not a cone you can draw somewhere or construct with clay. It's something that exists purely in space-time. And the reason why light is special is because relativity says that everyone measures the same speed of light. It's also the fastest speed that there is, but more importantly, it's invariant. It's constant. If I sit here and I measure the speed of a light beam going by, I get a certain answer, 300,000 kilometers per second. If someone else goes by here at 200,000 kilometers per second and measures the same speed of light, you might think that the velocities should add together. But they don't. That person passing by also measures 300,000 kilometers per second. The speed of light is the same to everybody. So with that in mind, think about sitting where you are right now and flicking a light bulb on and off very, very quickly. So you have a bunch of light rays, or photons, depending on how you want to put it. They move away from the light bulb. So there is a sphere in space, which is the distance to which all the photons got. If you really imagine that you flicked on and off very, very quickly, just one little shell of photons is leaving that light bulb. So in space, what we would have at any one moment of time is just a spherical region, which is where the photons have gotten from the light bulb to any point, given the amount of time they had to go. It's the speed of light times that time. But what about in space-time? Even though the light forms a sphere around us in three-dimensional space, when we portray it, we usually portray it two-dimensionally, so every moment has a circle of light. Imagine we took a picture of every three-dimensional moment in space, and we tracked the expansion of all these photons. And then we stack those moments on top of each other, just like we stack the pages of a book or the frames from a film on top of each other, to make a picture of space-time. At the moment you flick the light bulb on and off, the photons were all very, very close. They were at the point where the light bulb is. A second later, all of the photons are 300,000 kilometers away. 2 seconds later, all of the photons are 600,000 kilometers away. So as you stack up these different pictures of space, what you get is the photons going from a point out in all directions, forming a cone in space-time. That's the light cone. This is as fast as you can possibly go in the universe. And the fact that the speed of light is the same to everybody means that different observers construct the same light cones. So if somebody else moving by you at a speed of some large number of hundreds of thousands of kilometers per second in their spaceship also flicked on a light bulb at the same event as you did, their photons would do the same thing as yours did. They would form the same light cone in space-time. So what Einstein is really saying is that instead of dividing the universe into space and time, we divide the universe into the light cones that we can imagine making. We don't need the actual light bulb. We don't need to actually flick anything on and off. There doesn't need to be any actual light. This is part of the structure of space-time itself. You could, starting at any event, draw the light cone coming out of it, or draw the light cone going into it from all the hypothetical light rays that would reach that point rather than leave it. Now, usually when people give the popular introduction to relativity, this is not the language they use. They talk the language of time dilation and length contraction. Time dilation is the idea that if a clock is moving very quickly by you, you would see it tick more slowly, just like the muons going by you seem to take more time as they measure it to get down to here on Earth. Length contraction is the idea that as something moves by you, it is squeezed in the direction. It is contracted along the direction in which it is moving. As my favorite example, the Large Hadron Collider in Geneva, this giant particle accelerator, moves protons very, very close to the speed of light and then smashes them together. You think of a proton as a spherical collection of quarks and gluons, but when they actually smash together, they are more like pancakes. The contraction in the direction in which they're moving smashes the two pancake-like structures together. Now, it's a perfectly legitimate way to talk about relativity in terms of time dilation and length contraction. But to me, I find it confusing because you're trying to measure something at different points in space at the same time, which is exactly what Einstein tells you not to do. You're trying to measure the length of something, different points in space, at one moment in time. I think it's actually much more helpful to think of physics absolutely locally, to say, what can I measure here at this point, forgetting about the changes in lengths and time as things go by me. Think about what their clocks would read when they return to where I am. So with that philosophy in mind, what are the light cones getting us? The light cones are giving us a structure on space-time because we cannot travel faster than light. So if I flick my light bulb on very, very quickly right now, I have a bunch of photons leaving, and the point is that I can never catch up to them. I can never go faster than they are, so they will always be receding from me at the speed of light, no matter how hard I try, no matter how powerful my rocket ship is. So if I draw that light cone in space-time, what I'm drawing is my personal future. My future is only the points inside that light cone. If there is some event, some point in space and time that is outside the light cone, then in order to get there, I would need to travel faster than the speed of light. That means that that point is simply inaccessible to me. I can get to that point in space, but not to that point in space-time. I cannot get to that point in space at that particular time. So what Newton would have done is to divide space-time into past, present, and future. What Einstein does is divide space-time into the past of my event, the interior of the light cone that is approaching me at this point in time, the future of my event, the interior of the light cone that spreads out from me in space-time, and the unreachable parts of the universe, the parts that I would have to travel faster than the speed of light to get to. So the lesson is that in special relativity, time is not universal. It's personal. It's measured along an observer's world line. Now, don't get me wrong, you can slice the universe up into equal moments of time. I can talk about what time is it right now at Alpha Centauri or the Andromeda Galaxy. The problem is not that you can't do it, the problem is that there's no one right way to do it. There are an infinite number of ways to slice up space-time into space and time, and none of them is right and none of them is wrong. The division of space-time into space and time is not absolute anymore. It's not a Newtonian universe. As a result of that, the rules for moving through space-time are a little bit different, and this is going to become important because soon we're going to talk about time travel. The Newtonian rule is that there is a past, present, and future, and you must keep going toward the future. Whatever time you're at right now, 1 second from now, you will be 1 second into the future. What Einstein says is that you must stay inside your light cone. So the reason why that's going to become important is because in special relativity, what we're talking about right now, the light cones are fixed, they're rigid, they're there once and for all, they are the absolute elements of space and time. But in general relativity, you can move the light cones around. So the fact that all we need to do is stay inside our light cone is going to become crucially important. One of the ramifications of this for us in this course is that we care about Laplace. Remember, Laplace said if I knew the universe at one moment of time, I could predict its future and retrodict its past. Einstein says there is no such thing as the universe at one moment of time, once and for all. Don't worry about that. The point is that Laplace still works. It still remains true that if we know everything about the universe at any one moment of time, we can predict the future and retrodict the past. The only difference is that there's no unique way to say what you mean by any one moment of time. But the fact that it's non-unique doesn't matter. That means there's many, many, many ways to give the data of everything in the universe going on at any one moment of time. The important thing is you can work forwards and backwards. So special relativity doesn't help us with the arrow time. It's still a puzzle. We need to move on to general relativity to understand space and time a little bit better. Probably the most direct and immediate way in which human beings relate to time is by projecting ourselves into other moments of time, mental time travel. In other lectures later on, we're going to talk about physical time travel, hopping in a spaceship and moving around through a curved space-time and ending up in the past. But that's probably against the laws of physics, as they will eventually be understood. Mental time travel, on the other hand, is something we do all the time. We either have memory, putting ourselves in the past, trying to remember what was going on at some previous time, and we also have projection into the future, trying to imagine something that hasn't happened yet. Both of these procedures, remembering the past, predicting or projecting into the future, turn out to be absolutely crucial for human consciousness, not just for remembering and projecting other times, but for how we process information and make sense of our lives. So to investigate this just a little bit obviously requires going back to psychology and neuroscience. Even more than in the last lecture, what we're going to learn is that the human brain is a complicated place. It's a much harder thing to understand than the physical universe. And the single lesson we will get over and over again is that the brain does things in a very distributed way. So think about memory in particular. We sometimes think about memories and how they work in our real human brains in the same way that we think about a photograph or a file on the hard drive of our computer. It's some data stored in some place, reflecting an image or some description of a past event. But the human brain is not like a computer, and human memory is not like a hard drive. If you think about it a little bit, this makes perfect sense. For one thing, evolution, which gave us the brains we have, didn't drive towards building a computer. It built itself up very gradually through accidents and taking advantage of random changes in our DNA. But even more subtly than that, it just wouldn't make sense to imagine that a part of the human brain was left empty until we filled it with some memory. On a computer hard drive, you have the empty memory, then you put a file here, you put a file there, you put a file there until you filled up your hard drive. The human brain doesn't work like that. It doesn't have one part of the brain which is physically connected with one memory, another part which is connected with another memory, and so forth. It's a much more subtle and complex process, exactly as you would imagine, reflecting on how the human brain came to be according to the theory of evolution. Given that sort of obvious understanding about how memory works, we can nevertheless look at particular parts of the brain and see what role they play in memory. It's not going to be that there's a memory organ. There's going to be different parts of the brain that do different things, and nevertheless we can identify some of the things that we do. Probably the single most important part of the brain when it comes to memory is the hippocampus. Remember, we talked about the cerebral cortex, the gray matter that is the outside part of our brain, where we do our higher brain functionings. The hippocampus is part of the limbic system, which is inside, connected to but interior to the cerebral cortex. And the hippocampus is the most important part when it comes to memory. There's many specific kinds of memory functions served by the hippocampus. One simple one is place memory. Place memory means exactly what it says. It's the memory we have for different places in the world. You look around and you recognize that you're at home, or you're at work, or you're in your favorite restaurant, or you're in your car. So we can ask the question, how does that happen? What is the actual process that goes on in your brain when you look around and recognize that you're in this place rather than some other place? So this is something that is just at the beginning of the kind of thing that neuroscientists are trying to understand. What we can do right now are experiments where we look at the firing of individual neurons when a certain mental procedure is taking place. So for example, you can be asked to remember a certain memory, or just look around and recognize a certain place, and the neuroscientists can look at specific neurons in your hippocampus or elsewhere, and they can figure out what fires. It turns out that the hippocampus has particular cells called place cells, which give you place memories. These cells always fire when you are trying to recognize what place you're in, or trying to recognize other places in photographs or depictions. So this is a fascinating fact, that memory of places, knowing where you are or where a certain picture is confined to a certain part of the brain, a different part of the brain than, let's say, remembering a person or remembering a song. There are literally cells that help you remember what place you're in. But it's not that the place cells in the hippocampus have one cell per location. It's not like, here's the cell that fires when I'm at home, here is the cell that fires when I'm in my car, or anything like that. Again, you wouldn't expect that to be true because there would be a whole bunch of unused cells depending on how many places you had in your brain. Rather, what happens is that there are patterns of place cells that fire. If you're in a certain location, then about 50% of the place cells in your hippocampus will be firing. If you're in a different location, again, about 50% of those cells will be active, but it will be a different 50%. There will be overlap. It's not like there's this 50% and this 50%, therefore you can only remember two places. There are patterns that are forming in your hippocampus, and those patterns repeat themselves every time you recognize the same place. There is some pattern of cells in your brain that lights up when you look around and notice that you are at home. There is a different pattern of cells that lights up when you look around and notice that you are in your work or some other building. These location memories, as it turns out, are some of the strongest memories we have. We all know this sort of intuitively. If you drive to work, or if you commute even by walking or by taking the train, we all know that at some point, the repetition of this, the doing it over and over again, transfers that memory to a deep part of our brain. And you actually don't need to be paying attention to where you're going. You can do the commute even if you're driving your car, even if you're literally moving the steering wheel and pushing on the accelerator. You don't really need to be paying close attention to what you're doing. That part of the memory you have of where you're going and how to get there is utterly subconscious and very, very strong. This fact that memory of places is so strongly embedded in our brains actually helps you in a memory trick. There are people who get into the Guinness Book of World Records and so forth for memorizing long lists of random numbers or long lists of words. It turns out that these people don't have genetically superior memories. There are techniques for remembering complicated, unrelated lists. And one of the best techniques is to think of a complicated place, to think of some castle with many, many rooms in it, for example. And it doesn't matter that the castle isn't real. You can invent a place. You can create in your brain an elaborate place with many, many different sub-places. Your brain can remember the map very, very well. And then when someone gives you a list of random words or random numbers, the well-trained rememberers will put every word or every number in a different room, in the place that they have constructed in their minds. So when it goes back to remembering the list, they don't remember the list itself. They know, oh, what was the number that was in room number 1? What was in the number that was in the living room? What was the number that was in the dining room, etc. They're taking advantage of the fact that remembering places and maps is much better and stronger in our brains than remembering random lists of numbers. Another intriguing thing that has been learned by the neuroscientist is that even in complicated memories, you can have a single neuron which will always fire. So for example, there is something called the Jennifer Aniston neuron. This is very surprising because 100 years ago there was no such thing as Jennifer Aniston. But a psychologist doing an experiment noticed that when he showed a list of pictures, many, many different pictures, to test subjects, he was looking at a certain set of neurons, and you can't map one neuron in one brain to one neuron in another brain, but in any individual patient, whenever he showed either a picture of Jennifer Aniston or a picture of the TV show Friends or the words Jennifer Aniston, the same neuron would light up. This is, again, not because that one neuron contains everything you know about Jennifer Aniston. It's because there are many other neurons that the neuroscientist is not keeping track of. But the concept of Jennifer Aniston gets that neuron to light up. It's not the picture. It's not the words in the name Jennifer Aniston. It's the very concept. This is just, again, another illustration of how complex memory really is, about how the many different ways we remember things play out in our brains. So one of the things that we've learned is that different types of memory are associated with different parts of the brain. We said the hippocampus is, number one, the primary memory-keeping part of the brain, and in particular is associated with place memories, with where we are. The hippocampus is located inside something called the medial temporal lobe, and the combination of those two things help with memory formation, with consolidation of memories. Your memories can get more accurate the more you think about something, and with what we call explicit memories, facts, events, the order of different sequences in time. There's also the cerebellum, which is in the back of our brain, next to the cerebral cortex, which helps with motor learning and procedural memory. When you're driving that car, you don't need to actually think exactly about where do I put my key, when do I turn the steering wheel, and so forth. Your brain takes care of that, and that is stored in the cerebellum. There are other organs. There are the basal ganglia, there are the mammillary bodies for recognition memory, smell, unconscious memory. The point is, this is not a quiz. You don't need to remember all the different parts of the brain, but the point is that different parts of the brain, which presumably evolved biologically over many, many millions of years for different purposes, all play a role in what we call memory. There's also a part of the brain called the amygdala. The amygdala is actually not a place where memories are stored. It's actually a place where emotions come to be. The amygdala starts firing really strong whenever you have a strong emotion, and in particular, fear is something that is associated with the amygdala. In patients where the amygdala has been damaged or removed, it is found that they don't feel fear. So that's obviously important. You can ask, what does it have to do with memory? There is a phenomenon known as memory enhancement. If you are perceiving something for the first time, if you're seeing something, hearing something, learning about something, at a time of strong emotions, if your emotions are strong, the memory that you have of that experience will be better. You'll be able to better recall specific details later on. It'll be more vivid to you a long time later. It turns out that this phenomenon of memory enhancement goes away when the amygdala is damaged. So not only do different parts of the brain literally store the memories, but other parts of the brain where the memories are not stored come into play when it comes to storing them more or less efficiently. That's just how complex the brain is. So how do we know all of this? Sometimes it's because we do studies where we put someone in a fMRI machine and sort of try to map out activity in the brain. Other times it's when we literally open up the brain in a little rat or in a mental patient. But sometimes it's because there are people who have damage to different parts of their brain. We've talked about people whose amygdalas are damaged and do not feel fear response in the same way. There are other parts of the brain that can be damaged that lead directly to problems with memory. If you've ever seen the movie Memento, it was about a guy who could not form new memories. This is called anterograde amnesia, as opposed to retrograde amnesia. Retrograde means going backwards. Retrograde amnesia means you forget things you used to know. Anterograde amnesia means you can't form new memories. It is caused by drugs, by brain injuries, in particular damage to the hippocampus. The hippocampus is crucial for forming new memories. The subject in Memento, in the movie, had an accident and after that moment could not remember anything more than a few minutes. As you can imagine, this creates very interesting cinematic situations, but it's a very real syndrome. There are patients who cannot form new memories. As you might imagine, a human being who can't form a new memory has lost something that is very central to what we think of as being a person. You meet a person, you give them your name, you wait 5 minutes in the future and they can't remember meeting you or what your name is. They literally live in the present, plus whatever memories they formed before the event that gave them the anterograde amnesia, but they can't learn anything new. The interesting thing is that when you give people with anterograde amnesia tests, psychological tests to see how well they're doing, patients with this kind of amnesia inevitably score happier than regular, fully functioning human beings. I don't have any deep moral lessons to draw about this. It is certainly a tragedy when a person has this form of brain damage, but it's interesting to contemplate the relationship between memory formation, happiness, and the struggles that we have going through life. Even for people whose brains are fully functioning, we all know that memories are not perfectly reliable. We sometimes misremember things. That is not a surprising thing. What is surprising is precisely how unreliable memories can be. Not only can you misremember things, but you can have dramatically detailed false memories that are as vivid and true to your perception as any real memory is. Scientists and neuroscientists in particular are fascinated by the process by which memories are formed, both true ones and false ones. There's factors of misperception, misinterpretation, false similarity between different things that can cause you to misremember what happened. In one famous experiment, subjects were presented with a list of words, but the words were not random. They had similarities between them. So for example, your list of words would say sugar, candy, honey, other sweet kind of things. Then later on, some time would pass and you're asked to remember the list of words. Now, you will not be surprised to hear that sometimes you misremembered, you added some words that weren't there. You will not be surprised to learn that the kinds of words that are typically added were not random. They were in the same kind of category as the list. So if your list was sugar, candy, honey, you would remember words like sweet or chocolate or other related words. The reason why this isn't surprising to us is we think, well, the brain is trying to remember, trying its best to come up with words were on the list. It remembers that the list was full of words involving candy or sweetness, so it would put some words in there that are related to candy or sweetness. However, that's not the whole thing that is going on. It turns out that once the patient recalled this incorrect word, like chocolate, for the list, the psychologist could come back and say, actually, that word was not on the list. And the patient would say, yes, it was. Their memory of that word, once they invented the fact that it was there, is just as vivid as the real words that were actually on the list. This is true even if the subjects who were brought in for the experiment were told ahead of time that the purpose of the experiment is to test false memories. It is absolutely fascinating that the falseness of a memory has nothing to do with how vivid it is or how confident we are that it is true. Another example of how memories that are false can get into our brains is interference. You have a true memory that is in your brain, and psychologists can degrade that true memory, make it less vivid to you by interfering with how you remember it. There was another test in which subjects were shown a picture of a Datsun car, so you know when this was from, the 70s or the 80s. There was a Datsun stopped at a yield sign. So the patients were asked to look at this picture. They were later asked, did another car pass the Datsun at the stop sign? So even though the actual picture had a yield sign in it, they were asked as if the picture had a stop sign in it. What the result was that they were less likely to get right the answer of whether there was another car in the image. Even though the stop sign and yield sign had nothing to do with the other car, the fact that the experimenter put this false thing into their brain made them less likely to correctly remember other things about the image. Finally, of course, there are wholly new memories that can be put into the brain. The psychologist Elizabeth Loftus did a study called now the Lost in the Mall study. Subjects were told 5 stories, and they were told that these stories came from their close relatives who told them cute little anecdotes about their childhood. 4 of the stories were true stories. 1 was a false story, just as elaborate, filled in with plausible details about a time they got lost in the mall and had to be rescued by some passerby and were eventually returned to their parents. What the subjects were asked to do was to simply fill in the details, to say anything they could remember about those stories, or to say simply they didn't remember that event at all. 1 of the 5 stories was false. It turns out that about 25% of the subjects remembered that story, the false one, and filled in the details no problem. Even when they were told that 1 of the 5 stories was false, 25% of the subjects couldn't figure out which story was false. To them, the false story was just as true as the true ones. In fact, I have sometimes served as a science consultant on Hollywood movies, because as an expert in time travel, science, extra dimensions, as you can imagine, there's plenty of movies that want to know how that might happen. It was interesting and amusing to me when I talked to a friend of mine who was a psychologist. She was outraged by the movie Inception. I saw the movie Inception. I thought it was great. I didn't have any scientific complaints. But if you know the plot of the movie Inception, it was about an elaborate scheme to try to implant a false memory in someone's brain. To a working psychologist, that is a silly premise for a movie because implanting false memories is the easiest thing in the world. It's not just false memories. There's also something called false forgetting. If you tell a subject to not think of a word, don't think of the word snorkel. Now, at first you might think that this is hard to do. If I tell you don't think of a pink elephant, you will inevitably start thinking of a pink elephant. It turns out that you can really not think of a word. You can suppress your thoughts about it. You can think about other things to distract yourself. The psychologist Michael Anderson took patients and put them in a functional MRI machine that could map out which parts of their brains were active while they were doing certain tasks, and he asked them to not think of certain words. Interestingly, the hippocampus, which remember is what we use to form memories, had suppressed activity when they were trying not to think of this word. But the frontal cortex, the part of our central cortex, one of the conscious higher order parts of our brains, was highly active. So it was as if the conscious brain was beating up on the unconscious brain, trying to get it to not remember certain words. And it works very well. When you're asked later, the subjects were not able to remember what the word was they were told to not think about. So what is going on? What is happening in the brain where all these complicated things are occurring? Again, we don't know. We don't have the full theory of memory yet, but we do have certain individual clues. One clue is that remembering the past seems to be a very similar function in the brain to imagining the future. Daniel Schachter at Harvard, Kathleen McDermott at Washington University, and other neuroscientists have done studies where, again, they put you in an fMRI machine so they can look at what parts of your brain are active, where the blood is pumping in your brain, and they ask you to do two things. They give you a cue word, like puppy, and they say, remember a time when you got a puppy or saw a puppy, so you conjure up a memory in your brain. And then they say, now imagine a time in a future when you get a puppy or you see a puppy or something similar to the memory. The interesting thing was that when you're thinking about a future event that hasn't happened, or when you're thinking about a past event that has happened, the same parts of your brain become engaged. Remembering the past is a very similar brain activity to predicting the future. Once again, this brings us to a theory. That is the data. The theory says that memory is not like bringing up an image of a photograph from your computer hard drive. It's not like when you have a memory, you store every bit of the videotape someplace in your brain. Rather, when you have a memory, you don't store the videotape, you store the script, the screenplay. You have some data from which the brain can reconstruct the image and the details. You have a set in your brain that says, this is what my living room was like when I was 10 years old. You have a script somewhere else that said, oh, the time when the puppy came to my living room. When you remember that event, so this theory goes, you take the script, you plug in the sets, you bring out some actors, and you recreate the event in your brain in precisely the same way that you create the event in the first place if you're imagining the future. This can help us understand why false memories are just as vivid as true memories. If false memories only require a script in our brain, not a fully detailed set of pictures, it's much easier to imagine how they could get in there and how we could be convinced that they are true. Memory aside, there's also the future. We talked about how memory is an important part of being a human being. Imagining the future, which is very similar to remembering the past, is perhaps an even more important part of being a human being. In a very real sense, thinking about the future, contemplating the future, is the key to what makes us conscious. Now, I certainly can't tell you what consciousness is. If I couldn't tell you what life was before, you shouldn't rely on me to tell you what consciousness is. It's, again, something that is not well understood by anybody. But we do agree that consciousness has certain key features. Symbolic thinking, the ability to think abstractly, the ability to represent ourselves as well as the outside world, the ability to contemplate alternatives, to say not only what is real, but what might be real or what might happen in the future. Like memory, all of these functions are highly distributed through the brain and very complex. There's probably many, many stepping stones along the way in evolution to get from a single-celled organism to a conscious being like ourselves, and we can debate at what step along the way actual consciousness arose. But the more likely story is that there were different steps, all of which contribute. For example, the ability to imagine different futures is absolutely important. If you can't say, well, this could happen or that could happen, what should I do to make the preferred outcome happen, you cannot count yourself as conscious. Linguists have argued that a crucial step in the development of consciousness was the development of grammar. In particular, the ability to use language, not just to point at things and say, that is a rock, that is a cave, that is a tree, but the ability to speak in the subjunctive mood, to say, if you do this, I will do that. Once you have the ability to use language in that way, you can make agreements with other people, not just convince them to do something by threatening them. You can actually make up a contract. You can develop more elaborate societies based on thinking about the future. That is a relatively late step in the history of consciousness, there's also an earlier step that also refers to how we think about the future, which is the idea of making decisions. Malcolm McIver at Northwestern University has a theory that one of the most important steps in the development of consciousness happened 350 million years ago when the first fish crawled out from the sea onto the land. He is not a neuroscientist or a philosopher. He is an engineer, and he studies fish and land animals. And he points out that in the sea, you can only literally see in front of you a few meters. When you're inside water, when you're in the ocean, your visual field doesn't extend that far. When you climb out onto land, suddenly you can see for hundreds and thousands of meters. So McIver's theory is that if you're an ocean-dwelling, sea-dwelling animal, the only thing you have time to do is to see something and react. You see something, it's either food or it's an enemy, make a quick choice. But once we climb out onto the air, now we can see for a much longer distance. That means that we can see both threats and opportunities coming and have much more time to take advantage of them. Once you can see a much larger distance, our brains are now selected by evolution for the ability to contemplate the future, to keep in your mind alternative possibilities. That was not a useful skill, McIver says, when you are a fish or an eel or an octopus. It is a useful skill once you've climbed out on land. This is a step toward consciousness, the ability to think about different things at once. Having said all that, we will admit that the actual process by which we do consider alternative futures and make decisions about them is still very mysterious. It seems to be the case that human consciousness is more like Congress than like a dictatorship. It's more like a parliament where there are many little subcommittees arguing with each other than like a top-down structure where there is one totalitarian self that gives instructions to everything else. There is a classic study done by Benjamin Libet from the UC San Francisco in the 1970s that basically proves that you make decisions, at least in some contexts, before you even know it. What Libet did was to have you watch a moving dot moving around in a circle. So it was moving quickly, so it was basically like watching a clock. And Libet asked you to make a decision, just randomly, sort of decide when you're going to push a button. And when you made that decision, mentally note where the dot was. So essentially you're saying at what time you made the decision to push the button. And then, of course, you push it. He found, to nobody's surprise, that you decided to push the button 0.2 of a second before you push it. It takes some time for the signal to go from your brain to the finger that actually does the button pushing. But at the same time, Libet hooked people up to an EEG machine, an electroencephalogram, and he recorded activity in the brain. What he found was that there was a particular part of the secondary motor cortex that always fired 1/2 of a second, 0.5 of a second before you actually push the button. In other words, the brain does something before you consciously make the decision to act. 0.3 of a second before you know that you're going to push the button, some part of your brain knows that you're going to push the button. In subsequent tests, this was shown that you could even stretch that out to longer than 0.3 of a second, and a great deal of debate has gone back and forth. The question that studies like this raise is, how conscious are we, really? How much free will do we have? If my brain decides to do something before I even know about it, who is it that is doing the deciding? This may or may not be a good question. All that science is going to do is tell us how it works. We can decide what to make of it ourselves. And how it works is that the brain is a complicated thing. There are many little sub-processes going on. The way to think about ourselves is not as a little dictator telling our brain what to do. Ourselves are the emergent phenomenon that we get from all the different parts of the brain coming together to make us who we are. You've been very good. If you're following the lectures in order, you're more than halfway through the course. And I thought that as a reward, in this lecture, we would answer the question that everyone has when they're first talking about the mysteries of time, namely, why am I always late? This is not a question to which I can give a specific answer. It has more to do with your circumstances than with any scientific principles. But what we can do is talk about how human beings perceive the passage of time, how we in our brains and in our bodies measure time as it passes. We already talked about in earlier lectures the idea of using a clock to measure time. A clock is something that does the same thing over and over again in a repetitive and predictable way compared to other clocks. The reason why we human beings feel the passage of time is because our bodies have clocks in them. We have things that happen in a rhythm over and over again. You have your heartbeat, your breathing, the pulses in your central nervous system. Even Galileo, when he was in his cathedral in Pisa, and he first figured out that a pendulum rocking back and forth took the same amount of time, the way that he did that was to compare the oscillation of the pendulum to his heartbeat, to the best biological clock that he had available. However, biological clocks are not very reliable compared to a good mechanical or electronic clock. That's because our bodies are affected by many things that are outside our control, whether we are tired or exhausted, whether we have adrenaline rushing through our system, also our mental state. Are we focused on something or are we distracted by the world around us? Finally, the way that we get memories and keep them affects how we perceive the passage of time. So we do feel time passing. In many ways, it's pretty accurate, but there's always something that makes us not completely perfect compared to, let's say, a good atomic clock. To set the stage for this discussion, let's just talk about biological rhythms more generally. In any organism, there are things that happen over and over again. That's what a rhythm is, something that repeats itself over and over. The heartbeat is probably the single most fundamental rhythm that an advanced living organism has. We can compare how these rhythms work in different kinds of animals. And just to keep everything else as constant as possible, we can compare how mammals have different rhythms inside their bodies. One way of thinking about an advanced organism like a mammal is it's a network. You have the brain and you have all the different things coming out of the brain, the nervous system, your circulatory system, and so forth. And you can actually make predictions on the basis of network theory for how the rhythms cascade through your body and then compare those predictions to data. So Jeffrey West at the Santa Fe Institute, who studies complexity, he was a physicist at first, but he went into complexity studies as that field came to life and became more exciting, has asked the question about how the networks in different mammals are affected by their size. You find two of the most basic relationships are that if you're a smaller animal, your networks move faster. In particular, your heart beats faster the smaller you are. The less weight you have, the faster your heartbeat is. On the other hand, he found that smaller animals also live shorter lives. The lifespan, the typical lifespan of a tiny little shrew is much shorter than that of a giant elephant or a blue whale. So if you think about this, a smaller animal has faster heartbeats and also doesn't live as long. A larger animal has a slower heartbeat and lives longer. You might wonder, do these effects cancel out? And the answer is yes. As a very rough rule of thumb, every mammalian species, on average, has the same number of heartbeats in its lifespan. That number turns out to be 1.5 billion. Roughly speaking, every mammal gets 1.5 billion heartbeats in its life. Now, don't take this too seriously. When I tell this to people, they sometimes worry that this is a strict rule, that no matter what you do, it's almost like predicting the future, you will live for 1.5 billion heartbeats. And they wonder, should I exercise more? Should I exercise less to get more or less heartbeats? That's not how it works. It's an average. Of course, many animals live a little bit shorter, a little bit longer, but it's an interesting feature of our biology that somehow a shrew and an elephant have similar blueprints, just taking reality in different forms, in a really tiny form for the shrew and in a bigger one for the elephant. This kind of scaling law goes far beyond organisms. It goes all the way down to the cellular level. West and his collaborators were able to use this kind of scaling relationship to make predictions for the rate at which individual cells behave in certain ways if they're in an organism or outside an organism. They made predictions which hadn't yet been tested. After they made a prediction, they were tested. The idea that a human being is a complex network of smaller functions talking to each other is a very good fit to how real animals live. Of course, unlike shrews and elephants and blue whales, we human beings have another variable, which is the culture in which we find ourselves, the environment around us, the human environment in which we're embedded. And we all know that different cultures approach time differently. The psychologist Robert Levine, who studies how human beings interact with time, is based in Fresno, California, but he sometimes spends time in other countries, giving lectures and so forth. He tells a wonderful story of his first semester in Brazil. When he was going to give a lecture, it was scheduled to go from 10 a.m. to noon. It was a regular class he was teaching. He's walking down the street and he asks someone what time it was, and they said it was 9:05. He didn't have a watch himself. So he says, I have plenty of time to get to my lecture at 10 o'clock. About half an hour passes, and he asks someone else what time it is, and they say it's 20 minutes after 10. He panics, he rushes to the lecture room, and there's almost no students there yet. He says, what is going on? So he asks the students what time it is. One says it's 9:45, they're looking at their watches. One says it's 9:55, one says it's 5 minutes past 10. What Levine realized was that no one's clock in Brazil reads the same time, and nobody cares. The students sort of came in very, very gradually to the 10 a.m. class. By 11 a.m., the room had more or less filled up. But it wasn't that the students were lazy or didn't want to go to the lecture. When noon came along, he said that in California, when the end of the lecture was scheduled, you would know. Every single student would be rustling in their chair, looking at the clock, ready to go. In Brazil, none of the students moved. Who cares? It was 12 o'clock at the end of the lecture. They were still interested. They had questions. They kept discussing. It became 12:30. Eventually, he had to escape. The point is that different cultures approach time differently. Levine also spent time in Japan, and he says, of course, compared to what you would do in California, the Japanese found that his natural timekeeping was incredibly lax and kept telling him to hurry up. In Brazil, they kept telling him to calm down. It's not these anecdotes that are really important. What's important is data. Can we actually do a scientific experiment to justify these stories about how different cultures perceive time? And the answer is yes. A bunch of different studies have been done to basically try to measure the pace of life in different cities, different cultures, different environments. For example, you can take how long it goes if you walk up to a post office and you want to order some stamps. Psychologists have sent people to order stamps in different post offices in different cities throughout the world and found consistent differences in how long it takes to get those stamps to get to you. There's also a study where you can just measure how fast people are walking. You sit there in the cafe, you watch people walk by, you measure how fast they're moving, and once again you find systematic differences in different cultures and in different cities. For example, you will not be surprised to learn that in higher population areas, people walk faster. People literally will walk faster down the streets of New York City than they will down the streets of a small town in Massachusetts. It's not because everyone else is walking faster, it's just because that's what the environment does to you. Another obvious effect is technology and industrialization. Psychologist Richard Weissman has compared the pace of life in cities over time. So he does this walking experiment. He sees how fast people are walking down the street, but rather than comparing one city to another one, he compares one city 20 years ago to the same city today. What he found was that over the last 20 years, the pace of life has increased by 10%. That doesn't sound like a lot, 10%, but it's only in 20 years. How quickly will it go over the next century? Weissman also found that the effects are different from place to place. Singapore was up 30%. Guangzhou, a city in China, was up 20%. The areas of the world that are developing and industrializing and gaining high technology the most quickly also see their pace of life increasing the most quickly. Nevertheless, your stereotypical guesses aren't always right. It turns out that New York City is far and away not the fastest walking city in the world. In fact, it's behind cities like Dublin and Madrid and Copenhagen. There are many complex features that go into how quickly life is lived in different environments. Technology and density are very important, but we are very far away from having a complete theory of how this works. Another place where we're very far away from having a complete theory is how individual people perceive the passage of time. There's one lesson that we have certainly learned, which is that the human brain is not a computer program. We think about the human brain as very similar to computers because the human brain clearly computes in some sense. We can mimic some things the brain do in a computer program, but the way the brain came together is very different than the way you would write a computer program. The brain developed over literally billions of years of evolution of life here on Earth via incremental change through random possibilities being tested and seeing what works. A computer program, on the other hand, is usually written from the start. You have a task in mind, and you're going to design it from the top down in the most efficient way you can. Therefore, in a computer program, if you want to store data, for example, well, you have an array that you can put the data in, and that's that. In the brain, any task that you might want to do is probably shared among many different pieces because that's what was useful at the time. In particular, when it comes to keeping time, to measuring duration, there are different parts of the brain that kick in. It's a highly distributed feature. It's not like a simple clock that you have in your computer. There's some chip that has a rate that you can buy a faster and faster chip. The brain has many, many pieces, each one of which contributes to our understanding of time. As one experiment to demonstrate this that is very vivid, neurologists did an experiment with rats. And we should keep in mind is that neurologists, neuroscientists hate rats. They're constantly torturing these poor little rats. So the rats have a brain much like we do. They're mammals, as far as all of life is concerned. Rats are pretty close biologically to human beings. They have a complex brain. They have a cerebral cortex, which we have also. It's the gray matter in our brain. The cerebral cortex is the outside part of our brain. It's where we do our higher information processing. The life of consciousness is happening within our cerebral cortex. There's also other organs inside the cerebral cortex, which are more primitive. We think of them as giving us subconscious brain functions. So you can actually take a rat and remove its cerebral cortex. Remove sort of the advanced parts of its brain, but the rat will still be alive. It won't be able to do mazes and other things that we teach rats to do, but what the neurologists, neuroscientists have found is that rats can still tell time even with their cerebral cortex removed. They give them a little task like pushing on a lever. If they push on the lever once every 40 seconds, they get a food reward. The rats without a cerebral cortex can measure the time interval of 40 seconds. That means that whatever we're doing, when we're measuring duration and time, it's not a matter of our conscious brain. There are unconscious things going on. And there's more than one thing going on. Another experiment with mice was able to show that mice with their whole brains intact could keep track of at least 3 different rhythms. These mice had 3 different paddles that they would push to get food. And to get the food, one paddle needed to be pushed once every 10 seconds, once had to be pushed once every 30 seconds, and once had to be pushed once every 90 seconds. The mice were able to separately keep track of the time intervals necessary to get the rhythms right in all 3 paddles simultaneously. And you might think, well, 30 seconds is 3 times 10 and 90 seconds is 3 times 30, so you just press this one 3 times and this one once, etc. But you could actually turn on and off the rhythms. You could displace the rhythms so that the 10-second one was out of phase with the 30-second one and the 90-second one. The mice could still keep track. So inside our brains is more than one timekeeping device. In fact, you can sort of roughly divide it up into different kinds of timekeeping. As you are listening to this lecture right now, there is a part of your brain that is keeping track of what time of day it is. This is your circadian rhythm that tells you when you wake up, when you go to sleep. There's another part of your brain that is keeping track of how much time has passed since the lecture started or since you started listening to it. And there are yet other parts of your brain that are more or less like alarm clocks. They keep the amount of time before some relevant future event. If you want to go to dinner or go to bed or something is going to happen, how much time do you have before that happens? Your brain is keeping track of that. Now, this is a complex set of operations. We don't have a grand unified theory of everything. This is why brain science and biology is much more complex than physics is. But neuroscientists have been able to isolate at least 3 different kinds of time perception, 3 different ways in which we increase or decrease the rate at which time seems to pass for us. The 3 ways are, number 1, pulses, sort of the basic way that you would keep track of time in a clock or with a pendulum going back and forth. There are pulses in our brains and we simply count them. Another thing that affects the passage of time is our sensory input and focus. What are we paying attention to? And finally, and sort of most intriguingly, the way in which we accumulate memories affects our notion of how much time has passed. The more memories we accumulate, the more time we attribute to what happened. So let's consider these 3 aspects in order. When we say counting pulses, it makes you think that there is a little part of your brain that is almost like a pendulum going back and forth. And that is not true, or at least we don't know of any single part of the brain that acts exactly like a clock, like a chip in your computer. Rather, there are multiple levels of pulses. The different neurons in your brain do work via pulses. It's not that the neuron is constantly sending signals. It's that there's a signal or there's not a signal. So neurons turn on and off. There's multiple levels of pulses due to all the neurons in our brain, and together they help us perceive the passage of time. Again, you will not be surprised to learn that we can affect how quickly those pulses go. For example, we can affect them through drugs. Stimulants make our pulses beat faster. If you drink caffeine, the pulses in your brain that keep track of time go a little bit faster. Depressants will slow them down. If you have alcohol or other depressants, even something like marijuana, the pulses decrease in their rate, and it takes us longer to accumulate a certain perceived amount of time. Now, whenever we talk about this kind of phenomenon, we have to be very, very careful because people say, well, you drink caffeine and time speeds up. But in fact, as we talked about way back when in the early lectures, time is always moving at 1 second per second. When you want to say that time speeds up, what you mean is that one clock has sped up compared to some other clock. When you drink caffeine, your clock speeds up. But what that means is that when you compare it to the world has slowed down. So your clock has sped up compared to the outside world. We have to be sure to get that right when we're talking about effects on our internal clocks. These effects from stimulants or depressants, we think, are effects on the neurotransmitters that send signals from our neurons to other cells in our brain. Neurotransmitters like dopamine and other chemicals are what the neurons send, and they do it in the form of pulses. Caffeine or alcohol or other drugs can make it easier or harder for these neurotransmitters to be sent that speeds up or slows down our internal clocks. But that's usually not what makes you late. If you want to know why you're always late, it might not have anything to do with caffeine or booze or anything like that. It's probably due to the second aspect, which is the sensory input and focus. When you are focused on a task, when you have a really hot first date, or when you're in a really engrossing project for work or at home that you're really in love with, you don't pay as much attention to the outside world. And in some sense, which psychologists still don't understand, you also don't pay as much attention to your internal clocks. So your effective internal timekeeping device slows down. The outside world speeds up. If you're having a really interesting date or conversation with someone, you think that a half an hour has passed, but in fact it's been like 2 hours. Your focus on one task makes it harder for you to tell time. Usually, if you're late, it's because you've been focusing on something else. Contrary-wise, if you're bored, if you're on a plane ride and there's nothing going on, if you have a tedious aspect to your job, your attention is constantly flitting around. You are not focused on any one thing, and the opposite effect happens. Your internal clock seems to go faster, the outside world slows down. It seems to take forever to get that plane ride across the country simply because you're bored and your attention keeps wandering. The final aspect is the rate at which we form new memories. So this is a fascinating thing that neuroscientists are just beginning to understand. You might have, as an example, this idea that if you're in a high-stress situation, time seems to slow down, by which we mean your clock speeds up, the rest of the world seems to slow down. This was noticed by a neuroscientist named David Eagleman long before he was a working neuroscientist. When he was a child, he once fell out of a tree. And it was long enough that it was not so long that he was really hurt, long enough that he was very scared as he was falling out of the tree. And he remembered, as he grew up and became a working neuroscientist, that the world seemed to slow down. If you've ever been in an accident or a very, very stressful, sudden situation, everything around you seems to move more slowly. So Eagleman wanted to know, is it really true that in these high-stress situations, your internal clock beats faster, therefore making the rest of the world seem to slow down? The problem with this question, as a working scientist, is that to answer it, you need to scare people. And that's not really good procedure when it comes to human subjects. But what Eagleman did was to figure out a way to scare people in a way that wasn't really dangerous. He threw them off of a tall building. But he threw them off of a tall building onto a trampoline, so it was actually perfectly safe. And while they were falling off the building, the theory was they would get scared, there'd be adrenaline going through them, even though they knew there was a trampoline down there. They weren't surprised by the trampoline. And he had them actually do little recognition tests. He gave them little pieces of equipment that would flash numbers on a screen, and it flashed them either fast or slow. If they were so fast, they would be flashing so fast that you couldn't recognize the numbers. If they were going slow, then you had the time to see what the numbers were. And what Eagleman did was to compare how good you were at recognizing the numbers when your adrenaline was running and you were falling out of the building versus when you were just sitting at a desk calmly. The answer is there was no difference. Despite the fact that there was adrenaline going and your pulses were racing, you were not any better at recognizing the quick flashing numbers than you would have been sitting calmly at your desk. So therefore, in that sense, the speeding up clock inside didn't help you perceive the outside world. Nevertheless, if you talked to the subjects afterward, they said that the outside world slowed down. They had a perception that time had slowed down for them in recollection after the effect. So there's a theory about what is going on. The theory is, and it's just a theory, it's not something that we can test very accurately, that the more memories you accumulate, the more time seems to have passed. When you're in a high-stressed, scary situation, your brain does its best to record absolutely everything that has happened. It's scared, it's looking around, it's accumulating a huge amount of data. Even though it's not perceiving things any more quickly than it would otherwise, when you think about that event afterward, you have more memories, you have more data to leaf through. And therefore, it seems to us like more time has passed. This hypothesis gets a little bit of support from a related fact, which again, everyone knows, even if you haven't been in a scary situation. You know that time seems to pass more quickly as we age. When you're older, the summer seems to rush by. When you were a kid, the summer seemed to last forever. This is not just an anecdote. This is not just an idea that people have. This is something that you can test. The theory that Eagleman has and other people have is simply that when you're young, in the summertime, you're going to the beach and whatever, it's all new to you. Everything around you is a new experience. When you're older, you've been there before. It's a little bit more blasé. So it seems to pass more quickly for you compared to what it did when you were a child. And this is something that, again, we can try to test. The way that neuroscientists have tried to test it is to give 20-year-olds a test where they're simply told, starting now, tell me after 3 minutes had passed. And then they give the same test to 60-year-olds. And the answer is that 20-year-olds are pretty good at measuring about how long 3 minutes are. So they have no clocks around them. They're just sitting there quietly in an empty room. They say 3 minutes have passed, and on average, the actual amount of time that has passed is about 3 minutes and 3 seconds. Very, very accurate. But you do exactly the same test to 60-year-old people, and when they say 3 minutes have passed, the actual elapsed time is more like 3 minutes and 20 or 40 seconds. So 20-year-olds are better at estimating time than 60-year-olds. For an older person, it takes longer for the same amount of subjective time to pass. The theory is that that's because they don't create as many new memories, but the fact is that it does take longer. There's even a hypothesis that tries to make it quantitative, that says the amount of time we experience grows logarithmically with our age. It would be very hard to put exact data about that, but it makes sense to us. Think back to that boring plane ride. If you're on a boring plane ride, it seems to last forever. But if you recall it after the fact, it seems to go by very quickly. You might remember that you were bored, but you don't have some elaborate memory of every single event because none of the events were interesting. You were not focusing, so your subjective time at the time seemed to last forever, but you were also not making new memories, so your subjective time after the fact seems to make the trip actually quite short. Another aspect that is very interesting when it comes to how human beings perceive time is a simple statement that we live in the past. So forgetting about measuring time using our internal clocks, what about when we actually just perceive the moment now? We all think, whether we're presentists or eternalists, that there is a moment called now. We are perceiving it. We're looking around. We're getting data, sense data from outside of ourselves, and we experience what we call the present moment. It turns out, of course, and if you thought about it a little bit, it would make sense, that what we call the present moment isn't the present moment. That's because it takes time, number one, for the information to get to us, and number two, for our brain to process that information. The most obvious example of this is if you see lightning very, very far away, you see it, and we all know that if lightning is far away, it takes time for the sound to get to us. You can even count how many seconds it takes and figure out how far away the lightning storm is. That's because sound moves more slowly than light. But it's not just the external world that matters, it's the internal world that matters as well. So for example, you can do this at home, I won't demonstrate, but you can touch your nose and you can also touch your toes. Do it at the same time. Put your finger to your nose and to your toes. And what you will notice is that you feel the touch simultaneously. If you perform the touch simultaneously, you will feel the touch simultaneously. That seems very natural to us. But it shouldn't be natural because the amount of time it takes the nerve signal to travel from our nose to our brain is much less than the amount of time it takes the nerve signal to travel from our feet to our brain. Now, the nerves are moving pretty quickly, but we, as our brains, are very, very good at measuring tiny differences in time, more than good enough to be able to measure the difference between the signal coming from our feet and the signal coming from our face. Nevertheless, we don't perceive that difference. We perceive the simultaneous touches as simultaneous events. Why is that? It's because our brain knows that our feet are further away and takes that into consideration. It turns out that what we consider to be the correct moment right now is actually about 80 milliseconds in the past. The way that you can get that number, one simple way to do it, is to watch a person dribbling a basketball. As they're dribbling the basketball, you both see it and hear it, just like the lightning bolt. And your brain corrects for the fact that it takes the sound longer to get to you. So as the person dribbling the basketball moves away, you see and you hear the sound at the same time in your brain until they get so far away that it takes more than 80 milliseconds for the sound to get to you. At that point, suddenly, there's a mismatch between the sound that gets to you and the sight. That's because you get the vision of it and you put together that in the conscious now before the sound can get to you. So we live about 80 milliseconds in the past. And really, the primary lesson to learn from this is that consciousness is kind of a messy thing. It's very difficult to understand what's going on in the brain because it's a very elaborate mechanism. This is why physics is the right field of study to go into if you have a short attention span. Speaking of which, people have different attitudes toward time. And this has nothing to do with culture. This is just within any one culture. Individual human beings approach time differently. And it turns out, the psychologists have shown that our orientation toward time is a crucial component of how we live the rest of our lives. There's a great experiment that illustrates this called the Stanford Marshmallow Experiment. It was first done by Walter Mischel, a professor at Stanford, in 1972, and it's a simple setup. You offer a child a marshmallow. You fool the child first. Every psychology experiment involves fooling the subject into thinking that it's an experiment about something else. So you make the kid do something, and then as a reward you say, here is a marshmallow for being a good test subject. But then you say, I have another marshmallow. You first check that the kid likes marshmallows. I can give you a second marshmallow if I need to go out of the room for a few minutes. If you wait and you don't eat that first marshmallow, I will give you a second one when I come back. So roughly speaking, when you do this experiment on 3 or 4-year-old kids, only about a half or a third of them can actually wait for you to come back. The kids eat the marshmallow, some of them. Others are very, very patient. They use elaborate strategies of self-deception, looking around, trying their best not to look at the marshmallow. The claim of modern psychologists is that the difference between eating the first marshmallow immediately and waiting to get 2 marshmallows later shows you something about your orientation toward time. There are people who really, in some sense, dwell in the past. What they care about most, what they're talking about all the time, are what happened in the past, what happened when they were growing up, high school, college, whatever. There are other people who live in the present. They want something right now, they want that marshmallow, there it is, and they're going to eat it. There are other people who are future-oriented. They know that there is some benefit coming to them in the future. They will sacrifice the marshmallow right in front of them to get that marshmallow in the future. They're future-oriented. This is not a matter of being rational or irrational. Economists will tell you it makes perfect sense to discount something that is a reward that you won't get until the future. If someone offers you $10 now or $11 10 years from now, you should just take the $10 now, because our brain says, how do we know that they'll be around 10 years from now to give us the $11? That is a perfectly rational thing to do. Nevertheless, the ability to take the future just as seriously as we take the present turns out to be a good predictor through how we approach many things in our lives. The psychologist Philip Zimbardo, also at Stanford, has done a follow-up study on Michel's marshmallow study. He studied now the kids who were 3 and 4 years old. They're now in high school and in college. What he found was that children who waited, who got the second marshmallow by being good, scored higher on their SATs, had better behavior in school, and more scholastic achievement. It turns out that our attitude as human beings toward time is a crucial component in making us who we are. So that was fun. In the last lecture, we did a little thought experimenting. We talked about a cosmological scenario that attempted to account for the arrow of time just by imagining that the universe was infinitely big, lasted infinitely long, and there were random fluctuations that could give rise to people like us. We found that it didn't work. If you lived in that universe, you would make individual complex creatures just through random fluctuations, not through billions of years of evolution, both cosmological and biological. But in the next few lectures, we're going to return to the real world. We're going to say, all right, let's take what we think is actually true about the universe. We did start with a low entropy condition about 13.7 billion years ago. We've been evolving ever since. Let's try to put the actual features of life here on Earth, including how human beings think and perceive time, into this context. Let's see how that matches up with what we think about the arrow of time. One problem with this project, obviously, is that the idea of life is not something we understand very well. We know that living creatures are complex, but our understanding of what life is not very well developed. Thinking about anything living is always going to be more difficult than thinking about physics. That's why physicists get to talk about boxes of gas with partitions and so forth. Once you start talking about biology or psychology or neuroscience, you can't simplify things to boxes of gas. We don't even have a good definition of what life is. We think that living things are complex in some sense. We often talk about the fact that they reproduce, they create other living beings, that they metabolize, they take energy in from their environment and put it to good use. Sometimes we talk about information processing, that something that we might think of as alive can think about the world or represent it. But we don't know which exactly is important and which is not. Is a computer alive? Is a flame alive? Is a galaxy alive? These are questions to which we don't know the answer, probably because they're not good questions to ask. We know that these things exist. We shouldn't worry about whether or not they fit into the definition of life or not. Likewise, what we're going to concentrate on right now is life as we know it. We're not going to try to come up with an absolutely clear definition that could tell us whether something going on another planet is alive. Rather, given how life works here on Earth, how could it have arisen in the evolution of the universe? Let's start by thinking about the fact that life is complex. Living beings are complicated. They have a lot of different moving parts. So your first step might be to examine this notion of complexity. What does it mean for something to be complex? It's one of those things where we know it when we see it, but that doesn't mean that it's easy to come up with a definition. Immediately, we're going to worry about the fact that the whole focus of our course is the second law of thermodynamics, the fact that entropy is increasing and the universe is becoming more disorderly. One way of thinking about that is that the universe is tending toward what is called a heat death. Once the universe reaches equilibrium, there won't be anything going on anymore. Equilibrium means static, nothing happens. The temperature will be the same everywhere, there will be no more living beings. Why is it, we should be asking ourselves, that this tendency toward heat death has given rise to what we think of as life? So let's first start by just trying to give some definition to the notion of complexity. Like life, we don't have a single definition. There are different kinds of complexity out there. But there is a definition that is most common and will be good enough for us. It was proposed by Soviet mathematician Andrei Kolmogorov back in the 1960s. And he was thinking, in the 1960s, they were very interested in information theory and in the new science of computer science. So they were thinking about strings of numbers and wanted to talk about, well, when is a string of numbers, or for that matter, some physical object, complex versus non-complex? So Kolmogorov says, well, imagine you are providing me with the information I need to reconstruct that number or that physical situation. Imagine you have some language, some fixed way of talking. In the back of his mind, obviously, he had a computer language, something that could be very, very formal and rigorous. But we can think about talking in English or in Russian, if you like. In some specific language, come up with the briefest possible description of the thing you're trying to describe, the shortest possible string of words or symbols that would let somebody else reconstruct the thing you're talking about. What Kolmogorov said was that we should define the complexity of something as the length of the shortest description that captures everything relevant about that thing. So for example, imagine a 100-digit number. A random 100-digit number, so just a list of 100 different digits from 0 to 9, that's complex by Kolmogorov's definition, because in order to describe it, I need to give you 100 digits. There's no shorter way to capture what's in there if it's a truly random 100-digit number. On the other hand, if it's a non-random number, if it's some specific number, there might be much more concise ways of describing it. If I tell you 10 to the 100th power, that is a 100-digit number, a 1 followed by 100 zeros. It's a 101-digit number. But it requires far fewer than 100 characters to describe. I just tell you 10 to the 100th power. Pi is a number that requires an infinite number of digits to describe, but not to tell you what it is. I just tell you it's pi, or I tell you it's the ratio of the circumference of a circle to its diameter. These numbers are less complex by Kolmogorov's definition because we can describe them more concisely. Notice that when we're using this definition of complexity, what matters to us is that we have chosen a coarse graining. Just like when we talked about entropy, when Boltzmann said there's every possible configuration of a system, but we can't observe which microstate we're in, we only observe certain macroscopic features, the same thing happens in the real world when we talk about the complexity of something. When we talk about the complexity of some living being or non-living being, some object in the universe, it's not that we have to list the position and momentum of every atom. In that case, everything that had the same number of atoms would have an equal complexity. Instead, we coarse grain. We tell you what we care about. We say that a certain living being has a certain number of moving parts, a certain number of proteins and molecules and so forth. And that's the way that we describe it. That's the coarse grain description that we give. By that definition, the complexity of an organism is Kolmogorov's complexity applied to that coarse grain description. What is the shortest possible way I can convey to you which coarse grained features we are talking about? As a simple example, let's go back to one of our favorite ways of describing entropy increasing, mixing milk into your cup of coffee. We know that if the milk is separate from the coffee, that's a low entropy configuration. If you mix them together, that's a high entropy configuration. Even if you didn't do the counting of the atoms, you would know that was right because it's easy to mix the milk into the coffee. It's hard to get it to unmix. So let's think about this process from the perspective of complexity. Imagine an image of a cup of coffee with milk put on top. Very, very carefully, you put the milk on top of the coffee so they're separate from each other. That's a low entropy configuration. The coffee's on the bottom, the milk is on the top. It's also a very simple configuration. I don't need to give you a lot of information to describe it. I just did. Coffee's on the bottom, milk is on the top. Now imagine I take that cup of coffee and I mix it together. I mix it up all the way. I go to a high entropy configuration where all the coffee and all the milk molecules are mixed together. However, it is still a low complexity configuration. It's a very simple configuration. All of the milk and coffee are mixed together. That is a very short description that tells you everything you need to know. So low entropy can be simple, and high entropy can also be simple. There is no necessary relationship between the simplicity or complexity of something and its entropy. They are two different ways of characterizing some physical situation. But now go back to the middle period of our process of mixing the milk with the coffee. So before we were totally mixed, we began to mix the milk with the coffee, and in your mind's eye, you can picture what's happening. The tendrils of the milk begin to mix in with the coffee. If you took a picture of the halfway process in between the low entropy segregated milk and coffee and the high entropy mixed milk and coffee, what you would see is complex. Because in between, when some of the milk has been mixed but not all of it, there is no simple description that lets you precisely reconstruct what the milk and coffee configuration looked like. If you took a picture of it, you would have to describe at every part of the picture, well, there's so much milk here, so much coffee there, and so forth. In between the low entropy state and the high entropy state was a medium entropy state that was very complex compared to the extremes of high entropy and low entropy. So this is an absolutely crucial insight into the relationship between entropy and complexity. It's not that low entropy or high entropy corresponds to simple or complex. Complexity can arise when the entropy is in between very low and very high. This goes for a cup of coffee. It also goes for the universe. If we think about the evolution of our real universe, we'll talk about this in great detail later, but basically the universe began 13.7 billion years ago in a low entropy state and also a very simple state. It was homogeneous, it was smooth everywhere, and everything was densely packed. That was the universe. The far, far future of our universe is also very simple. Everything will scatter to the three winds, four winds, whatever it is. We'll have empty space once again. The early universe is simple, the late universe is simple. The early universe has low entropy, the late universe has high entropy. The middle universe that has medium entropy, that is on a journey from low entropy to high, is complex. It is today that we have galaxies and stars and planets and life on those planets. So the way to think about the relationship between complexity and entropy is that complexity depends on entropy. It relies on the fact that entropy is increasing. If you like, it is a side effect of the fact that entropy is increasing. So the people who worried about this question, how in the world can we get complex things like life in a world where the second law of thermodynamics says that everything is devolving toward a heat death where everything is smooth, needn't have worried. In fact, it's not despite the second law of thermodynamics that complexity can exist. It's because of the second law of thermodynamics that complexity can exist. So that's the right way to think about why there is life on Earth. It doesn't guarantee that there should be life on Earth. This way of thinking doesn't tell you whether there is life on Europa, one of the moons of Jupiter, or around some other planet, around some other star. But it tells you that the simple fact that entropy is increasing does not in any way make it surprising that we have complex structures like life. The fact that entropy is increasing is what makes life possible. You will often hear people say, well, it doesn't matter that there's a second law of thermodynamics to try to explain why there is life because life is an open system. If you think about the absolutely careful definition of the second law, it says that in a closed system, in an isolated system that is not interacting with the rest of the world, entropy always either goes up or remains constant. A living being is not a closed system by any stretch of the imagination. A living organism is constantly interacting with its environment. So, strictly speaking, the second law simply says nothing about any individual living being. You certainly can't say that the second law rules out the existence of a living organism. But we can say more than that. We can say that the second law allows for life to exist. So let's think about how this actually works out. One of the best ways of thinking about it was put forward by Erwin Schrödinger, the physicist who was a pioneer of quantum mechanics. Later in life, after he had helped develop quantum mechanics, he moved to Ireland and became fascinated by biology. Schrödinger wrote a tiny little book based on some lectures that he had given called What is Life? And it's a very interesting book to read. It predates our discovery of DNA, but Schrödinger's little book was actually inspirational for Francis Crick, one of the men who discovered DNA. It helped Crick decide to leave physics and go into molecular biology and understand the way that DNA actually works. Schrödinger was thinking about biology like a physicist would. So he was trying to understand how living organisms can persist, how they work. And he came up with a great definition of what life is. It's not the final definition by any means. It's not even very rigorous, but it gets you on the right track. Schrödinger says that life is something that goes on doing something much longer than you would expect it to. Now, what is that supposed to mean? What do we mean how long we expect it to? How long do we expect something to go on doing something? What Schrödinger has in mind is, imagine once again our favorite example of a glass of water and we put an ice cube in it. Over the course of a few minutes, the ice cube melts. The water in the ice cube comes to equilibrium with the water around it. Even if it's not a water ice cube, there are these plastic ice cubes that are made of a different substance, but you put them in your refrigerator, put them in the water, and it will cool it off, but it will still equilibrate. The temperature of a plastic ice cube comes to be the same as the temperature of its environment, just like Clausius would have said, and then once you reach equilibrium, everything stops. On the other hand, imagine putting a goldfish in a glass of water. The goldfish does not come to equilibrium with the water around it. It maintains its integrity, even though by mass, most of the goldfish is also water. If you give it food, if you feed it, what you're doing is allowing that goldfish to take advantage of energy in a low entropy form. Food is fuel. It can be used to do useful work. And then that goldfish can last a very long time. If you don't feed it, it will eventually die. If you feed it, the goldfish can last a long time. This is what Schrödinger had in mind. A living being, even in an environment, can put off the approach to thermal equilibrium for a long time. So what is going on? What's going on is actually very similar to Maxwell's demon. Remember, we talked about this thought experiment from James Clerk Maxwell that tried to ask whether a little demon could maintain a low entropy situation without violating the second law of thermodynamics. So the demon sits on top of a box, and the demon starts the box in equilibrium, but by cleverly letting some molecules go one way and some molecules go the other way, the demon constructs a lower entropy situation in the box. And then by constantly keeping track of the molecules and updating his little record book, the demon can maintain that low entropy situation as long as he wants. So what's going on is the demon is making use of the fact that he lives in a low entropy world in order to keep his particular favorite box in a low entropy situation. By itself, the box would equilibrate. Both sides would come to the same temperature. But the demon, remember, increases the entropy of the universe by writing things down in his notebook and later erasing them. If the external world were already in equilibrium, the demon couldn't do that. You can't increase the entropy of a system that is in equilibrium. So the demon makes use of the fact that he lives in a low entropy world in order to maintain the complexity of his box, the difference between the temperature on one side and the temperature on the other side. That is a very general paradigm for thinking about how life persists, how Schrödinger says a living being lasts longer than it should. What he's saying is the complexity of a living being can last longer than you would expect it to. It does not come to thermal equilibrium Because there's plenty of room for the entropy to grow. Again, it's not just that the entropy is one value or another, but living things, complex organisms in general, can maintain their integrity by taking advantage of the fact that they're increasing the entropy of the rest of the world. Let's think about how this works in the real-world example of the biosphere here on Earth. We live here on Earth. We have the sun in the sky. That's clearly a source of energy for living beings here on Earth. It's almost all the energy that we make use of. Now, that's a typical way of talking about how life on Earth makes use of the sun. We get radiation from the sun. That gives us energy. We use the energy to do things. But of course, if you've sat through all these lectures, you know better than that. It's not the energy that we get from the sun that matters. It's the fact that the energy is in a low entropy form. In particular, the sun is a hot spot in an otherwise cold sky. If the whole sky were the temperature of the sun, we would get a lot more energy than we get now. However, we would come to equilibrium with that sky very, very quickly. We would become the temperature of the sun, we would equilibrate, and all life would cease. Even though we have a lot more energy, we can't be alive because we would be quickly brought to thermal equilibrium. Likewise, if the whole night sky were dark, if the whole day and night sky were the temperature of the real night sky, completely dark and cold, the Earth would very quickly come to the temperature of the night sky, would equilibrate, and life would cease. The reason there can be life is because the whole sky is not at the same temperature, and we do not quickly come to thermal equilibrium. What actually happens is that the energy we get from the sun is in a low entropy form. We give back to the universe just as much energy as we get from the sun. We get radiation during the day, we give it back. We radiate into the universe almost exactly the same amount of energy that we get. It's not exactly the same because of global warming, but to a very, very good approximation, the energy we get equals the energy we give back. So you ask, what is it that drives life on Earth if we don't get a net gain of energy from the sun? The answer is the energy we get from the sun is in the form of visible light. We can see it. That's most of the energy, most of the photons that we get from the sun. But then we process that energy. For every 1 photon of visible light we get from the sun, we give back 20 photons to the universe, each with about 1/20th of the energy. So what that means is that we radiate infrared light to the universe. And what that means is that we have increased the entropy by a factor of 20. Our ecosystem, our biosphere, is very, very far from a closed system. Energy comes in, we increase its entropy by multiplying it by 20, and then we give it back to the universe in the form of infrared radiation. You can actually do the calculation to see by how much the entropy of the biosphere has increased. The entropy of the universe has increased, for that matter, by the function of the Earth. So people sometimes wonder, as I've mentioned, how it can be that there's all this complex life here on Earth just because entropy keeps increasing. Why would you have complexity increase in the biosphere? Well, you can ask, can you account for the increase of entropy quantitatively when you compare the amount that we've increased the entropy of the universe through our infrared radiation to the amount that we've decreased the entropy of the universe by inventing life here on Earth? One way of doing that is to imagine that the biosphere, all of the mass in living things here on Earth, was once in its highest entropy form and is now in its lowest entropy form. That's obviously not right. It's somewhere in between on both ends, but it's a conservative estimate, right? The maximum amount by which life on Earth could have gone down in entropy is what you would get if you imagined it started at the highest possible entropy and ended with the lowest possible entropy. So the biosphere has about 10 to the 15 kilograms, and we know the surface temperature of the Earth. That means we can calculate what the entropy of the biosphere would have been if it were in thermal equilibrium. It never was in thermal equilibrium precisely, but that's the maximum entropy it could have. You work out the numbers, it's about 10 to the 44. So to go from the maximum entropy that the biosphere could have to the minimum entropy it could have, all you need to do is decrease the entropy of the biosphere by 10 to the 44. In order for that to not violate the second law of thermodynamics, as the entropy of the biosphere goes down, as random muck organizes itself into living organisms, the entropy of the universe needs to go up by more than 10 to the 44. So you can again do the calculation. You can say, at what rate does the Earth increase the entropy of the universe by taking visible light from the sun and radiating it back into the universe as infrared radiation? The answer is it takes about 1 year for the Earth to increase the entropy of the universe by 10 to the 44. In other words, turning it around, the Earth has increased the entropy of the universe over the course of the history of life by 4 billion times the amount that the biosphere has decreased the entropy of the universe. The second law is in very good shape. The origin of life on Earth and the existence of life on Earth do not violate the second law. It's completely compatible with what we know about the increase of entropy. Life on Earth is a tiny little perturbation compared to the huge amount by which we have increased the entropy of the universe. Now, there's one thing sort of as an aside that I want to get clear here. The process of evolution, the going from simple single-celled organisms at early times to the very complex, organized biosphere we have today, is not teleological. It is not right to think of evolution as working toward the goal of greater complexity. Evolution doesn't work toward any goal at all. The way that evolution works is that individual species and the genes and the DNA they carry flourish or don't in whatever environment they're in, and when they flourish, they reproduce and create more of themselves. Sometimes to flourish means to be complex, to have a complex brain or very accurate vision, sometimes not. Very often in the history of evolution, you will see species that have lost abilities that they used to have. A mammal climbs underground and it loses over the course of generations the ability to see. It's not that evolution wants life to be more complex. It's that there are many ways to be complex. Sometimes those ways are very, very useful, therefore life adopts them. But the underlying laws, the underlying processes don't have any goal in mind. They just take advantage of whatever circumstances they're in. The reason why I want to emphasize that is because I'm about to tell you a story that suggests that in some sense, life is taking advantage of a function that complexity has. Complexity does actually help us do certain things, and that's one explanation for why there is life at all. Not just how life has evolved over the course of the last several billion years, but why life appeared. The science of the origin of life is very, very undeveloped. We don't know how life starts, even here on Earth, much less how life might start in some very, very different environment. But as physicists, we can choose not to sweat the details about the actual geology and atmospheric science of the Earth at early times, and ask, on the basis of physics, does it make sense to us that life started at all? Fortunately, the answer is yes. Remember, we argued that complexity is compatible with the second law. In fact, it is parasitic on the growth of entropy. When entropy increases, complexity will often follow until entropy starts increasing close to equilibrium, and then the complexity is going to have to go away. So think about the early Earth. The Earth, soon after it formed, it didn't take that long, I mean, maybe hundreds of millions of years, but still not billions and billions of years, for life to appear on the young Earth. Again, we don't know how it started, but there are two schools of thought about different ways in which it could have started. One school of thought is called replication first. This is the idea that the most important feature of life is that a living being can reproduce itself, not just continue to exist or create one other organism, but create more than one other organism like itself. To do that, you need some molecule that conveys information. So biologists talk about an RNA world, where RNA molecules, which are the partners of DNA molecules, the RNA molecules could have come first. They could have stored genetic information and reproduced themselves. And only later do these little reproducing molecules form around themselves cells and make the first single-celled organisms, and then those organisms could reproduce and evolve and come to the marvelous complexity of life that we see today. That's one school of thought. The competing school of thought, which is a little bit less popular, is called metabolism first. It's a little bit less popular, but it's still a respectable way of thinking. Metabolism first says that it's not the information and the replication that came first. It's the use of complex chemical reactions to take advantage of the low entropy environment in the early Earth that came first. So one way of thinking about it is hardware before software. The software is the information in the RNA. The hardware is the actual cell and its machines inside that make use of the fuel that it can get from its environment. From one point of view, it makes sense to have hardware without software. It seems difficult to have software without hardware. One of the advocates of this point of view is a scientist named Mike Russell, who says, I could take the computer out of my Prius and it would still go, but if I take the engine out of my Prius, it doesn't do anything at all. So the metabolism first school of thought says that the first life was just a chemical reaction. It was just like fire. It was taking advantage of the fuel around it to get going. In particular, we can think about what the chemistry was like on the early Earth in the early days. Again, we don't know very, very well. We have theories and we have data and we're trying to do our best. There's a very good understanding that we think is accurate that says that the early Earth had an atmosphere that was rich in hydrogen, 2 hydrogen atoms making a molecule, and carbon dioxide, 1 carbon atom and 2 oxygen atoms. The interesting thing about such an atmosphere full of hydrogen and carbon dioxide is that it is low entropy. With those exact molecules, hydrogen, carbon, and oxygen, there's a much higher entropy configuration, namely methane and water. Methane is 1 carbon and 4 hydrogens. Water is 1 oxygen and 2 hydrogens. So to increase the entropy, which is what the world wants to do, you would convert that hydrogen and carbon dioxide into methane and water. The problem is that to get there, to go from the original situation of low entropy to the situation of higher entropy, there is no one simple reaction. To get there, you need to go through formaldehyde, which is 1 carbon, 1 oxygen, and 2 hydrogens, and that requires a decrease in entropy. So the first step on this chain of reactions that wants to happen is very difficult to get started. It doesn't just go. It's not like a piece of wood where you can spark it and it will go to flame. You need a complicated series of many reactions to get the entropy to increase. So the hypothesis is that those complicated series of reactions started in certain very specific geological formations. There were little membranes that separated mostly positively charged atoms from negatively charged atoms. This differentiated structure allowed a series of complicated reactions to start that allowed the low entropy configuration to increase to the high entropy configuration. If this story is true, the reason why life started is that it was trying to increase the entropy of the primitive atmosphere on Earth. When I use the word trying, don't take me too seriously. There was no goal in mind, but there are many ways to rearrange the fundamental structure of the things in the Earth's early atmosphere, which would have had a higher entropy. But to get there, you needed something complicated like life. Given enough time, that complication would happen. And here we are as a consequence of it. It's very interesting to contemplate the thought that life is not only compatible with, but actually an outgrowth of the second law of thermodynamics and the arrow of time. To remind you of our goal here, just remember that we're trying to understand the mysteries of time, in particular the mystery of the arrow of time, why the past is different from the future. And we've put together a story that is hopefully pretty convincing. There's good news and bad news in this story. The good news is we understand why entropy increases toward the future. Ludwig Boltzmann explained that entropy is really a way of counting how many different ways you can rearrange the microscopic constituents of a system, which keep it macroscopically looking the same. So as you go toward the future, entropy goes up just because there are more ways to be high entropy than to be low entropy. The bad news is we don't understand, just on the basis of Boltzmann's counting, why the entropy was lower in the past. To make that come true, we need to introduce a new ingredient, the past hypothesis, We call it a hypothesis, but it's actually just a true fact. It's something that must be correct about our universe. It certainly fits all of the data. It's the idea that at some time in the observable past, we think now 13.7 billion years ago, the universe started in a very low entropy state. That's the past hypothesis. Once you do that, you explain both why entropy was lower in the past and why entropy will be higher in the future. There's another bit of good news, which we tried to argue for in the last lecture, which is that if you believe the story about entropy increasing, the second law of thermodynamics, you can argue that that one fact underlies all of the differences between the past and the future. The fact that you remember the past and not the future, the fact that you can make choices and affect the future, but not the past. So the whole story, we like to think, fits together. But there is an obvious thing that we would like to do. There is that past hypothesis that we just put in there as an extra ingredient. It's a little bit ugly compared to the rest of the story. Boltzmann's story of what entropy is and why entropy tends to increase is very, very compelling. Once you believe in atoms, once you understand what Boltzmann is trying to do, it just all makes sense. Of course, entropy goes up. There are more ways to be high entropy than to be low entropy. But then to make the past work, you have to add this extra ugly ingredient, the past hypothesis. This has been something that people have been arguing about from the moment that Boltzmann came up with the idea to the present day. What does the past hypothesis really mean? Where does it come from? There are different attitudes you can take toward that question. One attitude absolutely is, maybe it is just like that. Maybe just there is no bigger explanation for why the early universe had a low entropy. Maybe it's a brute fact. That is not something we're going to disprove. It is absolutely on the table, but is clearly unsatisfying. There's something about the low entropy past of the universe that doesn't seem natural to us. It doesn't seem that if you were just to start a universe, it would be so special in that way. Remember, if low entropy means there are very few arrangements of a system that look that way, what we're saying is that the very earliest moments of the universe could have been many, many configurations and were a very, very specific kind. That's what the Big Bang was like. That seems to be a feature that cries out for an explanation. So our bigger goal is going to be to try to come up with a theory that explains the past hypothesis, that says, yes, that was a natural outcome. It wasn't just arbitrary. It couldn't have been any other way. We should not be surprised that our early universe had a low entropy. Now, we are not going to succeed at doing that once and for all. We're going to discuss different possibilities. One of these possibilities might end up being correct, but the truth is that we currently don't know why the early universe had such a low entropy. It's one of the research questions that modern cosmologists are trying to figure out. In this lecture, we're going to tease you a little bit. We're going to talk about a very particular idea that didn't work out, an idea that goes all the way back to Boltzmann himself, and maybe even a little bit earlier than that, trying to explain why the early universe had such a low entropy. The basis for this explanation, or at least an inspiration for thinking about it, can be thought of as coming from a quote from Carl Sagan. Sagan once said, "In order to make an apple pie, you must first invent the universe." Now, I think what he was talking about was that the fact that to make an apple pie, it's not only true that the apple pie sits in the universe, it's also true that the apple pie came from apples and flour and so forth, which means that to make that apple pie, you needed apple orchards, you needed wheat fields. That means you needed a biosphere and an Earth. You needed a sun, and you needed the whole galaxy, and you needed the whole universe. Sagan is simply pointing out that every little piece of our universe inherits what it is from the larger story in which it was invented. However, a modern cosmologist would say that's not necessarily so. We can invent models of the universe in which the easiest way to make an apple pie is to just make the apple pie out of the surrounding primordial chaos, not to make a universe at all, not to make a solar system, a galaxy, much less the 100 billion galaxies we see in our current universe. And that's the essence of the scenario that was proposed by Boltzmann to try to understand the past hypothesis. Another way of motivating this idea was to go back to Friedrich Nietzsche in the 1880s. Now, Nietzsche was not a physicist, But it's interesting that he was writing in the 1880s when there were debates going back and forth among the physicists and the mathematicians and the chemists about what is entropy, why is there an arrow of time, and so forth. Nietzsche asked us to imagine a thought experiment, and his thought experiment was to say, imagine that a demon comes down. They loved talking about the demons in the 19th century. The demon comes down and tells you that you live in a world which is not just the only occurrence of this world, but that the world will repeat itself over and over and over again, that the life you're leading now, you will lead again, and then again and again, and you have led it in the past an infinite number of times. Now, the reason why Nietzsche wants you to think about this thought experiment is not for physics reasons. He's not trying to demonstrate something about the nature of time. He's thinking about morality. He wants you to say, I would like to live a life that I would be happy to live an infinite number of times. That's a moral piece of guidance. The question is that a realistic cosmology? Does the demon have a chance of being right? Is it plausible to imagine that the universe just repeats itself many, many, many times? Well, it wasn't long after Nietzsche did his little story that a mathematician and physicist, Henri Poincaré, proved a theorem that we now call the recurrence theorem. What the recurrence theorem says is that if you have a bunch of particles, you have some system for which the particles can only take on a finite number of states, or if they can only move within a bounded region. What he was thinking of was the planets moving around the sun in the solar system. They don't fly off to infinity. The planets just orbit around. And Poincaré proved that if that happens, if that's your system, it's somehow bounded, it can't roll off to infinity, and it lasts forever, then whatever state you find that system in at one point in time will repeat itself an infinite number of times toward the future. That's the Poincaré recurrence theorem. One interesting thing is that Poincaré didn't try to prove this theorem. He stumbled on it in the attempt to prove something else. He was trying to understand that the solar system was stable. He wanted to prove that the solar system would not go flying off to infinity. And he, in fact, did prove it. He submitted a paper to the journal. He won a prize for doing this wonderful proof. And when they were proofreading his paper, when they were checking every step, Poincaré realized he had made a mistake. He had made an assumption which isn't always true. He went back to fix the mistake, and he ended up inventing what we now call chaos theory. Poincaré ended up showing that if you include the gravitational effect of the planets on each other, not just the planets pulled by the sun, but the planets pushing on each other, it's very likely that one of the planets in the solar system will zoom off to infinity. It's very hard to control things when they can go infinitely far away. But in the process of doing that, he proved that if they can't go infinitely far away, then you are doomed to recurrence. Things that happen will happen again. As close as you are to any one particular configuration, you'll come that close again an infinite number of times. This doesn't sound very surprising to us, right? If you have a finite number of things you can do, and you have an infinite amount of time to do them, then yes, you will keep doing the same thing over and over again. But when you think about the implications of these ideas for the real world, it becomes a little bit disconcerting. For example, we put a glass on the table. It has warm water in it. We put an ice cube in it. The ice cube will melt. Entropy will increase. But if we leave that glass of water there forever, for an arbitrarily long period of time, Poincaré's recurrence theorem says that that ice cube will reform, that the random motions of the molecules in the glass of water will convert themselves back into an ice cube. And then it will melt again, and then it will reform and melt an infinite number of times. This is very, very surprising to our intuition, which says that entropy increases. Poincaré is saying that if you wait long enough, the entropy will spontaneously decrease. Now, we already talked a little bit about the fact that entropy is allowed to decrease in Boltzmann's way of thinking about it. If you have a box of gas or a glass of water that is in equilibrium, it will have fluctuations up and down, and occasionally, just through the random motions of the molecules, you will move into a lower entropy configuration. But Poincaré's theorem is stronger than that. He doesn't say there is some small probability that this will happen. He says the probability is 1. It will certainly eventually happen. All you have to do is wait long enough. That's a little bit more shaking to our conviction that entropy is supposed to increase. But fundamentally, it's simply a consequence of reversibility. If you can go there, you can come back. If you wait long enough, you will come back. This theorem of Poincaré's was turned against Boltzmann by a man named Ernst Zermelo. We now know Zermelo in the mathematics community as one of the founders of set theory, but at the time, in the late 19th century, he was a young guy. He was basically what we would now call a postdoc. He had just gotten his PhD. He had studied under Max Planck, the famous German physicist, and he was a mathematically inclined guy, so he seized on Poincaré's recurrence theorem to argue against Boltzmann's understanding of entropy. And Zermelo's argument was very, very easy. He says, if motion is periodic, if the motion of the molecules in a box of gas or a glass of water does something and then will do it again an infinite number of times, anything that goes up will eventually go back down and then go up again. So Zermelo says, how can you possibly prove that entropy will increase if I can prove that the entropy will eventually decrease and then increase again and going on forever? That doesn't seem to be the world in which we live. This is now called Zermelo's recurrence objection. It's a close cousin of Loschmidt's reversibility objection. Loschmidt said, yes, there are trajectories where entropy is increasing, but there's an equal number where they are decreasing. How do you say that one is more probable than the other? In some sense, Zermelo's objection is a little bit stronger. He says, if entropy is increasing now, Poincaré's theorem says it is certain that sometime in the future it will decrease. That's saying that you haven't shown at all that there is a tendency for entropy to go one way or the other. You haven't really established what we would truly call an arrow of time at all. Well, there is a simple answer to Zermelo's objection. The question is whether or not you are willing to accept it. The simple answer is that in the visible world, in the observable part of reality, the entropy was in fact very low in the past, in the observable past. That is what we would now call the past hypothesis. The point is that there's a period of time in the universe that we have access to. We now know it's about 13.7 billion years. But that period of time is much, much shorter than the timescale over which anything interesting would recur, according to Poincaré's recurrence theorem. If you have a glass of water with, say, 10 to the 25 molecules in it, the amount of time it would take that ice cube to reform is something like 10 to the 10 to the 25 years, or seconds. It doesn't really matter what units you use. 10 to the 10 to the 25 is such an enormously mind-bogglingly large number that it doesn't matter. So Boltzmann and other people said, who cares about the recurrence theorem? It's something that is so far in the future, I don't need to worry about it. Maybe it would happen, but maybe the laws of physics don't let the universe last that long. All we have to explain is the recent past. So he actually focused his mind on what we now call the problem of the past hypothesis. What Boltzmann had, and other people didn't at the time, was this firm conviction that entropy is fundamentally statistical, that it doesn't need to go up. What he didn't have, that we now have, is any idea about quantum mechanics or general relativity or the Big Bang. Boltzmann worked in a world that was governed by Newtonian physics. So he thought of space and time as absolute and also eternal. They were there forever. So when Boltzmann had to ask himself the question, what should the universe look like? What is a natural configuration for the universe? He took a Newtonian space-time, space and time are there forever, and he filled it with particles. So there's an infinitely big space, there are infinitely many particles scattered throughout the universe, and most of the time they are in thermal equilibrium. That is what the particles would like to do. After all, they've been there forever. In Newtonian physics, time does not begin or end. You have an infinitely long time. The particles would come to thermal equilibrium. But Boltzmann also knows that thermal equilibrium doesn't last forever. It fluctuates. Most of the time, any particular set of particles remains at the high entropy equilibrium state, but there will be occasional fluctuations to lower entropy states. Now, these are very rare, as we've discussed, but they are inevitable. In fact, arbitrarily large fluctuations to lower entropy configurations will eventually happen. If you wait the air in this room long enough, it will go all the way into one tiny little corner and then come back. It will take a very long time, but in this Newtonian eternal universe, you have forever to wait. At this point, Boltzmann makes a very unusual move for the physicists of his time. This is something that these days we would take very straightforwardly, but in the 19th century, no one made this argument, namely the anthropic principle. The idea that if you have a big universe, if you have a universe where there are many different conditions in many different places, then we human beings don't get to see typical parts of the universe. If typical parts of the universe are inhospitable to the existence of life, then we are going to find ourselves only in those regions that are hospitable. So the anthropic principle says our job is not to construct a theory of cosmology where the entire universe is hospitable to us. Our job is to construct a theory where those regions that are hospitable look like the universe in which we actually live. So Boltzmann's strategy was to take this eternal Newtonian universe with fluctuating entropy all over the place and apply to it the anthropic principle. Now, the anthropic principle, even today, has a somewhat shady reputation. It can seem empty. You can phrase it as simply saying, we live where we can live. And that is obviously true, but it's irrelevant unless we live in a universe where we can live some places and we can't live others. For example, here in the solar system, there's a lot more volume in the space in between the planets than on the surface of any of the one planets. So you might wonder, should we be surprised that life arose on the surface of the Earth rather than in between the planets? But that's a dumb thing to wonder. No one wonders that. Life would just not survive very long in the interplanetary space of the solar system. We live in the place in the solar system that is hospitable to life, so we're not surprised to find ourselves there. There are also arguments against the anthropic principle, saying that it is a move of desperation or that somehow it's spiritual and spooky and it implies that the universe was designed for us. None of that is necessarily true. I don't want to say that the anthropic principle is the right way to think about the universe or not, but it is certainly an important part of cosmology if we live in a universe that is big enough to have very different regions, to have regions that look like the universe we see in some places, but other regions that look completely different. If that's our universe, then the anthropic principle tells us why we live here rather than somewhere else. So Boltzmann knew about the fact we discovered previously that life itself depends on entropy being low and increasing. So he said that in this large universe of his, most of which is in thermal equilibrium, most of the places of that universe cannot support life. If the universe is in equilibrium, life cannot exist there. But there will be fluctuations. There will be regions of space in which the molecules just randomly find themselves in a low entropy configuration, and then they bounce back. If you wait long enough, there will be large fluctuations. If you wait really, really, really long, there will be a fluctuation large enough to form an entire galaxy. Now remember, in the late 19th century, they didn't know about the Big Bang, about different galaxies. They thought that our galaxy was the whole universe, what we now call the Milky Way. They thought there might be millions of stars in it. We now know there are 100 billion or more stars in the Milky Way. But what Boltzmann suggested was that there could be random, smoothly distributed gas and dust in the universe, but if you wait for eternity, it will simply happen through the random motions of that stuff that you collect in something that looks like our galaxy. Outside that region, it will not look like our galaxy, but here it will. There's essentially what we would now call a multiverse. There are different regions in this infinitely big and eternally persisting universe that look hospitable to life and many other regions that don't. So what Boltzmann is suggesting is, maybe our universe is just something that happens from time to time. Maybe our galaxy just is randomly formed on occasion and then dissolves back. Maybe that's how we find ourselves living in this eternal, mostly equilibrium Newtonian universe. Now it's interesting to think about the fact that in Boltzmann's scenario, the entropy is not increasing forever. It's like a box of gas that is usually in thermal equilibrium. The entropy can decrease locally because of some fluctuation, and then it will increase again. The overall evolution of the entropy is actually symmetric. It goes up and down equally often. So you might worry, isn't Boltzmann going to predict that entropy increases just as much as it decreases? But that's not the right way to think about it. The point is that we define the past to be the direction of time in which the entropy was lower. As we argued, the direction of time in which the entropy was lower is the direction we remember. The region of time in which the entropy is higher is the direction to which we can make choices. It doesn't matter what coordinate you use, whether you have your clock running clockwise or counterclockwise. What matters is we would always define the past to be the direction in which the entropy was lower. So if entropy goes up and goes down and then comes up again, there are two possible places you can live, during while it's going down or during while it's going up. Both sets of people would define the past as the minimum point of the entropy. So the scenario is potentially compatible with the data. You can argue that Boltzmann was not the first one to think about this scenario. You can go all the way back to 50 BC to the ancient Roman poet Lucretius. Lucretius, like Boltzmann, was a believer in atoms. He was a follower of Epicurus and Democritus, the ancient Greek atomists, and he wrote a poem called On the Nature of Things, where he tried to explain how the universe works in terms of the atomic theory. But he was faced with the same problem that Boltzmann was faced with. He didn't know about entropy or so forth, but he knew that we lived in a universe that was complex and orderly, and there was a whole bunch of structure in our universe. It did not look like the mindless interaction of atoms. So Lucretius proposed that if you wait long enough, those mindless interactions of atoms would eventually arrange themselves in the form of a universe. It's exactly the same scenario that Boltzmann had, he just didn't have the math. But it's a compelling idea that the random evolution of chaos ultimately creates the universe around us. I want to say that it's a good idea because it's a well-formed scientific hypothesis, by which I mean it makes predictions. Sadly, those predictions can be tested and the hypothesis completely fails. So don't get me wrong, I'm talking about this scenario in detail, but the final verdict on the story is that it is false. This was pointed out by Sir Arthur Eddington, an astrophysicist in England, in the 1930s, because he pointed out that unlike Lucretius, Boltzmann has equations. Boltzmann can talk about the exact likelihood of different fluctuations in entropy. And in particular, Boltzmann should know that small fluctuations in entropy are much, much more likely than large fluctuations. Basically, any fluctuation in entropy is unlikely, and a large fluctuation is like many small fluctuations right on top of each other. So you're much more likely to get a tiny fluctuation from thermal equilibrium to just outside thermal equilibrium than you are to get a large fluctuation from thermal equilibrium into a whole giant galaxy with millions or billions of stars. So Boltzmann's scenario makes a prediction, namely, you tell me what you want to make. You want to make a planet or a galaxy or a star or whatever. You want to make it in this universe that lasts forever, just like Newton said, and has all these fluctuations in it. Then Boltzmann's scenario predicts that you make that thing you want to make via the tiniest possible fluctuation that could make it. So for example, if you want to make the galaxy, then you can make the galaxy, that's fine, it is possible. But if you want to make a star with some planets, you would make the star and the planets, you would not make the millions or billions of other stars. You wouldn't need to make the entire galaxy. If you wanted to make just the Earth, you wouldn't need to make the other planets in the solar system. If you wanted to make a person, you wouldn't need to make the Earth. You could just fluctuate the random molecules around you into the shape of a person. And you might say that sounds very unlikely, and it is very unlikely, but it's much more likely than fluctuating into the entire Earth with many, many people on it. So Carl Sagan was wrong. If you are in this Boltzmannian scenario, where you have an eternal Newtonian universe with random fluctuations, the easiest way to make an apple pie is just to fluctuate the apple pie. It's much harder to fluctuate the galaxy, and then the sun, and then the Earth, and then the apple orchards, etc., just so you can get that pie. In Boltzmann's universe, the pie will appear all by itself spontaneously out of the chaotic surrounding universe. So what does this have to say about you and the past hypothesis? Well, you think that you have memories, that you remember your 10th birthday, you remember purchasing these lectures and so forth. But in the Boltzmann-Lucretius scenario, in this idea, where the universe lasts forever and things like you and me fluctuate into existence, it is immensely more probable that you fluctuated into existence with those memories, randomly out of the surrounding chaos, rather than actually having those memories happen. The actual appearance of you with the photograph of John Lennon is much more likely to randomly fluctuate into existence than to represent a real event in the past. In fact, there's no reason in this scenario for you to believe any of the memories that you think you have. Another way of putting it is that you don't even need you. That is to say, if you consider this scenario and ask, what are the most likely ways for conscious observers to arise in this universe? If you think that a conscious observer, a thinking person, is defined by their brain and their central nervous system, then you don't need to fluctuate a whole body into existence. You can just fluctuate a brain with whatever memories or thoughts or impressions that you want it to have. It will always be easier to just fluctuate that brain than to fluctuate a whole universe and have that brain learn in the conventional way. This scenario, or this horrible implication of this scenario, are called Boltzmann brains. The idea is that if we live in chaos, if the universe simply fluctuates, almost all observers in that universe would be disembodied brains. We are not disembodied brains, therefore we do not live in that universe. We need to do better than that. But when faced with this argument, you should be asking yourself, maybe you are asking yourself, how do I know that I am not a Boltzmann brain? How do I know that I did not fluctuate into existence yesterday? And there are two arguments against that possibility. There's sort of a sloppy argument that convinces most people, and there's a better argument that it really is completely convincing but might leave a sour taste in your mouth. The simple and short argument is simply that if we lived in a universe that had randomly fluctuated into existence, let's say that you believe you and the room that you're in right now randomly fluctuated into existence, then the Boltzmann scenario predicts that as soon as you leave that room, it should be thermal equilibrium. If you believe that you are in some city and outside of your current location, the city exists, Boltzmann's scenario says the impression of that city is much easier to put into your brain by itself than actually creating the city. So once you leave where you are, there shouldn't be any city there. The problem is that even when you do leave where you are and you see a city, it's still much easier to fluctuate that person into existence than to fluctuate the rest of the universe. The real reason why Boltzmann wasn't right is something called cognitive instability. The real problem with Boltzmann's scenario is that even if you do fluctuate exactly like you exist now into existence randomly, all of your impressions about how physics works, how math works, how logic works, how philosophy works, they are most likely to also have fluctuated randomly into your brain. So even if this scenario is true, you can never have any rational justification for believing that this scenario is true. You can never have any reason to believe the thoughts you think you have if you live in this universe. That's why it's called cognitive instability. Once you believe it, you realize you have no rational reason for believing it. So even if we do live in the universe described by Boltzmann and Lucretius and their friends, we have no reason for thinking it. We need to do better. So let's emphasize that's what we're here to do better. It's interesting to think that here was a fully sensible, well-developed theory of physics that predicted that we randomly fluctuated into existence. But that theory made predictions, and the predictions are not right. We're not advocating this way of thinking of it. We're saying that that was worth considering and we need to move on. This is not just a historical curiosity. It turns out that many of our best theories of cosmology today, as we will talk about, make the prediction that the overwhelming majority of conscious observers in those cosmologies are Boltzmann brains. Or, if you like, the overwhelming majority of situations like we find ourselves in right now, people like you and me with the memories we think we have randomly fluctuated into existence. We don't want that to be true. So one of the biggest challenges for modern cosmologies that try to account for the past hypothesis, is to make our impressions of the past be reliable, to make sure that if you and I exist, if apple pies exist, it's because there were universes in which we were embedded that gave rise to us, not that we just fluctuated into being here. By now we understand why there is an arrow of time. Given Boltzmann's understanding of entropy, there are more ways for entropy to be increased toward the future, and given the past hypothesis, there's a reason to believe that entropy was smaller in the past. Now, admittedly, the past hypothesis is just an extra hypothesis tacked on that says the entropy was small at what we would call the Big Bang 13.7 billion years ago. But it is just one extra added ingredient to the theory. Once we assume that 13.7 billion years ago the entropy was very low, the entropy has been increasing ever since. It's nowhere near as high as it can get. It would take a lot longer than 13.7 billion years for the universe to go all the way to thermal equilibrium. So we live in the aftermath of that low entropy beginning. That is why entropy has been increasing ever since the universe started. However, you remember that there is more than one version of the arrow of time. Sometimes when we're talking about the arrow of time, we use examples like melting ice cubes in a glass of water, or scent of a perfume spreading through the room, or mixing cream into coffee. But other times when we talk about the arrow of time, we use examples like, I can remember yesterday, I cannot remember tomorrow. I can make a choice about what happens tomorrow, but I cannot make a choice about what I had done yesterday. So what about these other examples of the arrow of time? The claim that we made earlier on was that they all reduce to what we call the thermodynamic arrow of time, the fact that entropy is increasing. So this is the lecture in which we try to justify that incredibly grandiose claim. We try to connect the human aspects of the arrow of time to the physical aspects of entropy increasing. And we should admit from the start, it can be a little bit disconcerting. It's a little bit spooky and alien to us to take features of human life that we think of as absolutely intrinsic and necessary and try to explain them in terms of laws of physics that are basically based on statistics. We will say a lot of things that sound outlandish, but that is what happens when you try to reconcile the way we go through our everyday lives with what physicists have learned about how nature works at a deep level. Remember that Newtonian physics, as interpreted by Laplace, and as continues all the way through quantum mechanics and more modern versions of physics, supports the idea of eternalism, or at least the idea that there's nothing special about the present moment. We have the moment we call now, but if you believe that there are laws of physics, they connect the moment we call now to the future and the past. At least if you believe either classical mechanics, which you shouldn't, or the many worlds interpretation of quantum mechanics, which at least has a chance of being right, if you knew everything about the present state of the universe, you could predict the past and future with perfect accuracy. And in any version of quantum mechanics, if you knew the present state of the universe exactly, you could at least predict the future in explicit probabilities. You would really know a lot about what could possibly happen. However, we don't know everything. We don't have perfect information about the present microstate of the universe. That's what we imagine Laplace's demon would have, but we certainly don't think that we have it. And it's not just sort of a technical problem. We will never have explicit knowledge of the complete microstate of the universe. So in the real world, when we talk about the future, when we talk about trying to predict what will happen in the future, we need to work in a world of incomplete information. And now that we have understood Boltzmann's ideas about entropy and macrostates constructed from microstates that look macroscopically the same, we can be very, very explicit about what it is we do know and what it is we don't know. What we know, what we talk as if we know, is the macrostate of the current universe. That is to say, we have some incomplete information about the present state. If we model the universe as a box of gas or a glass of water, we know things like the temperature and the density. We know some coarse-grained features of reality at the present time. We also know the past hypothesis. We know, we'll talk about this later, but the only sensible way to proceed in life is to go under the assumption that the past hypothesis is true. So we assume that both we have current information about the macroscopic configuration of stuff in the universe, And we also know that sometime in the past, 13.7 billion years ago, the entropy was much, much lower. It's the imbalance that we have extra information about the past versus the future that, of course, gives us the arrow of time. So in other words, the past hypothesis modifies Laplace's principle of indifference. Remember, the principle of indifference said that if you're in some macro state, you assume that we're equally likely to be in any of the microstates contained within that macro state. Given the macroscopic information, we could be in any of the microstates compatible with that macroscopic information. The past hypothesis says that's not quite right. Within our macro state, within all of the possible microstates that look like the universe currently looks, we are not equally likely to be in any of the microstates. We happen to be in one of the very specific microstates, which if you evolved it into the past, the entropy would decrease. That's a very tiny fraction of all the macrostates, all the microstates within our macrostate. Most of them have the property that entropy would increase if you followed them to the past. So we don't know which microstate that is, but it's one that had a much lower entropy in the past. That is the modification of Laplace's principle of indifference that is given to us by the past hypothesis. It picks out a tiny fraction of the microstates among all those within our macrostates. This information is incredibly useful to us as we go through our lives, even if it's so ingrained in how we think that we don't actually access it consciously. So let me give you a very, very specific example of how we use the knowledge of the past hypothesis every day, even though we don't put it in those terms. Imagine that you're walking down the street and you see on the sidewalk a broken egg. There's a lot of eggs in these lectures because they're great illustrations of how entropy works. So you're lucky enough that when you're walking down the sidewalk, there's a broken egg lying on the sidewalk. You see it splattered in some particular configuration. So what you're observing is the macro state. You're not observing every single molecule in the egg, its position and its momentum. You have some coarse-grained features. There's a bit of shell, there's a bit of egg yolk, etc. That is current information. That is information about the universe right now. That's what you have access to. Not complete information, some macroscopic, coarse-grained information about the current universe. What you want to know is what will happen in the future and what did happen in the past. You want to make predictions and retrodictions based on the information you have. So what can you say about the likely future of this broken egg lying on the sidewalk? The answer is you can't say the one true thing that will happen. You don't have enough information. Even if you have other macroscopic information about the world around you, the weather and the number of cars on the streets and so forth, it's still not enough information to say with 100% certainty what will happen to the egg. It's possible that it will just sit there for the next several days. Maybe it'll get really hot outside and the egg will fry right there on the sidewalk. Maybe somebody will come up and clean it up. Maybe the rain will come and wash the egg away. Maybe a dog or a cat will walk by and eat the egg. There's many different possibilities. All of them are compatible with the laws of physics and with our knowledge of the macrostate. It's even possible that the particular microstate of the egg will cause it to leap up and unbreak. It will Humpty Dumpty itself back into the form of an unbroken egg. That is not likely. It's an extremely small number of microstates that would behave that way, but there's some probability for that to happen even if it's really, really small. So what we see is the future of the egg is pretty open. There's a lot of things that are consistent with what we know. Now let's ask, what was the past of the egg? What was that egg doing 24 hours ago? Right now we see that it's broken on the sidewalk. It looks to us what we would describe as fairly fresh. So what we say is we don't know where the egg was 24 hours ago, but we're essentially certain that it was an unbroken egg. So there's a huge imbalance between how we talk about the future of the egg and how we talk about the past of the egg. In the future, many things are possible. Many futures are open to the egg. In the past, we think that there was an unbroken egg. The egg did not begin life messily scattered around the ground. It did not assemble itself randomly from molecules and atoms moving through the universe just to form a broken egg. There's an unbroken egg that broke. Why is it that we can be so much more specific about the past of the egg than the future of the egg? The answer is the past hypothesis. We don't look at the egg, look at its macrostate, and imagine that is just some random microstate and we don't know which one. We imagine that the microstate of the egg was one that came from a lower entropy past. And we know that the way that the real world creates broken eggs is first by making unbroken eggs. That is the likely evolution if you want to connect the past hypothesis, the low entropy past of the Big Bang, to the current situation where there's a broken egg lying on the sidewalk. That is where our asymmetry of epistemic access comes from. We are able to say more about the likely pasts, given our current information, than about the likely future because we know more about the past. We have a boundary condition in the past, at the Big Bang, of very low entropy. There is no boundary condition of the future. This way of thinking is alien to us. We think that the egg itself, the macroscopic information that we have looking at it, is all we need to talk about the past of the egg and the future of the egg. That's not true. We're cheating when we think that. If that were true, the set of things we could say about the egg's future would be the same as the set of things we could say about the egg's past. It's not just the knowledge of the state of the egg that lets us say it was unbroken. We pick out the possible trajectory of the history of the universe along which the egg was unbroken when we say that that's what we construct the past to be. That's based on the idea that there is a past hypothesis that fixes the universe to start in a state of very low entropy. So this is why there is a directionality to our knowledge of the universe. If we didn't know about that, we wouldn't be able to remember the past any more than we think we can remember the future. We tend to think that the past is fixed. The past is real. The past happened. It's not something that we can alter by our current actions. But there is a tension with that way of thinking and our belief that the underlying laws of physics are reversible. If you believe that the underlying laws of physics are Newtonian mechanics or quantum mechanics, they treat the past and future the same. So at the deep level of our best understanding of the laws of nature, there's no more reality or fixedness to the past than there is to the future. The real difference between the past and the future is not how real it is, not how settled it is, but how much we know about it. The difference between the past and future is that we can infer much more accurately about the past because we not only know the current macro state, we also know the past hypothesis. When it comes to predicting the future, all we have is the current macro state. There is no future hypothesis. So the point is that the past hypothesis illuminates the actual past. There is one particular past. There is one particular future. It's a matter of how well we know it. Because we have the past hypothesis, we know the past relatively well. Because there is no future hypothesis, the future seems up for grabs. Let's see a little bit more specifically how this works in the case of memory. Now, when I talk about memory, you tend to think of your actual memory in your actual brain. We'll talk about the brain in a later lecture. Right now, let's think about the abstract notion of memory, the idea that we have something in the present world that tells us something about the past world. We have some artifact, some record, some historical document, a photograph, for example, that tells us, that testifies to something that was really true in the past. We think we can have photographs or records of the past. We don't think we can have photographs or records of the future. Why is that? So let's look at a particular example. Let's imagine that you have a prized possession, a photograph that was taken back in the 1970s when you ran into John Lennon. And your friend was there with a camera. They took a picture of you shaking hands with John Lennon back in the 1970s. You've held on to this photograph as evidence of this moment that was a great moment in your life. You got to meet one of your favorite artists and musicians. So our question is, why is it true that photograph is evidence that you actually did meet and shake hands with John Lennon? We're not questioning that it is evidence. I agree that that photograph is good evidence. This is before Photoshop or anything like that. We're assuming you didn't doctor the photograph. But what right do we have to say that just because you have a photograph, that thing actually probably happened in the past? The image that is represented in the picture is something that is a true feature of the past. We wouldn't say that about the future. Let's talk about the photograph in the same language that we talked about the egg lying on the ground. What will happen to the photograph in the future? It's a document, it's a physical collection of atoms. The entropy of that document is going to gradually increase as time goes on. It's not a closed system perfectly, but it interacts gently with the environment. The entropy of the world is going up. The photograph will fade with time. It will get yellow, it will crumble, it might by accident get damaged, someone could spill coffee on it, it could get ripped. As the future goes forward, we can't predict the exact future state of the photograph, but we can see that it will gray and decay and eventually crumble away. 10,000 years from now, this photograph will not be around. Even in a couple of years, it might very well not be around if it's subject to a lot of disturbances. So what about the past of the photograph? Of course, we assume that the reason why there is a past image, why there is a photograph now, is because there was a real event and we took a picture of it. But what right do we have to treat the past of the photograph differently from the future of the photograph? The answer is the past hypothesis. Just like the most likely future of the photograph is to decay and have its molecules scattered throughout the universe, if it weren't for the past hypothesis, the most likely way for that photograph to come into existence would be by randomly becoming assembled out of molecules throughout the universe. Now, nobody thinks that this is what happened. I'm not trying to suggest that there's any reason to believe that your photograph is not good evidence of the actual event. I'm sure that it is. But we have to understand how the logic works. The usual way we would put the logic is not right. You would say two things. You would say, if I hadn't shaken hands with John Lennon, then it's very unlikely that I would have the photo. If I didn't actually shake hands, then of all the ways the molecules in the universe could have arranged themselves, it is very, very unlikely they would have arranged themselves into a picture like this. And furthermore, the second thing you would say is, if I did shake hands, it makes perfect sense that I have the photo. It's easy to take a picture, and that picture survives until today. So the way that you would justify using your photograph as evidence of the event is to say that if the event hadn't happened, the photograph wouldn't be likely, and if the event had happened, the photograph would be likely. All of these are true, none of them are relevant. That is not the question we're asking. The question we're asking is not, given the event or not given the event, how likely is the photograph? We're saying, given the photograph, how likely is the event? So given the photograph today, given some information about the macro state of the current world, what can you conclude about the past? And the answer is that without the past hypothesis, you could certainly not conclude that the event actually happened. To go from the photograph today to the actual event would generally lead you to sort of random collections of things happening, unless you could narrow down the trajectory of the universe by also including a low entropy boundary condition in the past. It is the past hypothesis that lets us believe our memories, that lets us take for granted that what we think is documentation of past events is actually reliable. Now, this way of thinking has deep repercussions. I mean, you can take that little part of the lecture and keep playing it over and thinking about it. Hopefully you'll come to understand that this is all a consequence of thinking about microstates, macrostates, and what is probable and improbable in the whole set of things the universe can do. It goes beyond simple memory and reconstruction. It also works toward the future. Toward the past, the helpfulness of the past hypothesis is it gives us a memory. But toward the future, we want to ask about cause and effect. Remember, we talked way back when about the fact that one aspect of the arrow of time is that causes precede effects. You say the window broke because the kids outside hit a baseball that went through the window. It would be bizarre and insane sounding to say the kids hit a baseball because the window was going to break and they had to break it somehow. That's not how cause and effect works. Causes happen first, effects happen next. But why is this true? Why do causes come first and then effects after? After all, if you believe that the laws of physics are reversible, I can explain any moment in the history of the universe in terms of any other moment. I can explain the kids playing baseball in terms of the broken window. I can say the state of the universe right now that has the window broken there, the kids scattering around, and everything that I know about the universe. If I knew the microstate, I could go backwards and say, ah yes, there are the kids out there. So why is it that in our phenomenological, everyday, real-life world, we think that causes happen first and events happened second? The reason is because given the broken window lying on the floor, we don't just think about every possible way for the molecules of glass to arrange themselves in the form of a broken window on the floor. We also imagine there was a past low entropy boundary condition. And given that past hypothesis, then the most likely way to get a broken window on the floor is to have an unbroken window in the window that something broke. What we call the cause of the broken window on the floor is the event that connects the unbroken window to the broken window. And it's the past event that is lower entropy that needs to be connected to the future event that tells us that the cause must have happened before the effect. It's ultimately because we know more about the past, because of the past hypothesis, that what we call causes always precede what we call effects. This way of thinking goes even deeper than that. Causes and effects, windows breaking, knocking over glasses of wine and so forth, that's fine. But the same logic applies to your human ability to make choices, what we call your free will. We think that you have the ability to decide where to go to have dinner tonight or tomorrow night. We don't think that you have the ability to decide what to have had for dinner last night. Again, the laws of physics treat the two events the same. There's the future, there's the past. They're connected by the laws of physics to the present. If you knew the microstates, there would be no difference between predicting the future and retrodicting the past. But we don't know that. We have less information. You will not be at this point surprised to learn that the reason we think we have free will about the future and not about the past is because of the past hypothesis. The past hypothesis fixes enough about what happens in the past that we don't think we can affect it. Because there is no future hypothesis, the set of things that are open to us in the future is very, very large. We conceptualize that large set of possibilities in terms of choices, in terms of free will. Now, philosophers argue up to the present day, and I'm sure into the future, about whether or not free will is real. That is not the argument that I'm trying to adjudicate right now. There are people called compatibilists who think that the laws of physics do govern everything, and nevertheless, we should talk in the language of free will because we don't know what will happen next. Even though the laws of physics tell us what will happen next, if we know the microstate, we don't know the microstate, and therefore the way to speak about the world is as if we are making choices. There are also libertarians in the philosophical sense, not the political sense. A philosophical libertarian is one who believes that our human choices overcome the laws of physics, that you are not determined by the laws of physics. I am not one of those because I'm a physicist, but I do believe that free will is the right way to talk. There's a third group who just say that free will is wrong. Free will does not exist because the laws of physics tell us what is going to happen in the future. Personally, even though I believe in the laws of physics, even though I believe that the future is determined at least probabilistically if we know the microstate of the universe, I don't mind talking about free will. I believe that it's okay to say we have free will because we don't know what the microstate is. We have the macrostate of the universe. When we use the language of free will, we're not describing the individual microstates of the universe. We're not talking about atoms and molecules. Just like when we talk about the melting of ice in a glass of water, we can talk about that in the language of the molecules of water, or we can talk about it in the thermodynamic language of fluids and temperatures and densities. We don't talk about it in both languages at once. You don't talk about the temperature of the water and the position and velocity of every molecule. You use one vocabulary or the other. Likewise, I would say that you can use the vocabulary of atoms and microstates to describe what you as a human being will do, and in that language there is no free will. There is only Schrödinger's equation and the laws of physics. But when we don't talk that language, which makes sense because we don't have all that information, we talk about human beings in a different vocabulary. And that vocabulary can include the possibility of making choices. Only, of course, making choices that are compatible with the laws of physics and our current macrostate, but there are many such choices. This is a very rich area of not only physics and philosophy, but also neuroscience. The study of when we actually do make choices is one that is a hot topic in people who are looking at the brain. Consciousness is not a clean thing. It's kind of a mess. It turns out you can make choices before you know that you are making choices. Nevertheless, for our purposes, what matters is knowing the macrostate leaves choices open to us. Just knowing what you can possibly know about the universe right now does not fix the future. Thinking this way reveals that determinism, the idea that starting with the current state of the universe and predicting what will happen in the future, has a bad reputation. People confuse determinism with what we might call fatalism. Fatalism is the idea that I am doomed to have something happen to me in the future. I am destined to struggle with poverty, or I am destined to be bored with my job, or I am destined to kiss a frog and turn him into a handsome prince. Something like that, some gross future boundary condition. That is what fatalism is. The determinism that lurks in the laws of physics is not like that, because the determinism of the laws of physics says, yes, if you knew the microstate, then you could say in the future you will be kissing frogs, working in a dead-end job, or winning the lottery, whatever it is that will happen. But you don't. You never will. You don't know the microstate. You can't. The determinism of the deep-down laws of physics cannot possibly affect how you personally think about the future. It can be determined, yet not fatalistic, exactly because there is no simple future boundary condition. That is not, as far as we know, how the laws of physics work. So the right way to think about determinism is contrasted with the usual way people think about predicting the future. When we think about predicting the future, we think about something like what happened in Macbeth, where Macbeth talked to the three crones stirring a cauldron that was bubbling, and the crones made a prediction he was going to die when the forest marched on him, etc., etc. Making a very specific prediction, whether it's Fabergé eggs or kissing frogs or losing your kingdom, that's what we think of when we think of determinism. The real world is more like a little annoying kid who says, I know exactly what is going to happen to you. And you say, well, tell me what is going to happen to me. And the little annoying kid says, I can't tell you. And then you say, all right, I'm going to ignore you. I'm just going to go on and do something. And then you do something, and the kid says, I knew that was going to happen. This is annoying, but it doesn't change how you live your life. The universe knows what is going to happen to you next. But you don't know. Nobody else knows. There's no realistic sense in which the determinism of the laws of physics affects how we should think about our future choices. So what it all means is that the arrow of time is not just a physics problem. It's not just a story about mixing different kinds of sand or heating up boxes of gas or anything like that. Everything about how we live our lives relies on the arrow of time in an absolutely intimate way. The way that we conceptualize the past versus the future, what we remember, what we predict, what we plan for, how we do things, make choices, affect the future, and live our lives toward in a future-oriented way, all of this relies on the arrow of time, which in turn relies on the combination of the past hypothesis and our incomplete knowledge of the current state of the universe. This is not the usual way we think about it. This is, however, the right way of matching our best description of reality with the everyday reality in which we live. You might think it's a little bit creepy or off-putting, it's not the usual way we think, but I think it's actually quite marvelous and wonderful that we can reconcile the fundamental laws of physics with what we do on an everyday life. Hopefully by now, you're convinced that Boltzmann's understanding of entropy is the right one. We were able to think about the world in terms of atoms, arrangements of atoms that look macroscopically the same to us, and explain why entropy increases. Entropy increases because there are more ways to be high entropy than to be low entropy. We're able to recover our previous understandings of the second law from Carnot and Clausius in terms of efficiency of engines and heat equilibrating naturally over time. So in this lecture, we're going to admit that there are problems. We're going to reveal the dirty laundry. It is true that Boltzmann's explanation gives us the right answer under certain assumptions. But these assumptions are not unproblematic. We really need to interrogate why the world works exactly in this way. What are the loose ends that need to be cleared up? There's no real reason to be coy about it. There's one loose end that is the biggest one. Boltzmann helps us understand why entropy will be bigger in the future. He fails at helping us understand why entropy was lower in the past. This is one of those puzzles that wasn't a puzzle before the correct ideas came along. Before Boltzmann, to the extent that there was something called the second law, it was a law. The law says that entropy increases over time, and therefore a consequence of that law is that entropy was lower in the past. But what Boltzmann says is that the second law is not autonomous. It's not separate from the rest of the behavior of matter. The second law is something that we can derive if we know what atoms do. And when you look into the derivation that Boltzmann gives us, you find that it's easy to explain why entropy goes up toward the future, but it's very hard to explain why entropy goes down to the past. So the question in front of us is, do we just need to work harder? Do we have to come up with some clever explanation as to why the understanding of the world in terms of atoms would make the entropy of the universe smaller in the past? Or is our theory incomplete? Do we need to add something to it? And we'll find that, in fact, that yes, we do need to add something to Boltzmann's understanding to truly understand why the second law is true and has always been true in the history of the observable universe. So to get there, think about a set of states. When we think about entropy a la Boltzmann, we think about some system, whether it's a glass of water or the air in a room or the whole universe, and we think about the abstract space of every single configuration that system could be in, the set of all possible states. And we could be thinking about it classically, a la Isaac Newton, in terms of momentum and positions. That's often the language that we will use. We could be thinking about it in terms of quantum mechanics, in terms of wave functions. We don't use that language as often, but it works equally well. It's the same kind of story. We have the set of all possible states, and then we divide it up. We divide the microstates up into sets of macrostates. And a macrostate is a collection of many microstates, all of which look the same to us. The entropy is basically the volume. It's really the logarithm of the volume of that macrostate. How many microstates are in it? So for some large set of states, we have a set of low entropy microstates in one macrostate. Let's imagine we have a set of medium entropy microstates in another macrostate, and we have a larger set of high entropy microstates in a bigger macrostate. The important thing to keep in mind is that a state evolves through time, and that means that every state lies on a unique trajectory. Given the laws of physics and given what state we're in, the whole definition of a state is that it is all the information we need to predict the future and reconstruct the past. So every state is on a trajectory, it evolves toward the future, it came from somewhere in the past, and trajectories never end. That's a consequence of the reversibility of the laws of physics. Trajectories do not stop evolving, nor do two trajectories come together or one trajectory split apart. Every trajectory is unique and it goes on forever as long as time lasts. So maybe there's some ambiguity at the Big Bang, depending on what the universe did then, but at least since the Big Bang, the trajectory of the universe has simply been evolving and will continue to be evolving uniquely. So this space of states that we're thinking about is full of trajectories passing through it, and every state lies on a unique trajectory. So if you like, in every point in this space, there's an arrow going into it, saying which state you came from to get there, and there's an arrow going out of it, saying where you will go in the future. And every single point has an arrow coming in and an arrow going out, whether it's high entropy, low entropy, or whatever. So what Boltzmann asks us to do is to think about what we've called the medium entropy macrostate. That is to say, there's some lower entropy set of states, there's some higher entropy set of states, and there's some medium states that are just right. We know that our entropy now in the universe is not as high as it could possibly be, or as low as it could possibly be, so we are in some sense medium entropy right now. Boltzmann points out that if you follow all of these states, all of these medium entropy states, some of them will just evolve into other medium entropy states, some of them will go to higher entropy, and some of them will go to lower entropy. Boltzmann knows that's true. It's not an absolute law anymore that medium entropy must go to higher entropy. It's possible to go to low entropy. But Boltzmann says we should simply count. We should compare the number of medium entropy states that go to high entropy versus those that go to low entropy. And the counting is very easy. In fact, it's very difficult to represent it accurately in a picture because the total number of states is much huger than we can draw. But the upshot is the same. Many more medium entropy states evolve to high entropy than to low entropy. So if you pick a randomly chosen medium entropy state, it is more likely its entropy will increase than will decrease. We can simply count the number of trajectories where entropy goes up versus going down. There's more where the entropy goes up than when the entropy goes down, starting from a medium entropy state. Now, there's two big puzzles that this picture raises. And one puzzle is kind of minor and annoying, and most people ignore it. The other puzzle is big and profound, and we're going to be worrying about for the entire rest of the course. So let's first get to the minor and annoying puzzle. That's the part of the statement where I said, in this medium entropy macro state, most trajectories increase in entropy. So in other words, if we pick a typical trajectory, the entropy will go up. The question is, who says we should pick randomly a trajectory? In other words, we have many, many trajectories in the medium entropy macro state. In other words, this is basically our current world, all the different arrangements in our world of the atoms and particles that make us up. We don't know the specific positions and momenta of all of them. We know the macroscopic features. So Boltzmann says that to predict what happens next, you choose randomly a typical macro state, a typical microstate within this macro state, and you ask what typically happens. If many, many more of the microstates increase in entropy, you say it is probable that entropy will go up. But who is to say that we are typical? Who is to say that we are on one of the trajectories that actually does go up rather than going down? Even though we don't know the microstate of the universe, we think that there is something called the microstate of the universe. It could be true that we just get unlucky, that we are on a trajectory that will take us to lower entropy. How do we know that's not true? The answer is we don't know in some abstract sense. You can't prove that it's not true. It is an assumption. The assumption actually predates Boltzmann. The idea behind this kind of assumption goes all the way back to Laplace himself. We've talked about Laplace's contributions in terms of determinism and predicting the future and Laplace's demon, but he is also one of the pioneers of probability theory. So Laplace thought about what it means to be typical, what it means to be randomly chosen. He invented what we now call the principle of indifference. Basically, the principle of indifference says that when you have some information, but not all of the information, let's say you know the macro state of the universe, but you don't know the microstate of the universe, the principle of indifference says you should treat every allowed possibility as equally likely. Every alternative is created equal. So in other words, Laplace's principle of indifference tells us that if we want to predict the behavior of the universe, it is okay to consider what happens to a typical microstate, to simply count the microstates that do one thing versus another thing and turn that counting into a probability. Everybody makes this assumption all the time. If you don't know what's going to happen, you assume every alternative is equally likely. If you flip a fair coin, It is true that if you knew the microstate of the universe, you would predict that that coin is going to come up either heads or tails, and you would know which one. You don't know the microstate of the universe, therefore you say it's 50-50. You're assigning equal weight to undistinguishable alternatives. But of course, there is only one universe. The universe does have a microstate, so the justification for this assumption is a little bit shaky. Nevertheless, everybody makes it. And even though it is a problem, we would like to be able to actually say which microstate we're on, and to use that to somehow justify using Laplace's principle of indifference. This is not something that a lot of people worry about. Most of us are happy simply to say our microstate is probably typical within the macrostate we're in, and to reason on that grounds. That's what we're going to be doing for the rest of this course. But that is not the only problem. It is not, in fact, the important problem that we will be talking about. And the important problem we'll be talking about goes right back to the very first days of Boltzmann's ideas. Boltzmann had a mentor back in Austria named Joseph Loschmidt. He was a slightly older Austrian physicist, and he was a friend of Boltzmann's. He was not, in any sense, a competitor. He was not trying to tear him down. But just like Maxwell with his demon, Loschmidt worried a lot about the foundations of this statistical point of view on entropy and statistical mechanics. And Loschmidt invented an objection to Boltzmann's version of the second law, which we now call Loschmidt's reversibility objection. Loschmidt's reversibility objection basically comes down to a very simple fact about the evolution of microstates within this space of all possible states, namely that the trajectories don't begin or end. Every trajectory you're on came from somewhere and goes somewhere. As a simple consequence of that fact, there are just as many trajectories along which entropy is decreasing as there are entropy increasing trajectories. So Boltzmann's statement is true. If you start with medium entropy and let it go, you will usually increase in entropy. But there are just as many trajectories in which the entropy is decreasing as increasing. So you might ask, how can we reconcile these two true statements? It's a matter of which question we are asking. Boltzmann phrased his question in a very particular way. Start with a medium entropy macrostate, ask what happens to it. But you see that's already sneaking in some directionality to time. You start with something and then ask what happens. Loschmidt says I could just as easily ask the question, where did the medium entropy states come from? In other words, instead of saying where do the medium entropy states evolve to in the future, I could say what is a typical past of a state that is now medium entropy. And of course, it's exactly the same kind of calculation, but just with the arrow of time reversed. And crucially, because the laws of physics are reversible, the features of the past are the same as the features of the future. Therefore, the consequence of this is that for all the states that have medium entropy, many more of them came from high entropy states in the past than came from low entropy states in the past. If you are going to take seriously Boltzmann's claim that most medium entropy states increase in entropy as time goes on, then you should take seriously Loschmidt's point that most of these medium entropy states came from a higher entropy past. The problem is nobody believes that's true. We do not think that is how the universe actually works. So Boltzmann, if we take him seriously, managed to give us a very convincing argument that starting from the universe today, starting from our medium entropy configuration that we find ourselves in, it is natural for entropy to increase. There's more ways to be high entropy than to be low entropy. It's not an absolute law, it's just a probability. But the same argument says that it is natural to come from a higher entropy past because there are more ways to be high entropy than to be low entropy. He can explain the future, he cannot explain the past. Now, Boltzmann didn't believe that the past was higher entropy. He believes, just like everybody else, that the second law has been true throughout the history of the observable universe. But the manifest implication of his ideas was different. It implies that the entropy was higher in the past. Now, this is something that is worth sort of emphasizing and dwelling on, because this is the first implication of Boltzmann's ideas that is not at all intuitive. It makes sense to us that if you put gas in a box and most of it is on one side and not the other side, it tends to even out. Put a hot thing next to a cold thing, their temperature tends to equilibrate. All of that makes sense to us. But because we live in a world with such a pronounced arrow of time, we tend to think about the future and the past differently. We tend to think that our current situation has some sort of tendency to have been going from lower entropy to higher entropy. So when Boltzmann says, I can predict on the basis of statistics that the future will be higher entropy, we nod our heads and go, oh yes, that seems to make very much sense. When Loschmidt says that exactly the same logic predicts that our current macro state came from a higher entropy past, we shake our heads and go, no, that can't possibly be right. But the logic is exactly the same. So we want to know, how can we escape this conclusion? What we want to do is to accept Boltzmann's logic that says entropy will increase toward the future, but reject the fact that it implies it was higher in the past. It's interesting to note that historically, even Boltzmann himself fell prey to the difficulty we have in treating the arrow of time fairly. Remember, way back in the beginning lectures, we talked about the view from nowhen, from the idea of standing outside the universe, not assuming there is an arrow of time, and just contemplating all the different ways that time could evolve. Now, Boltzmann himself, when he was dealing with the second law, he proved a theorem called the H theorem, which amounted essentially to proving the statement that the entropy must always increase in time. To get the technical connection right, H was minus the entropy, and he proved that it should always go down. So I don't know why that was a clever thing to do. Essentially, Boltzmann's H theorem is a statement that entropy tends to increase. And he didn't think that he put any assumptions in there about time asymmetry. He thought that he was just making reasonable assumptions about statistics. But later people who dug into the dirty details of the axioms Boltzmann used to prove his H theorem realized there was a subtle assumption that did sneak time asymmetry into it. Boltzmann assumed that when particles were bouncing into each other, that the velocities and direction in which the particles were moving were uncorrelated with each other. So if you have some box of gas, particles bouncing around, where one particle is moving doesn't know what other particles are doing. That sounds completely innocuous. This is the assumption of molecular chaos, he called it. The problem with this assumption is that once you start the evolution, even if particles start uncorrelated, once they bump into each other, they are suddenly correlated. The two particles that are moving apart from the same place because they just bumped into each other. So if you start your box of gas with an assumption that the motion is uncorrelated, it instantly breaks the next moment. By putting that assumption in at the beginning, you're sneaking in the arrow of time from the start. So this was the challenge that people faced. They wanted to derive the arrow of time, not just assume it from the start, but what Boltzmann had bequeathed was a set of machinery that didn't have an arrow of time built in. It could explain entropy going up toward the future, but it also explains entropy going up toward the past, which nobody thought was true. So the challenge was, could you use these time-symmetric underlying laws of physics to derive a time asymmetric conclusion? The answer is no. Loschmidt was right. It was not that he was making some mistake or that Boltzmann wasn't careful enough. Loschmidt's reversibility objection is absolutely valid. If all you have to work with are underlying laws of physics that are symmetric with respect to past and future, and Boltzmann's statistical ideas that you chunk up the space of states into macro states that look the same to our macroscopic observation, you do not derive a different behavior for the future than you do for the past. You need to add something to that machinery. You need to add an extra assumption, and you need to add an extra assumption that is explicitly asymmetric with respect to past and future. That extra assumption is what we call the past hypothesis. The past hypothesis is the assumption that the entropy of our observable universe not too long ago was much lower than it is today. In fact, a little bit more carefully, the past hypothesis assumes that the early universe was in a configuration which was, number one, low entropy, and number two was the kind of low entropy configuration which, under natural thermodynamic evolution, would get us to where we are today. The point is that there are many ways to be low entropy, but there's a specific low entropy kind of thing that naturally grows into the universe we see. For example, if you imagine a box of gas and you took a snapshot of it, and you notice that all of the gas was sort of concentrated in the vicinity of one corner of the box of gas. Now, according to statistics, that could just be an unlikely fluctuation, but you might say, well, that would make sense to me if all of the gas in the box started in a very, very concentrated form right in the corner, and I'm just observing it as it's expanding and filling the box. That's a sensible explanation for what you have observed. That's a version in the box of gas of what we call the past hypothesis for the universe. The past hypothesis for the universe talks about what we would call conditions near the Big Bang. Now, obviously, Boltzmann and his friends, Loschmidt, etc., they didn't know about the Big Bang, but they knew that the correct way, or at least they eventually realized, the correct way of justifying the second law of thermodynamics within Boltzmann's framework was to add this assumption that explicitly broke the symmetry of past and future. So the point is that the past hypothesis teaches us that the arrow of time, the real difference between the past and the future, isn't a matter of atomic theory, statistical mechanics, or anything like that. It's not deeply ingrained in the nature of time. It's a feature of our environment, a feature of the universe in which we find ourselves. It's a statement about the stuff in the universe and what it was doing in the past. One way of thinking about it is, Boltzmann, given his assumptions, given Laplace's principle of indifference, and given the definition of entropy as the number of microstates or the log of the number of microstates in a macrostate, he gives us a convincing argument for why the entropy of the universe tomorrow should be higher than it was today. He doesn't give us an argument for why it would have been lower yesterday. So the past hypothesis says the reason why the entropy of the universe was lower yesterday than it is today was because it was even lower the day before yesterday. And the reason why it was even lower the day before yesterday is that it was even lower the day before that. And so on, 13.7 billion years all the way back to the Big Bang. This is a remarkable fact. We can't derive the history of the universe as we know and love it on the basis of purely dynamical grounds. We have to put in an assumption about the boundary condition in the past. There is no matching assumption about the boundary condition of the future. We get the answers right by assuming that there is nothing special about the future. The future will be a typical state. We are evolving toward higher and higher entropy. That will keep going. You don't need to say anything about the future. That's where the imbalance comes from. That's where the difference between past and future comes from. We make a past hypothesis. There is no future hypothesis. Now, just to give you an idea of what a future hypothesis would be like, remember, there is no future hypothesis that we actually think is part of physics. We only think there's a past hypothesis. But philosopher of physics, Craig Callender, has asked us to imagine what it would be like. He says, imagine you go to a fortune teller, one who is always right. And the fortune teller gives you bad news. She says, you are going to die within a couple weeks, but before you die, all of the world's imperial Fabergé eggs are going to collect in the dresser drawer in your bedroom. Now, you don't like the fact that she says you're going to die, but you're not worried too much because you say, well, I will just prevent the Fabergé eggs from collecting in my dresser drawer. These are these beautiful Russian works of art. There are about 42 of them scattered throughout the world's museums. It shouldn't be too hard to not collect them in my dresser drawer. But what happens is, despite your best efforts, they keep accumulating there, these Fabergé eggs. There is a delivery that was supposed to go to a museum, but the address got written a little bit sloppily. Instead, it gets delivered to your house, and there's an egg. You get scared, so you throw the egg out the window, but it happens to hit a lamppost and careens off back into your bedroom and lands in your dresser drawer. Things like this happen over and over again, and gradually, one by one, your dresser drawer fills up with imperial Fabergé eggs. The important thing about this thought experiment is that no laws of physics are broken along the way. Just like it does not break the laws of physics to take a scrambled egg and turn it back into a regular egg. It's unlikely, but it could happen. Likewise, this future boundary condition that says all of the eggs land in your dresser drawer can be achieved without breaking any laws of physics, just breaking the rules of probability. Unlikely things keep happening. Now, do you say to yourself, that's kind of a silly thought experiment? It's bizarre to imagine that there's some condition in the past that is so specific. There might be many ways to get there, but it says something specific about what the world will be like 2 weeks from now. The reason why it's nevertheless worth thinking about is because it is actually no more bizarre than to imagine that there is a past condition that says the world is in some very specific macrostate, some low entropy macrostate, some macrostate that is very, very small numbers among all the possible configurations we could have been in. The past hypothesis seems to be necessary and true if we want to understand the past, but it doesn't come from the underlying theory. It's not atomic theory, Newtonian mechanics, classical mechanics, quantum mechanics, particle physics. None of those things justify or explain the past hypothesis. It has to come from cosmology. In other words, it's conditions near the Big Bang, 13.7 billion years ago, that are what we refer to when we talk about the past hypothesis. The universe started with low entropy. It's an interesting historical question. Why didn't Boltzmann invent the Big Bang? So just to get the history right, Boltzmann died in 1906. The controversies over entropy were mostly 1870s, 1880s, 1890s. The Big Bang didn't come along until after Einstein invented general relativity in 1916. So the idea of the Big Bang wasn't really developed in details until the 1920s. But you can ask yourself, given that Boltzmann and his friends should have known that the success of their program for understanding thermodynamics relied on an assumption that the universe started with a low entropy, should they have invented something like the Big Bang? Should they have been able to say the universe started in a condition like that and has been evolving ever since? They didn't say that, so it's an interesting historical thought experiment, but maybe that's what they should have thought of. So with that in mind, we understand the statement that we made long ago, that the arrow of time is like the arrow of space. The arrow of space here on Earth is not something intrinsic to the laws of physics. It's just because we're standing on the Earth. The gravitational field of the Earth distorts our local environment. It creates a direction, namely down, that we all agree on what that direction is. But it's not universal. We don't agree on it between us here and someone on a continent on the other side of the world. It's a feature of our local environment. The past hypothesis tells us that the arrow of time is the same way. It doesn't come from the deep down laws of physics. It comes from our local environment. Now, by local we mean the whole observable universe. But just like the Earth is an influential object that creates an arrow of space, the Big Bang is an influential event that creates an arrow of time. The next challenge we have is to be cosmologists, to explain why the early universe had such a low entropy. We need to do that not just to understand cosmology itself, but ultimately to understand why we can go from eggs to scrambled eggs, but not from scrambled eggs to eggs. So now we know what entropy really is. The world around us is made of atoms. Those atoms have many different ways of arranging themselves, but when we look at the things in the universe, we don't see the individual atoms. There are many different ways that look the same to us. And Boltzmann taught us that the entropy is just a logarithm of the number of ways to arrange the atoms so that they look macroscopically indistinguishable. It's the number of indistinguishable microstates within a macrostate. Basically, in the last lecture, we ate our vegetables. We learned about logarithms, we got the definition right, we considered an example and calculated some numbers. For the rest of the course, it's all going to be about the main course and the dessert. No more logarithms and very few numbers. All you need to remember is that a high entropy state is one where there are many arrangements that look that way. A low entropy state is one where there are few arrangements that look that way. If you're shuffling a deck of cards, there are many ways for the cards to be randomly shuffled. There's only one way for them to be perfectly ordinarily arranged. If you're playing pool, there are few ways for all the balls to be racked together. There are many ways for them to be scattered across the table. If you have a glass of water, there are few ways to have ice and warm water. There are more ways to have all of the water be in the same state. So entropy tends to go up, according to Boltzmann, simply because there are more ways to be high entropy than to be low entropy. That's his version of the second law of thermodynamics. We also, of course, have the other formulations of the second law of thermodynamics. So our first task is to make sure that Boltzmann's definition of entropy helps us to recover the previous ideas that we had. We had Carnot's version of a maximally efficient steam engine, the one that was absolutely reversible. And we also have Clausius's notion that if you take two objects and put them together at different temperatures, the temperatures will even out. We should check that Boltzmann's way of thinking about entropy is compatible with these pre-existing ways. So let's think about Clausius. He says you have one box of gas at one temperature, you have another box of gas at another temperature. If you put them together, they will equilibrate. They will come to the same temperature. Now Boltzmann, when we were investigating his idea, we used one box of gas and another box of gas, but instead of different temperatures, we had one box that was full of atoms and the other one that was empty. With a small hole in between, we found that the atoms would generally tend to even out. We would like to do the same thing for the heat that is in the boxes that Clausius was considering. Note that Clausius's definition wouldn't tell us anything about the example we looked at in the last lecture. Clausius talked about the transfer of heat, but when we have a box at constant temperature, just with a higher density on one side than the other, then Clausius is silent. He isn't saying anything. The temperature is the same on both sides. Boltzmann tells us what we know to be true, which is that if you have one box with a lot of atoms, they will generally leak to the other box until the density is more or less the same. We want to check that that is also true for the temperature. And it's a pretty easy thought experiment to do. Remember, temperature is just telling us how fast the individual atoms are moving. So in each box, if you have a high temperature box and a low temperature box, think of the fast moving atoms as red grains of sand, the slow moving atoms as blue grains of sand. There are more arrangements where the sand grains are mixed than ones where they're kept segregated in the different boxes. In other words, in the boxes of gas with different temperatures, there are more arrangements where there are an equal number of hot atoms in the left box and the right box, and an equal number of cold atoms in the left box and the right box. And therefore, the highest entropy state is one in which the temperature is the same. So Boltzmann's reasoning gets us back to Clausius's version of the second law of thermodynamics. Temperatures tend to come to equilibrium. What Boltzmann has done is to unify the entropy of heat with the entropy of mixing. We have one formula that's on Boltzmann's tombstone that lets us understand both different circumstances. That's a classic example of progress in science, when you can understand two different phenomena using one single unified picture. So what about Carnot's picture? It sounds a little different. Remember, Saji Carnot was interested in building the perfect steam engine, so he invented a cycle, a way of running a steam engine that was maximally efficient. He realized that to get this maximally efficient steam engine, you would have to have a process that was reversible, and that most real-world steam engines were irreversible. We would now say that the entropy is increasing. So what we would like to do is to think of entropy in Boltzmann's language and use it to distinguish between efficient and inefficient steam engines. Or another way of saying it is, can we get useful work out of a certain arrangement of atoms? Useful work is stuff that we can do something with. We can push a vehicle, or we can lift something from the ground to a higher altitude. That's what we would like to be able to do. A box of gas has energy in it. The question is, can we use that energy for some purpose? Can we make it do useful work? So consider a piston, not a big thick piston, but a rather thin piston that is in a big cylinder. So basically, we start with our piston in the middle of the cylinder, and we're reconstructing our two boxes of gas. We have one side of the cylinder and the other side of the cylinder divided by the piston. So what we're going to do is we're going to put gas into that cylinder, into that chamber, and we're going to ask, can it do useful work? So first, imagine that we put all of the gas on one side of the piston. So we have one side of the piston that's full of gas, the other one is completely empty. Well, what's going to happen? And again, we don't even need to use science or equations, we can just think about it intuitively. If one side of the piston is empty, if it's a vacuum, and the other side of the piston is a gas, it's as atoms moving around and pushing on the piston, exerting pressure, then we know what's going to happen. That piston is going to be pushed away from the gas. It's going to move into the direction of the vacuum and expand the volume of the region that has the gas in it. In other words, those atoms moving around do useful work. They push the piston in one uniform direction. We are extracting energy from the gas because as we expand its volume, just as in a refrigerator, expanding the volume of the gas cools it down. We lower the temperature of the atoms. So in that configuration, that's a low entropy configuration, and we can do useful work with it. It's not that energy is created or destroyed. We're just taking energy out of the atoms and putting it into the piston, using it to move our car along the highway. Now imagine the same amount of energy, but in a different configuration. Take the same gas molecules, the same number of molecules with the same temperature, but have the piston in the middle of the cylinder and put half of the molecules on one side of the piston, half of the molecules on the other side. So the total energy is the same as we had before. It's just that the distribution of atoms is different. But notice what happens. Now that the same amount of gas is on one side of the piston as on the other side, there is no net force. The piston doesn't move. We can push or pull the piston, but that requires work. That would take work away from us. Even though the same amount of energy is in the piston now as was before, we can't extract that energy out. And the reason, of course, is because the energy is in a high entropy form. High entropy is an even distribution of gas molecules on both sides of the piston. And even though the energy is there, we cannot take it out. In other words, Boltzmann's way of looking at entropy, which says that the entropy will be highest when there's a large number of arrangements, when the gas molecules are evenly spread one side and the other, recovers Saji-Carnot's insight that low entropy energy can do useful work, high entropy energy cannot. So that reinforces the idea that we had that entropy is one way of measuring the uselessness of energy. The total amount of energy is conserved, but it can go from a useful form, a low entropy form, to a useless form, high entropy. That's what happens when you burn fuel. When you burn gasoline in your car, you're not creating energy, you're releasing it, and you're converting it into a higher entropy form. That's why you can burn fuel, but you cannot unburn it. If you look at the other set of lectures I've done for the teaching company about dark matter and dark energy, you'll learn about dark energy, which is most of the energy in our universe today. It is absolutely uniformly spread through space. Something like 73% of the total energy of the universe is in this form of mysterious cosmological stuff called dark energy. We know it's there, it's making the universe accelerate. Our astronomical observations say that it is there. But the sad story is that because it is absolutely perfectly uniform throughout space, it is in its highest entropy state. Dark energy is maximally useless. You would like to say, well, there's all this energy in the universe. Can we somehow use it to do something? And the answer is no. Dark energy is like fuel that has already been burned. It's energy in its most useless configuration. So back to our everyday world. Now that we understand the definition of entropy, Boltzmann gave it to us, and we understand that we recovered the second law of thermodynamics, we can clean up some of the sloppy ways that we've been talking about entropy. For example, you will often hear, and I will often say it because it's almost completely true, that entropy measures the disorderliness of a certain configuration of stuff, the randomness or the haphazardness. The reason why that's almost true is because entropy measures disorder when all other things are created equal, but sometimes not all other things are created equal. The true statement of entropy is not that it's the disorderliness. The true statement of entropy is it's the logarithm of the number of configurations that look macroscopically the same. Whenever you're confused about entropy, go back to the equation that's on Boltzmann's tombstone. That is the right definition. So to get this notion exactly straight, consider again gas in a box. Let's say a big size box, a box the size of the room that you're in right now. Imagine that the whole atmosphere in the room you're in were squeezed into a very tiny cube right in the middle of the room, just 1 millimeter on a side. Now, I'm not imagining that there's literally a box that's holding it together. Just imagine that happens to be a randomly chosen configuration of all the gas molecules in your room. It's an allowed configuration, but it's a very, very low entropy configuration. There are very few arrangements of the atmosphere in your room that just by chance have all the molecules squeezed into a 1 millimeter across cube. That's very, very low entropy. We could also consider a random arrangement of the molecules of atoms of air in your room, which are squeezed into a miniature version of the Statue of Liberty, 10 centimeters high. So just by chance, all the air molecules in your room miniaturize a little form of the Statue of Liberty, including the crown and the torch and all that, about 10 centimeters tall. That is also a very low entropy configuration. However, when you plug in the numbers, having all the air molecules in the room form a little Statue of Liberty 10 centimeters tall is much higher entropy than having them all in a little cube or even a little sphere just 1 millimeter across. Even though the shape of the Statue of Liberty is more specific, even though it is more complex and has more details, because that Statue of Liberty that we're hypothesizing is simply bigger, there are just more ways to arrange the atoms to look like that than to squeeze them all into 1 millimeter across. There are more configurations that look like a 10 centimeter Statue of Liberty than look like a 1 millimeter cube. So the entropy is higher. That Statue of Liberty is more likely, even though it is more complex. Don't mix up complexity or simplicity with low entropy and high entropy. Don't even mix up the idea that high entropy means that things are more mixed together. We all know that oil and water don't mix. If you take milk and stir it into your coffee, they naturally mix together. If you take oil and water and stir them together, they might mix for a little while, but their natural evolution is to separate. So you want to ask yourself, why do oil and water behave in the opposite way to milk and coffee? It seems to violate the second law of thermodynamics. What you have to do is actually think about the individual properties of oil molecules and water molecules. It turns out that oil molecules are hydrophilic. They like the water molecules and they like to stick them into a very particular configuration. So when one oil molecule is next to water, it freezes into a particular configuration. What that means is that if all of the oil is mixed with all of the water, the total number of arrangements is actually smaller than when the two are segregated. When the oil and water are segregated from each other, the oil is in whatever configuration it wants, the water is in whatever configuration it wants. When they're mixed together, they stick, and there are fewer such configurations. I'm driving home this example because over and over again, what you really should care about is, are there more configurations or less configurations? So again, entropy is not about complexity or simplicity. If you want to know what is higher entropy, you plug in the number of configurations that look the same. Now often you won't know. You'll have something like, a cloud of gas that wants to make a galaxy, and you don't know how to count how many configurations look that way. But you can also work the definition backwards. If you know that a certain procedure, a certain process in nature happens in one way but not the other, for example, a giant gas cloud or dust cloud forms a galaxy, but galaxies do not dissolve into giant clouds of gas and dust, you know that the way that the system wants to go is in the direction of higher entropy. So a galaxy is higher entropy than an undifferentiated, smooth cloud of gas and dust. That's a simple way of realizing whether something is higher or lower in entropy. So now we can get to some of the deep philosophical implications of Boltzmann's way of thinking about entropy. The biggest implication is that the second law of thermodynamics is not really a law. It's a really good idea. It's a statistical statement about probabilities. Boltzmann says that the reason why entropy goes up is because there are more ways to be high entropy than to be low entropy. And what that means is that it is probable that a random configuration that isn't already at maximum entropy will tend towards maximum entropy, will tend towards increasing the logarithm of the number of states. But what that means is that occasionally, improbably, but if you wait long enough it will happen, entropy will decrease. The second law is not an absolute law. In fact, if you take a box of gas that is in equilibrium, a box of gas that is in its highest entropy state, let's say in our example where there's 1,000 atoms on one side and 1,000 atoms on the other side, certainly if you wait, there will occasionally be fluctuations where there's 1,002 atoms on one side and 998 on the other, and vice versa. What that means is if you keep track of exactly the number corresponding to the entropy of a box of gas, if it's sitting at its maximum, if it's in equilibrium, there will be fluctuations. Just through the random motions of the molecules, the entropy will go down a little bit and then it will relax back to equilibrium. It turns out that this is actually relevant to the functioning of life. In certain macroscopic biological molecules, you don't just see what they want to do in the most probable way, you look at the fluctuations, and that's incredibly important for how cells actually function. This is cutting-edge biology trying to match the statistical understanding of fluctuations to how molecules work in our bodies. Now, in the real world, all around us, we are not in equilibrium. We're not a box of gas with highest possible entropy. We are many, many, many molecules. It's not just 2,000. It's a lot more molecules in the real world than Avogadro's number, 6 times 10 to the 23. So it is true that the entropy of something in the real world could go down, but the probability of it happening is incredibly tiny. If you have, let's say, 100 particles in a box moving back and forth, and you want to know how long would it take for a sizable, noticeable decrease in entropy, it's much longer than the age of the universe is the most probable answer. So because the number of atoms, the number of molecules, the number of moving parts in the universe is so large, even though Boltzmann says that it's only probable that entropy will increase, it is so overwhelmingly probable that it is practically a law. Nevertheless, it was hard for people to accept this. In the 1870s, all through the 1890s, when Boltzmann and other people like Maxwell and Gibbs and Thomson were pushing this idea that atoms helped us understand entropy, they met with enormous resistance. After all, this was the second law of thermodynamics we're talking about. The first law says that energy is conserved. No one was going to suggest that that was only approximate. That is absolute. Energy just is conserved. And now you're saying that entropy increasing is not absolutely conserved. That met a lot of resistance. Furthermore, once you enter that idea into your head, that entropy increasing is just probable, not necessary, you realize that you could do experiments which intentionally decreased the entropy. Imagine you have a box of gas which starts in a low entropy state, like all the gas is in one little corner, and you let it evolve so all the gas spreads out, the entropy goes up. And imagine that you are Laplace's demon, so you can see every atom, you can see its position and its momentum. Take the configuration you're in at the end of that experiment, when you have a high entropy box of gas, and just reverse the velocity of every single atom. Send every atom and molecule backwards along the path it came. What will happen? Because the laws of physics are reversible, the box of gas will evolve exactly backwards the evolution that it did going from low entropy to high entropy. In other words, if you arrange it that way, which is certainly a thought experiment kind of thing, you can't possibly do this in the real world, but if you could, you would arrange a box of gas that decreased in entropy even though it was a closed system, in gross violation of what we think of as the second law of thermodynamics. Now, it's important to emphasize this doesn't happen by itself, spontaneously. You could arrange it to happen, and even arranging it to happen is, again, only a thought experiment. The point is that any tiny deviation would spoil it. Imagine you have 10 to the 23 molecules of gas in your box, and you keep track of the momentum, the velocity, and the position of every single molecule, and you delicately arrange it so that the entropy will go down. But just before you start your experiment, the cat that is in your laboratory goes and touches one of those molecules and disturbs it from the precise velocity that you gave it. Just that one disturbance of one molecule is enough to completely spoil the experiment. The entropy would not go down because you have not accurately arranged all of the velocities and positions of the atoms in your box. It's like shooting an arrow at a target that is millions of miles away. Any tiny deviation from the perfect accuracy means you will miss the target completely. So even if you could imagine doing it, what this means is there's no danger that in the real world you would ever meet a person who lives backward in time. There's no danger that Merlin from The Once and Future King or Benjamin Button from the movie or F. Scott Fitzgerald's story could actually possibly live in the real world. Even if you can imagine a box of gas isolated whose entropy goes down, once that box of gas started interacting with the outside world, our interactions would disturb the velocities and the positions of the atoms in that box, and the entropy would stop going down. Therefore, there's no danger that in the real world we will meet aliens or people close by or artificial intelligences that remember the future and don't remember the past. The idea of consciousness is something that is absolutely tied up with the increase of entropy and the arrow of time, and because it is so delicately arranged, it is absolutely universal. Everything we will ever meet in the real world experiences the arrow of time in the same direction. But this possibility of a thought experiment, the possibility of arranging something carefully to decrease in entropy, was very intriguing to the physicists of the 19th century. Remember, they thought that entropy increase was absolute. Kinetic theory, atomic theory suggested that it was not absolute, and therefore they worried that they were missing something. They worried that maybe they should be fixing their atomic theory so that the increase of entropy was not just probabilistic, that it really became absolute. And along these directions, there was a thought experiment proposed by James Clerk Maxwell, the guy who is most famous for unifying electricity and magnetism, but also did a lot of work on kinetic theory and thermodynamics. Like Boltzmann, Maxwell believed in atoms. He believed that Boltzmann's ideas about entropy were on the right track, so he was not a competitor. He wanted to believe in the answer. He was sympathetic, but he was puzzled about the statistical nature of the second law, and so he proposed this thought experiment that people should think about to get their ideas exactly right. Maxwell's thought experiment was the famous idea of Maxwell's demon. I believe that Maxwell actually did call it a demon, unlike Laplace. The idea in the 19th century was that demons were these little things that were intelligent and a little bit mischievous, so they got in our way. Maxwell's demon sits on top of our box of gas with a partition in the middle. So there's a box of gas with a bunch of molecules on the left, a bunch of molecules on the right, a partition in the middle with a little hole in it so atoms can pass back and forth. But the difference is that Maxwell's demon stands on top of the box and he looks at the molecules. And he has a little switch that he can turn on and off. And what Maxwell's demon does is to let some molecules go from right to left, other molecules go from left to right. In particular, he's choosy. He lets the high velocity atoms go from left to right, and the low velocity atoms go from right to left, but not vice versa. If that could happen, what you would get after the demon has worked for quite a while, he hasn't disturbed the velocity of any of the atoms, he just lets them through or doesn't let them through. But because of the work of the demon, you start with equal temperatures on both sides, and at the end you have a high temperature on the right and a low temperature on the left. You have violated Clausius's formulation of the second law. Heat seems to have flowed from thermal equilibrium out of thermal equilibrium. So this was a challenge to kinetic theory and atomic theory and its understanding of how entropy worked. This comes from 1871. So this is right at the beginning of when people were thinking about these ideas, and they were very worried about it. Now, it's kind of obvious what the solution to the Maxwell's demon conundrum has to be, but it is very far from obvious how it actually works. The obvious thought is that somehow the demon itself creates entropy. Remember, the problem is that in the box of gas the demon stands on, it can decrease the entropy of the gas inside the box by letting molecules go one way but not the other. But to do that, the demon has to do something. It has to look at the molecules, it has to observe them, and has to open and close the door. So you worry that maybe you're just not being careful enough, you're not keeping track of the activities of the demon, and if you could, you would realize that the demon is actually generating heat or entropy or something like that. So literally for decades, people thought hard about the Maxwell's demon thought experiment, trying to see how the entropy really went up, really obeyed the second law of thermodynamics. The first idea was that, well, when the demon opens and closes the door slams shut and it makes noise or something like that, thereby increasing the entropy of the world. People quickly show that that was not the right answer. You can design a little door that the demon controls that moves almost imperceptibly up and down so you don't increase any entropy. It was then suggested that, well, maybe when the demon looks at the molecules, that process of observation increases the entropy of the universe. And a famous physicist named Leo Szilard, who actually played an important role in the atomic bomb project, in 1929 thought about the Maxwell's demon problem, and he showed that the demon could observe the molecules, again, without increasing any entropy. The effect of the demon looking at the molecules and keeping track could be made as pointless, as effectless as you want. It does not need to have an important influence on what the molecules do. So that's 1929, almost 60 years after the original experiment, and we were still wondering about it. So the next idea came in 1960, when Rolf Landauer, a physicist at IBM, made an explicit model where he showed that you can measure the velocity of the atoms in the box reversibly. In other words, what we want to do is not increase entropy, so you want to let the demon look at the molecules without increasing their entropy. To absolutely prove it, you just do it in such a way that you can undo it, make it a reversible process. What Landauer was able to show that Szilard was not, was that the way to make the measurements reversible was to simply write them down in a notebook. You need, if you're the demon, to have a way of keeping track of the information. And this actually played a crucial role in the development of what we now call information theory. Landauer was able to show that irreversible computations are the ones that generate entropy. He made a connection between calculation and computation and the increase of entropy in the universe. What we now call Landauer's principle says that irreversible computations increase entropy, reversible computations do not. Taking 2 plus 2 and adding them together to get 4 increases the entropy of the universe. But Landauer was not able, of course, to convince us that Maxwell's demon really did increase the entropy of the universe. In fact, he worried us. He seemed to be telling us that you could be Maxwell's demon without increasing the entropy. It wasn't until 1982, over a century after Maxwell proposed the idea, that Charles Bennett, who's a computer scientist also working at IBM, finally solved the problem in a way that many of us think is satisfactory. What Bennett realized, again using ideas from information theory, is that since Landauer showed Maxwell's demon needs to have a notebook, eventually that notebook is going to run out of pages. Now this sounds a little silly, but the point is that a finite-sized Maxwell's demon can only keep track of a finite amount of information. But to really convince yourself that the molecules will only go one way and not the other, the demon needs to constantly be updating his information about where the molecules are. He needs to keep a potentially infinite amount of information. That's okay as long as he can erase the previous entries in his notebook. And what Bennett realized is that it is erasing information that is the irreversible step. That Maxwell's demon can look at the molecules, get the information, that's reversible. The demon can open the door and he can let heat flow in one direction and not the other, that's also perfectly fine. But if he wants to keep doing this for a long period, he needs to erase the information in his memory, and it's erasing information that increases the entropy of the universe. That makes sense to us. Increasing entropy means doing something irreversible. Writing something down is reversible, but erasing something is not. Once you've erased it, you don't know where it went. So I want to mention one final thing about Boltzmann. He met with resistance from many physicists about his ideas that entropy was statistical, not absolute. And he also struggled with depression all of his life. He committed suicide ultimately in 1906, which was ironic because only in 1905, Einstein and other people put together perhaps the strongest evidence yet that atoms were real and they really existed. A lot of people speculate that it was the resistance to his ideas that led him to suicide, but that's not true. He simply was depressive. He struggled with that all of his life. But the important thing to remember is that Boltzmann is as influential as any of the physicists that we know. As Einstein, as Newton, as Galileo, his role in putting together a statistical view of the world is absolutely central to how we think about the universe today. We're now 1/3 of the way through the course. It's a good time to sort of take stock, figure out what we've learned so far and where we're going. And the truth is that so far, what we've really been doing is laying the groundwork. We talked about time, what time is it just as real in the past and the future? We've talked about measuring time with clocks and calendars, and we've said that the real mystery of time is the arrow of time, the fact that the past is different from the future. We've also claimed that the reason why the past is different from the future is because of entropy, because of the second law of thermodynamics, which says that toward the future, entropy increases, toward the past, it was lower. We've investigated a couple of possible explanations for why there is an arrow of time and said that they're not the right explanation. It's not because time reversal is violated by the weak interactions of particle physics, and it's not because of the collapse of the wave function being irreversible either. It has to come down to entropy. So in this lecture, we really start answering the question, not just setting it up. We're going to dive into what entropy really is, give the rigorous modern definition of it, and explain what we do understand and what we don't understand about how entropy works. Our modern understanding of entropy comes from the 1870s. That's not very modern, but it's still the right answer as far as we currently know. It comes from the Austrian physicist Ludwig Boltzmann. The idea of entropy predated Boltzmann. It came from Carnot and Clausius, the second law and the word and the notion of entropy. What Boltzmann added to the discussion was the idea that matter is made of atoms. And atoms have a really important role in how we think about stuff in the universe. You've all seen the periodic table, if only because it was hanging in the room when you took chemistry back in high school, the list of all the different chemical elements. The idea of atoms goes all the way back to ancient Greece. People like Democritus said the world is made of discrete objects called atoms. So when chemists in the 19th century realized that elements could be divided into their smallest possible pieces, they naturally gave the word atoms to those smallest possible units of an element. And that is what you see in that periodic table, the elements of chemistry, hydrogen, zirconium, iron, and so forth. These days, we would say that even the atoms can be divided into smaller particles, the protons, neutrons, and electrons, and the protons and neutrons are made of quarks and gluons. But none of that is absolutely necessary for Boltzmann and his understanding of entropy. All we need is that matter consists of discrete little pieces. This is a tremendously powerful idea. It means that when you see ice, when you see water vapor, these are not different things. These are different arrangements of the same fundamental set of things. Since there's only really electrons, protons, and neutrons, everything you see around you, every form of matter is just a different arrangement of those substances. When we talk about the different properties of different kinds of matter, we have to explain that in terms of the different arrangements of the underlying pieces, different arrangements of the atoms and the particles. So this was the task that physicists found themselves faced with in the 1800s when the chemists began to convince the physicists that there were such a thing as atoms. And the chemists and the physicists teamed up to invent what was called kinetic theory, trying to understand thermodynamics, the science of heat and fluids and motion, in terms of atomic theory, in terms of the idea that all of these different substances were collections of atoms. What that means is that what you might think of as an absolute law could just be a statistical law. It could just be that probably the atoms will do a certain thing. The point is that even in a very small collection of macroscopic material, there is a large number of atoms. The number that scientists use to indicate a macroscopic amount is Avogadro's number. It's the number of carbon atoms in 12 grams of carbon. 12 grams is not very much. It's a good-sized pinch of sand. But in that pinch of sand, there's something like 6 times 10 to the 23 atoms or molecules. That's a huge number, 6 followed by 23 zeros. It's a giant number, far bigger than ones that we use in our everyday lives. Avogadro's number is the indication that we can throw away information. That's the key to going from the world of atoms to the macroscopic world. It's called coarse graining. It's basically the idea that because in any tiny macroscopic object, not to mention any big macroscopic object, we can't possibly keep track of what every atom is doing. Therefore, we need to keep track of less than perfect information. We don't write down the position and the velocity of every atom. Laplace taught us that if we wanted to know exactly what was going to happen, that's what we would have to do, but it's completely impractical in the real world. Instead, we average. We take typical features of the whole collection of atoms in some macroscopic object. We talk about the density of the material, which is the number of atoms in any one little volume. We talk about the pressure of a fluid or a gas. That's just the force. When the atoms hit some boundary, those atoms push on the boundary, and that's the pressure that you feel at the boundary. We talk about the temperature of a material. That's the average kinetic energy, the energy of motion, because all the atoms are jiggling back and forth. High temperature means the atoms are jiggling fast. Low temperature means they're jiggling slowly. And then we talk about the heat. That's just the total thermal energy. You take the temperature and you include all of it over the whole volume. That's how you get the heat. What you notice about all of these ideas is that they are all properties of the atoms. Density, temperature, heat, these are not separate substances. There is no heat fluid. Back in the early days of the 19th century, they thought there was a heat fluid. They called it caloric. Atomic theory says that they were not correct, that all of these different things are properties of the atoms. And so it's obvious to ask, is entropy also a property of the atoms? That's what Boltzmann put together. He realized that entropy, just like the other thermodynamic quantities, could be thought of as a property of the underlying atomic description. If you like, think of grains of sand. Just imagine we blow up our atoms until they're the size of grains of sand. And imagine that some of those grains are blue and some of those grains of sand are red. If they're in separate piles, or if they're in, one box, but all the blue grains are on one side and all the red grains are on the other side, that is a low entropy configuration. There's the blue sand and the red sand. If you mix it together, it's clear that the entropy goes up. It's clear that's an irreversible process. You mix all the sand together, and what happens is that instead of blue and red grains, from a distance, everything would just look purple. If you're far enough away, your eye does not perceive the individual grains of sand. When they're all mixed together, it would look like one mass of purple sand. We know that if you look very, very closely, the individual grains still maintain their identities. Every grain is either blue or red. The grains have not become purple, but because we've mixed them together, the substance now looks purple. There's a property of the sand that it now is all mixed together. It is high entropy. But when we increased the entropy by mixing it, we did not change the substance, we merely rearranged. That's underlying Boltzmann's idea that entropy can be thought of as a property of the arrangement of the atoms, not as a substance all by itself. To see this at work in a real situation, consider the example we will be using over and over again, which is a box of gas, but a box of gas with a partition. So you have a box of gas divided in two. There's a dividing thing in the middle of it, but there is a tiny hole in the partition. So most of the time, the atoms in the gas just bounce around inside whichever side they're on, the left side or the right side. But rarely, but occasionally, an atom will go right through the hole and pass from one side to the other. Now, the nice thing about this example is it's perfectly obvious how it will behave. You don't need science, you don't need equations to think very hard and figure out what the box of gas will do. Imagine that you have this partitioned box of gas, and you start with all of the gas on one side. So there's a little hole in the middle. Particles from the one side, let's say the left-hand side, will gradually leak over to the right-hand side. If you start with all the atoms on the left, no atoms on the right, and you wait long enough, the box of gas will equilibrate. Just like the heat equilibrates when you bring a hot object close to a cold object, this empty box next to a full box equilibrates until there's half the gas on the left-hand side, half the gas on the right-hand side. It is intuitively clear to us that entropy increases during this process. Why is that true? Because we imagine that that's the direction in which the gas will naturally evolve. The gas will even itself out until it's 50-50 left and right, and once it's there, it will not naturally go back. You can imagine it going back, but it's not going to naturally happen. That's an irreversible process. Entropy has gone up. So we can consider this a little bit more quantitatively. I told you we're going to be taking things seriously in this lecture. We're going to work our way up to Boltzmann's equation defining the entropy. So imagine you have this box of gas, and to make things definite, imagine there are 2,000 particles of gas. So this is obviously more than a handful, but it's much, much less than Avogadro's number. This is much, much less than a truly macroscopic amount. But what we'll see is this is more than good enough to see the effects of entropy and the averaging process of having so many molecules. So you start with 2,000 atoms or molecules, and you put them all on the left-hand side of the box. And let's just say, to make things definite, that every atom has a 1% chance per second of going through the hole, of flipping sides from left to right. And it doesn't matter whether the atom is on the left or on the right. If it's on the left, it has a 1% chance of going to the right. If it's on the right, it has a 1% chance of going to the left. So what happens in this circumstance? Obviously, if you start with all the atoms on the left, they will gradually diffuse to the right until they even out. If you're the kind of person who likes to write little computer programs, you can easily program this yourself, draw the picture, and watch what happens. After only about 200 seconds, after a few minutes of these atoms going back and forth, you can't tell the difference between the left-hand side of the box and the right-hand side of the box. It looks like there's the same amount of atoms on either side. So clearly the entropy has gone up. Clearly this is an irreversible process. So what we'd like to do is to describe that process quantitatively. We don't want to just draw pictures of it and look at it happening. We want to write down equations that we can solve and predict what will happen in any circumstance. So that's exactly what Boltzmann did. He tried to figure out how many combinations there would be of atoms in one configuration versus another, and showed that our intuitive notion of high entropy corresponds to many different arrangements of a particular configuration. So for example, in our box of gas with two sides and 2,000 atoms, let's say we only keep track of whether an atom is on the left-hand side or the right-hand side. So we're not keeping track of the specific position and momentum of every atom. It's just like the real world. We can more or less see how full the left-hand side is, more or less see how full the right-hand side is, but we don't see every atom. Our task is to count how many arrangements look one way versus another, and then apply to that counting some formula that lets us calculate the entropy. So let's actually do that. How many ways are there to have all of the atoms on the left and none of the atoms on the right? The answer is very simple. There is one way. You know that all the atoms are on the left, none of the atoms are on the right. That's all you need to tell me. There's no other way to do that. It becomes interesting when we have 1,999 atoms on the left and one atom on the right. How many ways are there to do that? Well, basically, you start with the 2,000 atoms on the left and you take one of them, you move it to the right. How many ways are there to take one atom? There are 2,000 different ways, because there's 2,000 different atoms you could have chosen. Therefore, there are 2,000 ways to get one atom on the right, 1999 on the left. You see that there are already many more ways to get one on the right and 1999 on the left than there were to have 0 on the right and 2,000 on the left. That's the trend we're going to see. As the numbers become closer on the left and the right, the ways that you can do it, the number of combinations that look like that, increase very rapidly. Let's ask what happens if you have 2 atoms on the right and 1998 atoms on the left. You might think, well, there were 2,000 ways to choose one atom, and then there's 1999 ways to choose another atom. So the number of arrangements is 2,000 times 1,999. But that's cheating a little bit, because you have 2 atoms and it didn't matter which one you chose first and which one you chose second. The right number of arrangements is 2,000 times 1999 divided by 2, because it doesn't matter whether you took one atom first or the other atom first. The answer is almost 2 million different arrangements. It's 1,999,000 different arrangements, much larger than the 2,000 arrangements you had with 1 on the right and 1999 on the left. So don't worry, I'm not going to do this for 3 or 4 or 5 atoms on the right. The point is that there is a formula. There's a mathematical procedure for counting the number of arrangements. You are not surprised to learn that the maximum number of arrangements has 1,000 atoms on the right, 1,000 atoms on the left. You might be surprised to learn that the number of such arrangements is greater than 2 times 10 to the 600. That's 2 followed by 600 zeros, an enormous number. Just for calibration purposes, the total number of particles in the visible universe is only 10 to the 88th. So 10 to the 600 is a number that we would never come into contact with in our everyday lives, but that's the number of ways you can have 1,000 atoms on one box and 1,000 atoms in the other. Then as you continue to move atoms from the left to the right, the number of arrangements goes down again. Once you have no atoms on the left and 2,000 on the right, that's again a unique configuration. There's only one way to do that. So the number of arrangements is small when there's an imbalance between left and right. The number of arrangements is large when there's a balance between left and right. Our intuitive notion is that the entropy is higher when things are balanced, lower when it is unbalanced. That gave Boltzmann the idea that what the entropy is really doing is just counting the number of arrangements. That is to say, the entropy tells us the number of microscopic arrangements of a set of atoms that look indistinguishable to our macroscopic perception. We don't see every individual atom. All we see is the total number of atoms on the left and the total number of atoms on the right. So what Boltzmann says is that if you count the number of arrangements, that tells you the entropy. He doesn't say that the number of arrangements is the total entropy. That is too good to be true. Boltzmann's formula is that the entropy is proportional to the logarithm of the number of indistinguishable states. That is to say, Boltzmann gives a formula for the entropy in terms of the number of ways we have to rearrange the system which don't change its macroscopic properties. His formula is S. The entropy gets the letter S because E was already taken up by energy. So the entropy is S equals K log W. This is such an important formula, it is engraved on Boltzmann's tombstone, which you can visit in Vienna. I always tell my physics students that Boltzmann has achieved every physicist's dream. He has an equation on his tombstone, and they should be thinking in their physics career, what is the equation that will someday go on my tombstone? Boltzmann's equation, S equals K log W, is not that hard to understand. S is the entropy. K is Boltzmann's constant. It's just a constant of nature. It's a sort of proportionality constant out there that translates from the number of states to the entropy of the system. W is Boltzmann's notation for the number of ways we can rearrange things. So W in our box of gas was 1 or 1999 or 2 times 10 to the 600, etc. And log means the logarithm. It's a way of going from the actual quantity to a more manageable way of dealing with that quantity. So we have to understand what a logarithm is if we're really going to wrap our heads around Boltzmann's formula. Boltzmann is telling us that the entropy is proportional to the logarithm of the number of rearrangements. The logarithm is basically the power to which you would raise the number 10 to get the number you want. So that probably is not immediately clear if you're not already familiar with logarithms. The point is that the logarithm of 10 is equal to 1. Why? Because in order to get 10, you raise 10 to the power 1. 10 to the 1 equals 10. The logarithm of 10 is therefore 1. The logarithm of 100 is 2, because 10 to the 2 is 100. The logarithm of 1,000 is 3, because 10 to the 3 is 1,000, and so forth. The logarithm of 1 is 0, because 10 to the 0 is 1. It's easy if you're taking the logarithm of a power of 10, like 1,000 or 10,000 or whatever. Logarithm of 1,000,000 is 6, no problem at all. But you can also define the logarithm for every number in between. You can take the logarithm of 2, of 5, of pi, whatever you want. Basically, the logarithm is a function. It is small when the number you're taking the logarithm of is small. In fact, it's negative when the number is less than 1. The logarithm of 1/10 is -1, because 1/10 is 10 to the -1. The logarithm is small when x is small. It is large when x is large. But you'll notice that the logarithm grows more slowly. We multiply 10 by 10 by 10 by 10. We only add to the logarithm. We go from 0 to 1 to 2 as the number we're taking the logarithm of goes from 1 to 10 to 100. So the log tells us the number of ways we can rearrange it, but it tells us in a more compact and manageable form. So Boltzmann's equation says, if you want to know the entropy of something, count the total number of combinations that look the same, take the logarithm, and then multiply by this constant of nature, which I'm going to call Boltzmann's constant. He didn't call it Boltzmann's constant, but in his honor, that's what we call it now. So go back to our box of gas. Remember, the lowest entropy configuration has 2,000 particles on the left, 0 on the right. The number of combinations that look like that is 1. The logarithm of 1 is 0. So literally, the entropy of that configuration is 0. It's the most orderly configuration you can have. Its entropy is the lowest number you can ever get, 0. When there was 1 atom on the right and 1999 on the left, there were 2,000 combinations like that. The logarithm of 2,000 is 3.3. When there was 1998 on the left and 2 on the right, you had almost 2 million combinations, and the logarithm of that number is 6.3. Once you get all the way up to 1,000 on the left, 1,000 on the right, absolutely equal, highest entropy configuration, you had 2 times 10 to the 600 combinations. The logarithm of that is just 600, 600.3 to be precise. So you see how much easier it is to write down the logarithm than to write down the actual number of combinations. This huge number of combinations, when you have 1,000 on the left and 1,000 on the right, 2 times 10 to the 600, once you take the logarithm of that, it's just 600.3. That's much easier to deal with. Now, to be honest, the reason why Boltzmann says that the entropy is the logarithm of W, of the number of microscopic arrangements, rather than W itself, is not just because the logarithm is smaller and therefore easier to deal with. Remember, Boltzmann came along when entropy had already been defined. Clausius had given us the notion of entropy. He had a definition of it that was very specific about exchanging heat. Boltzmann wanted a much more general definition, but he still wanted his general definition to match with Clausius's specific definition in the same arrangement. So one of the properties of entropy as it was already understood is that if you take 2 boxes of gas, or 2 objects, one box has a certain entropy and the other box has another entropy, and you put them together to make one larger system, the total entropy is the sum of the entropy in the first thing plus the entropy of the second thing. That was something that was already known about entropy. The entropy of the total is the sum of the individual entropies. But Boltzmann wanted to define the entropy in terms of the number of arrangements. And when you take one box and connect it to another box, you open up many more ways to arrange the individual particles. Now you can move particles between the 2 boxes. So the number of arrangements is not just the sum of the total number you had before, it's the product. You take the number of arrangements you had in one box and you multiply it by the number of arrangements you have in the other box. So if you tried to define the entropy as the total number of ways you could arrange the atoms, that would give you a wrong formula for the entropy of adding 2 things together. It would multiply them rather than add them. The magic of the logarithm is it fixes this problem. The logarithm has this wonderful property that the logarithm of a product is the sum of the logarithms. So consider the logarithm of 100. The logarithm of 100 is 2. 10 to the 2 is 100. We can also write it as the logarithm of 10 times 10, because 10 times 10 is 100. So the log of a product is the sum of the logarithms. That means that the logarithm of 10 times 10 is the logarithm of 10 plus the logarithm of 10, which is 1 plus 1, which equals 2. It's the right formula. What Boltzmann realized was that putting the entropy proportional to the logarithm of the number of arrangements preserves the nice property that the entropy of 2 systems added together is the entropy of each system added to the entropy of the other system. So there's a lot of details here that we're not going into. For example, I said that the logarithm is the number to which you raise 10 to get the number you want. You can choose any number to do the raising. You can take the logarithm base 2, that's the number you raise 2 to get the number you want. You can take the logarithm base 12, whatever you want. In science, we usually use either base 2 or base e, this weird irrational number, Euler's constant, is very convenient for calculus and physics. But for this course, we're just going to take the logarithm base 10 because we all know that 10 to the power 3 is 1,000 and so forth. Now, a crucial role in all of these considerations is that we're taking microscopic configurations of atoms and treating them the same. We're using the phrase over and over again, a certain arrangements of atoms look the same macroscopically. We say that means they are in the same macro state. So what we're doing is we're distinguishing between the micro state of a system, which is the exact Laplacian state, the thing you would need if you had all of the positions and momenta to predict the future and to retrodict the past. That's the microstate. If you knew the microstate, then the evolution of the system would be perfectly reversible. You would be able to use the laws of physics, if you were Laplace's demon, to go forward and backward in time. But we don't know the microstate. You look at a glass of water with an ice cube in it, you don't see the exact microstate of every atom inside the glass of water. You know that it's a glass of water, it has a certain temperature, maybe there's an ice cube in there. We call that information the macrostate. We define ahead of time what it is we can macroscopically observe, and two arrangements of atoms that look the same according to our macroscopic observations, we put into the same macrostate. This process is coarse graining. It says we take all the possible states you could have and we chunk them up. We chunk them up into microstates that look the same macroscopically. We call the set of all those microstates the macrostate. What Boltzmann's entropy tells us is that the entropy of an individual configuration of particles is the logarithm of the total number of other configurations in the same macrostate. We coarse grain by some observations, we calculate how many particles, how many arrangements look the same, take the logarithm, that's the entropy. Now there's obviously a step here that requires some thinking. How do you do the coarse graining? How do you decide what I can macroscopically see and not? What if there is some alien who comes along who has much better vision than I do and is able to see the positions and the velocities of every molecule in the glass of water? Would the alien coarse grain differently? It seems a little arbitrary. Imagine that you're playing pool one day, playing billiards, and you've scattered the balls across the table, and a friend of yours walks by and says, "Wow, that's an amazing configuration of billiard balls." And you look and you say, "What? I don't see anything special about it. It's just randomly scattered across the table." And your friend says, "Yes, but the particular place where the 8-ball is and the 3-ball is, how unlikely it was that it would end up in precisely that configuration." You would not be impressed by your friend's purported amazement. You know that they would not have predicted ahead of time that that particular arrangement of billiard balls was special. Every individual arrangement of billiard balls on the pool table is individually unlikely. But we treat different configurations the same if they look more or less the same to us. We would say, yes, that was a good break and all the balls are scattered across the table, or that was pretty lame and they're all clustered around one pocket or something like that. We decide ahead of time what we can measure macroscopically. We use that definition to do the coarse graining. For example, when it comes to atoms, it's not simply an accident that when we look at a box of gas or a glass of water, we can see things and measure things like the temperature and the density and so forth. This is not arbitrary. You could imagine picking other features of that collection of molecules, but they would be harder to measure. The way we coarse grain the real world depends on what is actually easy for us to measure. And even though aliens might be better at measuring some things than we are, they would not measure different things than us. That's because it's the laws of physics that basically give us what is easy to measure. If you build a machine, it would be very, very hard to build a machine that would actually be able to look at the position and velocity of every molecule of water in a glass of water. It is not difficult to build a machine that measures the density or the temperature and so forth. The way that we coarse grain the real world is very natural given how the laws of physics work and how we actually measure things in reality. So once this is all in place, once you take Boltzmann's program and take it seriously, we have an understanding of how entropy works at a quantitative level. We take all of the ways that a state can be, all the microstates of some system, a box of gas or a glass of water, all of the different ways that the individual molecules can be arranged. We divide up that space of states, that set of all possible configurations, into macrostates. We say, these look alike to me, these look alike to me, and so forth. We calculate in each macrostate how many microstates are there. We take the logarithm of that number, and that is the entropy. So given that understanding, it makes sense to us now why entropy increases. Boltzmann's definition of entropy is that high entropy means there are more ways to arrange things that way. Low entropy means there are fewer ways. So therefore, given a system that has a low entropy, if you just let it evolve, let it change its state over time without tricking it, without conspiring it or setting it up in some subtle way, it will naturally move to a higher entropy configuration simply because there are more ways to be high entropy than to be low entropy. In fact, there are many, many, many more ways to be high entropy than to be low entropy. So Boltzmann explains for us why entropy increases toward the future. There's simply more ways to be that way. He also makes the difficulty very explicit. Why was the entropy lower in the past? There are fewer ways to be low entropy. So this puzzle, why was the entropy lower in the past, becomes not just puzzling, but a real conundrum. We're going to have to work hard to offer an explanation for this phenomenon. We've alluded several times now to quantum mechanics, the theory of the world, the model of physics that was developed in the first half of the 20th century and applies to the really tiny world of subatomic particles. Quantum mechanics is really a way of doing physics, a way that replaced the Newtonian classical world. And even though I've said it and other people have said it, it's not really completely accurate to say that quantum mechanics describes the subatomic world. The truth is, quantum mechanics describes the whole world, the small and the very, very large. The good news is that in the very, very large scales, Newtonian mechanics also works. So when you go through your life, when you go from here to the moon in a rocket ship, or if you just get in your car and go shopping, you don't need to know quantum mechanics, but that doesn't mean that quantum mechanics isn't applying. It just means that you're in a realm where the predictions of quantum mechanics are the same as the predictions of Newtonian mechanics. So Newtonian mechanics gets you through the day. But quantum mechanics is not just a theory of the very small. It's only that when we look at things that are very small, the predictions of quantum mechanics deviate from the expectations we would have from Newtonian mechanics, and it's quantum mechanics that gets it right. Quantum mechanics is the correct theory of reality as far as everything we know about the universe is concerned. So we need to understand what the implications of that theory are for our understandings of the arrow of time. The first step is to figure out that there's certain folk beliefs about quantum mechanics that are not correct. Certain things you will hear if you linger on the wrong street corners about what quantum mechanics says that we want to remove from your mind. So the first one is the idea that quantum mechanics is a theory of quanta. That is, a quantum is just a discrete packet of something. Quanta are just more than one quantum. And you might get the impression from the name that quantum mechanics says that everything comes in discrete packets. That is simply false. Quantum mechanics is a little bit more complicated than that. It says that some things come in discrete packets. For example, if you have an electromagnetic field, a wave in an electromagnetic field, and you look at it, if you look at it carefully enough, you see individual particles called photons. But there are other things in quantum mechanics that are not discrete at all. Time, as far as we can tell, is not at all discrete in quantum mechanics. So the name quantum mechanics is a little bit misleading. Don't let it force you into thinking that it implies things really come in discrete jumps. The other potentially confusing thing about quantum mechanics is the role of uncertainty. There's something called the Heisenberg uncertainty principle, which is absolutely central to understanding the implications of quantum mechanics. Quantum mechanics makes the following very careful statement, that if you want to predict the future outcome of an experiment, based on the current state of the world, you can only predict the probability of getting a certain outcome. You cannot predict with 100% certainty that any particular outcome will ever attain. It's not that you're not good enough to do it. Quantum mechanics says that it cannot be done. So this leads to a sort of hand-wavy uncertainty kind of thing where you say, well, quantum mechanics doesn't let us say what will happen. Quantum mechanics says what will happen extremely precisely. It's just that the language it speaks is in probabilities, but those probabilities are not up for grabs. They are predicted to extremely high accuracy by quantum mechanics. It turns out that our understanding of particle physics based on quantum mechanics is the most precise theory ever invented. So quantum mechanics predicts probabilities. That doesn't mean that everything in quantum mechanics is simply uncertain. So to understand how quantum mechanics works, it's useful to contrast it with classical physics. When we talk about Newtonian mechanics or classical mechanics, these mean the same thing. It's the vision of the world that was given to us by Isaac Newton. And it's a vision of the world that was expanded on by Newton's followers in subsequent years, but it was still always within the framework of quantum mechanics, of classical mechanics, sorry. When Maxwell figured out how to marry electricity and magnetism together, his theory of electromagnetism was still a classical theory. When Einstein built the theory of relativity, the special theory and the general theory, those were still classical theories. Quantum mechanics is a different way of doing physics that does not fit with how we think of electromagnetism according to Maxwell or relativity according to Einstein. You have to start from scratch, and you can get things right, but you have to work in a different language. So the language of Newton was what we talked about in the context of Laplace. You give me the state of the world right now, by which I mean the position and velocity of every particle in the world, and I can use the laws of physics to predict what will happen in the future and to figure out what happened in the past, to retrodict the past. The laws of physics in Newtonian mechanics are deterministic. They tell me what will happen and what did happen, and information is conserved along the way. Now, even in Newtonian mechanics, we might have uncertainties in our predictions because we have uncertainties in our measurements. If you don't know exactly the positions and the velocities of everything in the world, then you cannot make precise predictions. But there was always the possibility that if your measurements were better, your predictions would be better. And your measurements could, in principle, be infinitely good, and then your predictions would be infinitely good. Quantum mechanics is a different theory and a much richer one. Quantum mechanics, the way that it really differs from classical mechanics, is in the role of what you can observe. In classical mechanics, what you can observe wasn't even really something we worried about very much. The state of a system was defined by its position and its velocity, or the position and velocity of all of its parts, and you could measure the position and the velocity of all of its parts. There would be some uncertainty if your measurement apparatus was not very good, but you could improve it just by making more and more precise measurements. The difference between quantum mechanics and classical mechanics is that just because something exists doesn't mean you can observe it. So in quantum mechanics, you don't define a system by giving positions and velocities. There are no such things as positions and velocities. In quantum mechanics, what the world is described by is something called a wave function. It's also called a quantum state or a quantum amplitude. It's basically a set of pieces of information that answers the question, if I were to observe a certain thing, what is the probability I would get a certain answer? For example, I know that I have an orange, but I don't know exactly what state the orange is in. The orange has a wave function. The wave function will tell me if I look for where the orange is. The wave function says what is the probability that I see it in one place or that I see it in some other place. This is not a matter of our ignorance. It's not just that quantum mechanics doesn't let us know where the orange is. The point is that quantum mechanics says there is no such thing as where the orange is. It's not because we're not good enough. It's because quantum mechanics doesn't let us go from the state of the universe to a prediction with a perfect match. There are always probabilities that get in the way. So the way that we talk about this is to say that objects exist in superpositions of classical properties. In other words, there really is no position of the orange. There is a possibility that we would find the orange here, and a possibility that we would find the orange there, but it's not in either one position or the other. It's in both. It's in a superposition of both possibilities. The wave function tells me how much of the superposition is here, how much is there, and therefore how much probability I have of seeing it in one position versus the other. The other great thing about the wave function is that it can be a negative number. Just like a wave on the ocean means sometimes the water is above its typical height, sometimes it's below it, a wave function can be a positive number or a negative number. That means that you can contribute to the wave function in different ways, and they can interfere with each other. A positive contribution can cancel a negative contribution. This leads to really interesting phenomena in particle physics, where, for example, you can add a new particle to your theory that gives some other particle a new way to interact, and the net effect is that the probability of interaction goes down, because that new addition was a negative number in the wave function. We get the probability from the wave function by squaring it. If you square -1, you get +1. So the probabilities are always positive, but the wave function can be positive or negative. There is no connection between this way of thinking and classical mechanics. There's no negative numbers for the probability of seeing something in classical mechanics. There's no negative numbers for the probability in quantum mechanics either, but the machine you use to make the probability, the wave function, can be negative. You have to square it to get what the probability is. So when you put all of this together, when you think about reality in this way, that it's made of wave functions, it's not made of positions and velocities, remarkable consequences follow. Some of those consequences are as simple as certain things are quantized. For example, in an atom, the energy levels that an electron can be in come only in discrete quantized pieces. You can't get any possible energy for the electron around an atom. You only get certain possibilities. That has crucial implications for how we live our lives. For example, if you close your eyes, it gets dark. This is not a surprise to you. You say, well, there's no light coming in. But if you look at it carefully, there is a tremendous amount of light even in your closed eye. Because you are a warm body, you are giving off infrared radiation. The amount of infrared radiation inside your eye is much greater than the amount of light you get from the external world. But because it's lower energy per photon, because the infrared light has longer wavelengths and less energy per particle, even though there's a lot of infrared photons in your eye, they're not enough to make you see anything. And that's because of quantum mechanics. To get the chemistry in your eye to be excited and to say, I'm seeing something, requires individual photons of high energy. You can see visible light, you can't see infrared light. If you could see infrared light, it wouldn't matter to you whether your eyes are open or not. You would be blinded all the time. You can thank quantum mechanics for the fact that we can see the world and apprehend it, and everything goes dark when you close your eyes. Now, as far as we know, this quantization does not extend to space and time itself. There might be theories in the future that do quantize space and time. One of the problems with quantum mechanics is that we have not yet been able to reconcile it with relativity. Not special relativity, that was Einstein's first theory, but his next theory, general relativity, which we'll talk about in great detail, his theory of gravity and the warping and changing of space and time. General relativity doesn't play nice with quantum mechanics, and the search for a theory of quantum gravity is one of the major goals of modern physics. If we get there, it may be the case that time and space become quantized. But it may also be the case that they do not. We just have to say that we don't know the answer to this. The name quantum mechanics is just not a very good name. The major difference between quantum mechanics and classical mechanics is in the difference, the relationship between what exists and what you can see. In classical mechanics, you can see everything that there is. If you look hard enough, you can measure the position and velocity of every particle. In quantum mechanics, what there is the wave function. But what you see when you look is something different. You don't see the wave function. For example, that orange that we had, that could have had one position or another. It doesn't have either one until I look at it. So the orange has a wave function that describes the probability I will get a certain answer when I look at it. Before I look at the orange, it is truly in a superposition. The wave function describes it being in more than one place. It is when I look at it, when I make that observation, that the reality of the orange collapses to one possibility. You see the orange in one position and not in a superposition. What you see is different than what there is. This is a bizarre and disturbing feature of quantum mechanics, that reality seems to change when you look at it. This is something that has led to all sorts of bad popular science saying that our interactions with the world bring reality into existence. It's not like that. It's still the laws of physics are being obeyed. But the problem is the laws of physics are really disturbing to us. They don't quite make sense to us. We're saying that the rules by which physical objects evolve are different when we are looking at them and when we are not looking at them. That is not an exaggeration. That is how quantum mechanics is taught in every undergraduate quantum mechanics course. Now, many of us, including myself, are unsatisfied with this way of looking at things. We think that this is not how reality works. This is just a reflection that we do not yet understand it. This is called the measurement problem in quantum mechanics. The rules of quantum mechanics, as they are written down, say that there's one way that things evolve when we're not looking at them, another way that they evolve when we look at them. But then you ask yourself, what counts as an observation? When am I observing it? What if it's a robot that is observing it? What if it is my cat that is observing it? What if it's just a rock that falls on it? When does it become the case that reality collapses into one configuration? We call this collapse literally the collapse of the wave function. So the question is, when do wave functions collapse? What counts as a measurement? The short answer is we don't know. We don't have a reliable answer to the measurement problem. We don't know what the correct way of thinking about it is. But one of the puzzles that makes us wonder is the fact that wave function collapse seems to be irreversible. If it's true that the orange is spread out in its wave function, it could be here, it could be there, it could be there, but when I look at it, I see it in one location, then if I look away and look back again, it's still in that location. So it was spread out before I looked. After I looked, it's localized into one position. What this means is that information seems to be lost. If I look at the orange and I see it in one position, I know it's there now. I know if I look again, it will still be there, but I don't know where it came from. I don't know what the wave function of the orange was before I looked. There's a huge number of possible wave functions, of possible quantum states, all of which have some amplitude, some probability that I will see the orange there, and once I see it, that's where it is. I cannot reconstruct what the wave function was before I did my measurement. So that sounds like true irreversibility. That sounds like an arrow of time. And this is why when we talk about the fact that the fundamental laws of physics are reversible, we often have to add a little footnote saying, except for quantum mechanics, that's not so clear. But we can ask ourselves the question, is this once again quantum mechanics' fault, or is this our fault for not understanding quantum mechanics as well as we should? So way back in the 1960s, this question was investigated very carefully by three physicists, Yakir Aharonov, Peter Bergman, and Joel Leibovitz. And the question they ask is the time asymmetry of wave function collapse really the fault of quantum mechanics, or is it our fault for setting up the question in a certain way? And of course, I'm stating this in a leading fashion. What they argued was that it is our fault. It is not the fault of quantum mechanics. They said that the reason why we think there's time asymmetry in wave function collapse is because we're asking a time asymmetric question. If we asked a symmetric question, we would get a symmetric answer even in quantum mechanics. So what Aharonov, Bergman, and Leibovitz, ABL for short, what they said was, think about how we usually work quantum mechanics. We prepare a system, it has some wave function, it has a probability for being seen in different positions, and then we observe it, and we record the answer to our observation. So in other words, there's an initial condition followed by an observation. What if we tried to do that symmetrically? So first setting it up and then observing is one way of doing it. We could also set it up, observe, and then set it up again. So this sounds weird. What we're saying is we have a state for the system to be in, we observe it, and then after the observation, we insist that it be in some particular state. So we prepare it, we observe it, and then what we call post-selection. We only include those times that the final state of the system is something that we chose ahead of time, just like the initial state. Now, this is not something that we do ordinarily because we don't have access to the future. We have access to the past. So we set things up in the past and then we make an observation. What ABL found is that if we insist on asking questions that are symmetric with respect to the past and the future, then the formula for predicting the probability of quantum mechanical experiments is itself symmetric. In other words, quantum mechanics treats conditions set up before the experiment and conditions set up after the experiment in precisely the same way. There's no intrinsic time direction in quantum mechanics, it's just that we ask questions that presume a direction of time from the start. So you might be a little bit leery about this. How do you, after all, set up a condition after you've done the experiment? Well, the answer in quantum mechanics is you just measure the object twice. You measure it in what you call the measurement, and then you measure it later on. And if the state at the end is not the state you want, you throw away that experimental result. So you set up the particle, for example, with some position or some wave function. You evolve it a little bit. You observe it. You let it evolve more. And then you insist that it be in some position at the end of the day. You can do that by measuring its position, by doing this experiment many, many times, and when it was, at the end of the day, in the position you wanted it, you keep that experimental result. If it is anywhere else, you throw it away. You only keep the experimental results that agree with your final boundary condition. These experiments have been done. People have checked the formula derived by ABL, and they found that it agrees with experiment. The conclusion is that quantum mechanics doesn't impose time asymmetry on the world. The world imposes time asymmetry on quantum mechanics. The reason why wave function collapse seems to be time asymmetric to us is because we have asked a time asymmetric question. We set up initial conditions and then make an observation, rather than making an observation and then imposing final conditions. So why do we do that? Why is it that we always set up the system and then observe it rather than the other way around? The answer comes not from quantum mechanics, but from our knowledge of the world. Remember, we remember what the world was like in the past. We don't remember the future. So if we set something up and then let time pass and then do the experiment, when we do the experiment, we can still remember how we set up the apparatus. You can't do that for the future because we don't have a memory of the future. Why don't we have a memory of the future? Ultimately because the entropy was lower in the past. This is an assertion that I've made before. We haven't justified it yet. We'll have a whole lecture in the future where you will learn why the reason you remember the past and not the future is because entropy used to be lower in the past. The future is harder to predict than the past was because in the past the entropy was smaller. So the lesson of this is that the arrow of time is not explained by the time asymmetry of quantum mechanics. The time asymmetry of quantum mechanics is explained by the arrow of time. The reason why wave function collapse is irreversible is the same reason why the melting of an ice cube is irreversible, because we know more about the past than we know about the future. This doesn't mean that there's nothing to worry about. We still need to ask about what about conservation of information. It's not like the ice cube where information didn't seem to be conserved because we can't keep track of it, right? We can't see the position and momentum of every water molecule in the glass of water, but in the quantum mechanical system, it seems like we can. We have a single particle or a single orange. We know everything there is to know about it. Why can't we just keep track of all the information in the quantum system as time goes on? This is a very good question, and again, this is a source of controversy among people who work in quantum mechanics as professional physicists. The naive answer is that in quantum mechanics, information is not conserved. If I look at an orange and I see it in a particular place, I don't know what the wave function was before. It appears to be gone. This whole controversy is what drives the philosophical field of interpreting quantum mechanics. So people argue over which is the right way to think about quantum mechanics. What is the right interpretation to impose upon this weird way of thinking about the world? The leading interpretation, in the sense that most people who do physics accept that it is probably true, is called the Copenhagen interpretation. It is what was developed by Niels Bohr and Werner Heisenberg and other of the founders of quantum mechanics back in the 1920s and 30s. And the Copenhagen interpretation says something very simple. It says that there are simply two different ways for quantum mechanical systems to evolve. There is what happens when you're not looking at it and what happens when you look at it. The collapse of the wave function, according to the Copenhagen interpretation, is real, it is true, and it is irreversible. Collapse happens when a macroscopic classical system, like a person or a cat or a robot, interacts with a small-scale quantum mechanical system. The problem, of course, is this interpretation makes no sense whatsoever. So I said that most working physicists believe in it, but I don't think that they should believe in it. What you will find is that in the subset of physicists who think hard about quantum mechanics, nobody believes in the Copenhagen interpretation. It's basically a stopgap measure. It's sort of a kludgy way of thinking about the world that is good enough as long as we don't do sufficiently careful experiments to distinguish between what happens on small scales and what happens on large scales. Remember, I started the lecture by saying that quantum mechanics is not just a theory of the very small, it's a theory of the whole world, including the very large. Quantum mechanics should apply to me and you as well as it applies to individual electrons. If that is true, then the Copenhagen interpretation can't be right. The Copenhagen interpretation relies on the fact that you and I are not quantum mechanical, that we are classical things. But no one really believes that the real world is made of small particles that obey quantum mechanics, and that then when you take all those small particles and put them together to make a human being, they suddenly stop obeying quantum mechanics. The Copenhagen interpretation doesn't have answers to questions like, why is the behavior of the world different when we look at a system than versus when we don't? What really counts as looking? Does a virus interacting count as looking? What is the dividing line between the classical world and the quantum world? So there's another interpretation of quantum mechanics. There's many, actually. But the leading alternative to the Copenhagen interpretation is called the many worlds interpretation. The many worlds interpretation says that there is no separate way of evolving when you are looking at a system versus when you are not looking at a system. There's only one way the world evolves, and that is in accord with the rules of quantum mechanics. The difference is that the many worlds interpretation takes seriously the fact that you, the observer, are a quantum mechanical system. Not just the thing you're looking at, but the observer is just as quantum mechanical as everything else. So not only does an orange have a position it could be in, or multiple different positions, not only does an electron have the possibility of being found in different places in the universe, but you, the observer, have different possibilities, and they are described by a quantum mechanical superposition just as much as the state of the electron is. So what does that mean? What that means is that when I, as a classical observer, interact with the quantum mechanical particle, the right way to treat it is not to treat me classically, but to think about my wave function. My wave function interacts with the wave function of, let's say, the orange. So the simple-minded way that we talked about it before was, I look at the orange and it could have been in two positions, but I will only ever see it in a single position. What happens according to the many worlds interpretation is that I look at the orange and I evolve into a superposition myself. There is a version of me that sees the orange in one place. There's another version of me that sees the orange in another place. And these two versions live in separate worlds. They live in separate universes. So this is a theory of multiple universes. Every time that two quantum mechanical systems interact with each other, the wave function doesn't collapse, it splits. It splits into alternative versions of reality, all of which are equally real. Now this story sounds a little outlandish. People don't like the many worlds interpretation, both for good reasons and bad reasons. One of the bad reasons is that they say, that's an awful lot of universes out there. Every time we observe a quantum mechanical system, a whole new universe comes into existence. The reason why that is a bad way of thinking about it is that the world is not weighted down by the number of universes that it has. The many worlds interpretation says there is one wave function for the whole universe, and it simply evolves according to one equation. One wave function, one equation. That's the simplest possible theory we can write down. It is true that that wave function describes many, many universes, but it's still the same amount of information contained in the same wave function. That's one of the benefits of the many worlds interpretation. Another benefit is that the evolution of the wave function is completely deterministic. There's an equation, Schrödinger's equation, written down by Erwin Schrödinger, another one of the giants of the early days of quantum mechanics, that tells you how the wave function evolves. In the many worlds interpretation, the evolution of the universe is just as deterministic and reversible as it was for Laplace and Newton. If you tell me the wave function of the universe now, and you tell me Schrödinger's equation, I can evolve that wave function forward in time, I can evolve it backward in time, and no information is lost. You might ask why it seems that information is lost when wave functions collapse, and that's because I don't know where I am in the wave function. There are different copies of me in the many different universes that are produced. That's why information seems to be lost. It's not that entropy is increasing. It's not that the fundamental laws of physics are truly irreversible. It's just that my ignorance increases because I don't know where I am. This is a complicated question, whether or not this fairy story can actually apply to reality. It seems outlandish on the face of it. But the more you look at it, the more logical it becomes, and the better it fits in with other things we think are true about the universe. For our present purposes, the important thing is that understanding quantum mechanics reveals that there are true mysteries to which we don't know the answer. Richard Feynman once famously said, "It's not that hard to understand general relativity, but I can safely say that nobody understands quantum mechanics." These issues of interpretation are very real. But for our immediate purposes, all we need to know is quantum mechanics does not explain the arrow of time in our universe. It does not explain why entropy increases toward the future. It's easy to explain why entropy increases. The real mystery is why entropy was lower in the past. Quantum mechanics doesn't help with that. To understand that, we're going to have to think a little bit more carefully. In the last lecture, we talked about the reversibility of the fundamental laws of physics, and how that raises a puzzle for our understanding of the arrow of time. How can it be true that the deep down laws are perfectly reversible, there's no difference between moving toward the future and moving toward the past, and yet the macroscopic laws, the world that we phenomenologically see around us, so strongly picks out a direction of time? However, our notion of the fundamental laws of physics on which we based that tension came from Isaac Newton, what we call classical mechanics, the whole system of Newtonian physics that says that there are positions, there are momenta, and if you knew the positions and the momentum of every individual atom, you could predict things arbitrarily far into the future and retrodict them into the past. Now, we know a little bit better than that. We know that the atoms of which real matter is made do not, strictly speaking, obey Newton's laws of physics. We've changed the laws of physics since Newton's time. And you may ask, does that change have an important impact? We now know that there is quantum mechanics. We now know there is particle physics. Has that affected our notion of reversibility and the arrow of time? So the bad news is that it has, but in a very subtle way. And I don't like subtlety. I like things that are very, very simple to understand. The point is that quantum mechanics and particle physics change the story of reversibility, but not in a way that helps us explain the arrow of time. So to be honest, to be completely correct, we need to understand exactly why quantum mechanics and particle physics are not fully reversible, and yet they don't help us explain why the past is different from the future. So first, let's look at particle physics. In the next lecture, we'll look at quantum mechanics, but right now let's take that for granted. Let's talk about the different interactions that govern our physical world. Particle physicists say that we have four interactions, four forces of nature. There are two of them that are long range and two of them that are short range. So to a particle physicist, a force is not like friction or centrifugal force or something like that. It's one of the fundamental basic interactions that let different particles talk to each other, bump into each other and go their own separate ways, or pull each other together. The long-range forces are the ones we know about in our everyday lives. There's gravity. Gravity pulls us to the Earth. It keeps the moon moving around the Earth and the planets going around the sun. The other long-range force is electromagnetism. It sounds like two forces. There are two different phenomena, electricity and magnetism. But in the 19th century, Maxwell and Faraday and others realized that the phenomenon of electricity and the phenomenon of magnetism are actually just two different manifestations of one underlying force, electromagnetism. These long-range forces are absolutely obvious to us in our everyday lives. We have magnets that tell us which direction we're walking in. We have the electromagnetic field, the thing that tells the electromagnetic force how to stretch across space. And electromagnetic radiation is just a wave in the electromagnetic field. That means that light, X-rays, radio waves, basically everything that makes the modern world go is all just electromagnetism and the waves in the electromagnetic field. It's these long-range forces that are very obvious to us in our everyday lives. But it's the short-range forces, the nuclear forces they are sometimes called, that are of most interest to particle physicists. And the short-range forces have the boring names, the strong force and the weak force, or sometimes the strong nuclear force and the weak nuclear force. The strong nuclear force is what holds the nuclei of atoms together. An atom is an electron, or a set of electrons, orbiting a nucleus. The nucleus is a set of protons and neutrons, which are in turn made of quarks. So that bag of quarks that make up protons and neutrons in the atomic nucleus are held together by the strong nuclear force. There's also the weak nuclear force that has almost no effect on our everyday lives. It is in fact very, very weak. It is very hard to detect, and it's also the weirdest of the fundamental forces. They all seem difficult to understand if they're all just forces of nature. But as a physicist, you look more carefully at the four fundamental forces and you realize that three of them kind of make sense. Gravity, electromagnetism, and the strong force are theories that we have that fit the data very well. For the weak nuclear force, we also have a theory, but it's a mess. It's much more complicated, and that is a story that has to do with spontaneous symmetry breaking and the Higgs boson, and I'm sure there are other teaching company lectures that talk about this. For our purposes, the weird thing about the weak interactions is that they are not invariant under time reversal. So we've talked a lot about the arrow of time, but if we're going to get subtle and careful about it, we should recognize there are different degrees of having an arrow of time. There are different ways in which you could be different from the past going to the future. So let's distinguish between three different kinds of arrow of time from sort of the weakest to the strongest. The weakest, the least interesting, most trivial kind of arrow of time you could have is if you just have something in the world that is going one way and not the other. If you have a car going one way down a road, in some sense, that's an arrow of time, but it's not a deep, fundamental thing about nature. The next level of an arrow of time is if fundamental processes go one way and they go the other way, but maybe at a different rate or in a different way. So that's not what we talk about when we talk about entropy. The point about entropy is that you can take an egg and you can scramble it, but you simply cannot unscramble it. But let's imagine there was some fundamental feature of reality that could go back and forth, but when it went backwards and forwards, it did it in different ways. That would be the second level of an arrow of time. The third level of an arrow of time is that if things can only go one way, That's true irreversibility, and that's the arrow of time that we care about. The arrow of time that lets us remember the past and not the future, make choices about the future and not the past. That's a true irreversibility. That's the strong third level arrow of time. Now, even Newtonian mechanics includes the weak first level arrow of time. Things happen in one direction but not the other. For example, the sun always rises in the east, and then it moves over and it sets in the west. That is in some sense an arrow of time. You can tell which was the morning and which was the evening from where the sun is, but it's clearly an accident of nature. If you made a movie of it and played it backwards, you would be able to tell that you were playing the movie backwards because you see the sun setting in the east. But we could easily imagine a universe in which the sun really did set in the east, still obeying the same laws of nature. Likewise, the hands of a clock move what we call clockwise, but there's no difficulty in building a clock that went counterclockwise. Even the expansion of the universe is something that is just something that happens to be the case in our actual world. We can invent hypothetical universes that obey the same laws in which the universe is contracting. So all of these are just accidents of nature in our world. They are different from the past to the future, but they are not fundamental arrows of time. The increase of entropy in the universe is a fundamental arrow of time. That's a real irreversibility. You can mix milk into your coffee. You cannot unmix the milk out of your coffee. That's the kind of arrow of time that we care about. The weak interactions of particle physics are in that no man's land of number 2. Things are reversible. The weak interactions happen one way in time, and you can imagine undoing them. They're not irreversible. But when they happen one way in time, it's different. It's at a different rate than when they happen the other way of time. That's the kind of arrow of time that you get in the weak interactions. It's not an irreversibility. In the language of Laplace, if you know the state of the universe at one time, you can evolve it forward using the laws of physics, including the weak interactions. And from wherever it gets to, you can know where you came from. You can unevolve it. You can go backwards. But you need to know that you are going backwards in time because the weak interactions work differently going in one direction than the other direction. You might ask, how can this possibly be the case? And if it is the case, how could we know? What we're talking about here are interactions within particle physics. And the stage in which particle physics acts is that of quantum mechanics. So we have the whole next lecture where we'll talk about quantum mechanics in great detail. All we need to know right now is that quantum mechanics says that when you do an experiment, you can't predict the outcome of that experiment with 100% certainty. Instead, what you predict are the probabilities that one thing is going to happen versus some other thing. So in particle physics, a paradigmatic experiment is to take two particles, smash them together, let them interact, and watch what comes out. For the weak interactions, for example, you can take a proton and an electron, smash them together, and they can interact through the weak nuclear force and turn into a neutron and a neutrino. The neutron is the slightly heavier version of the proton that does not have an electric charge. The neutrino is a very, very light particle that just zips away. So that is an allowed interaction according to the weak nuclear force. Proton hits an electron, turns into a neutron and a neutrino. And then you can ask the question, what about the time reverse of that interaction? Take a neutron and a neutrino, smash them together, and you can create a proton and an electron. That can happen. That is allowed by the weak nuclear force. If one thing can happen, then the time reverse can happen. But you can ask the question, do they happen at the same rate? Do they happen with the same probability? Is the way in which they happen precisely the same moving forward in time as moving backward in time? The bad news is that as a practical fact, as a matter of actual procedure, those experiments would be extremely hard to do. Remember about the weak nuclear force, it's weak. It very rarely happens. When you take a neutrino, for example, and smash it into a neutron, you can hope that the weak interactions kick in and you create a proton and an electron out of it, but the chances, the probability of that happening is very, very small. So as a practical matter, if you actually want to build the experiment and ask what happens, smashing two particles like that into each other is not the way to go. Fortunately, there is a way to go. There's a very unusual and amazing phenomenon within particle physics called particle oscillations. It kind of makes sense to us that if you take two particles and interact them with each other, they can turn into two other particles. But there's another thing that only involves one particle. You can have a single particle, according to the rules of particle physics, simply turn into another kind of particle and then turn back. This isn't something that happens in our macroscopic everyday world. It's very rare and the conditions need to be just right, but this does happen. It's known as a particle oscillation. Neutrinos oscillate, and this is a whole industry within particle physics measuring the oscillations of neutrinos back and forth. The problem is that neutrinos are hard to capture and do experiments with because they're so weakly interacting. What we want is one kind of particle that oscillates into another, and then oscillates back into the first kind, and we can ask, how fast does it happen? How fast does particle number one oscillate into particle number two versus particle number two oscillating back into particle number one? So what you see here is we're distinguishing between the concept of reversibility, meaning I can figure out where you came from, and the related concept of if I play the movie backwards, does it look the same to me? In previous lectures, we've been sloppy about drawing the distinction between these two things. We've said reversibility means you can play the movie backwards or you can recover where you evolved from. In the weak interactions, it's not quite the same. You can recover where you came from, but if you really understood the weak interactions and you saw one particle oscillating into another one, you could figure out whether you were playing the movie backward or forward. Now, it's not that often that these particle oscillations happen. If one particle oscillates into another one, it better be the case that none of the laws of physics are violated when that happens. For example, the mass of one particle better be the same as the mass of the other particle because mass is not coming into existence. The electrical charge of one particle better be the same as the one that it oscillates into because electrical charge is also conserved. So when we want to do experiments in particle oscillations, we need two different kinds of particles that look more or less identical, but truly are different at some fundamental level. Fortunately, nature gives us the perfect candidate, a particle called the neutral kaon. This is a meson, and if you are into particle physics, you know that what that means is it's a combination of one quark and one antiquark. So quarks come in different flavors. There are up quarks, down quarks, top quarks, bottom quarks, charmed quarks, and strange quarks. 6 different flavors of quarks. The kaon, the neutral kaon, is a combination of a down quark with an anti-strange quark. It has an antiparticle, the neutral antikaon, which is an anti-down quark and a strange quark. None of these details are at all relevant. What you need to know is that there's a kaon that is neutral, it's a particle. It has an antiparticle that has the same mass and is also neutral. All particles have antiparticles with the same mass. The best thing about the kaon is because it's neutral, it has no charge, it has no conserved quantities whatsoever. A kaon can oscillate into an antikaon and then they can oscillate back. So how do you know when it happens? This is the tricky experimental question. I say, I have a kaon here. Look, it oscillated into an antikaon. The problem is they have exactly the same mass, the same charge, they interact in the same way. How do you know whether you have a kaon or an antikaon? The answer is that neither the kaon or its antiparticle are stable. They both decay into other particles. And the good news is that a kaon decays into different particles than an antikaon decays into. If you must know, a kaon, an ordinary regular particle kaon, decays into a negatively charged pion plus a positron, which is the antiparticle of an electron. It's a particle with a positive charge, plus a neutrino. Kaon goes to negative pion, positron, and neutrino. The antikaon goes to the antiparticles of all those things. So the antikaon decays into a positively charged pion, a regular electron, and an antineutrino. The point is that we can wait and see. If you have something that is either a kaon or an antikaon, just wait for it to decay. If it is really a kaon, it will decay into a negative pion, a positron, and a neutrino. The neutrino you don't notice, so who cares? But if it's an anti-kaon, it will decay into a positively charged pion and an electron. The point then is that if time reversal is violated, if the weak interactions treat going forward in time differently than they treat coming backward in time, then kaons and anti-kaons will decay at slightly different rates. The rate for one will be a little bit different than the other. So what you do is you start with a box of kaons. In the real world, you don't have kaons in a box, but you can create a beam of kaons. You smash particles into each other, get rid of everything that is not a kaon, and just let the beam of kaons travel. As the kaons are traveling, they're oscillating. So you start with a 50-50 mixture of kaons and anti-kaons. They will oscillate back and forth into each other, and eventually they will decay. If time reversal invariance is violated, the rate at which a kaon turns into an anti-kaon will be different than the rate at which an anti-kaon turns back into a kaon. What that means is that even if you started with a perfect 50-50 mixture of kaons and anti-kaons, particles and antiparticles, you will not decay ultimately into the same 50-50 proportion of positrons and electrons, or negatively charged pions and positively charged pions. So this is an experiment you can do, and even though it's quite a subtle experiment to do, it requires a great deal of heroic experimental effort. It doesn't violate any of the laws of physics. It's not implausible in terms of very, very rare interactions. You just need to be very, very careful while you're doing it. So this experiment has been done. It was done by experimenters at CERN. It was called the C.P. Lear experiment. CERN is the giant particle accelerator laboratory outside Geneva in Switzerland. Right now, the CERN is most famous for the Large Hadron Collider, which is smashing protons together to look for new particles of nature. But the nice thing about a huge particle collider is that you get little spin-off experiments. You can take the particles that they don't need and use them to do other experiments. So the C.P. Lear experiment was one of these little side experiments, and it went in 1998. And they built a beam of kaons and anti-kaons. They started with 50-50 kaons and antiparticles. And you would expect, if time reversal invariance were a good symmetry of nature, if the weak interactions respected going forward in time and backward in time equally well, you'd expect to see an equal amount of decay products from kaons and decay products from anti-kaons. What you actually saw was different. There were more kaons decaying in that beam than anti-kaons by 2/3 of 1%. Some tiny little fraction of a difference that says that the weak interactions like being kaons more than they like being anti-kaons. So in other words, it takes more time for a kaon to turn into an anti-kaon than for an anti-kaon to go back to a kaon. The time it takes to go in one direction of time is different than the time it takes to go backwards. Time reversal is not a symmetry of the weak interactions. That is an amazing fact. This is a deep feature of reality that, unlike all of the regular forces that we know and love in our everyday lives, electromagnetism, gravity, even the strong nuclear force that keeps nuclei together, all of those forces respect time reversal invariance. They do things with the same speed forward in time or backward in time. But the weak interactions don't. That's a crucially important feature of the world. You might wonder, why haven't they won the Nobel Prize for this? They've discovered something crucial about the world. The world does not treat going forward in time the same as going backward in time. The answer is that even though the C.P. Lear experiment did verify that the weak interactions violate time reversal, it was not a surprise to us. Everyone in the world expected that that is exactly what they would find. And you should think about why this is the case. There's sort of the vague reason and the more precise reason. The vague reason is that if you believe in reversibility, if you believe that Laplace was right, that if you have the information about the current state of the universe to perfect precision, that lets you predict both the future and the past, then that predictability seems to treat the past and future on an equal footing. And maybe there's an implication of reversibility that says, well, because the world is reversible, there's something symmetric about the past and future. After all, Information is conserved as you go from the past to the future, so shouldn't other things be conserved as well? That's kind of a vague hope that you might aspire to. Then you would like to make that more specific. So what is the symmetry between past and future that is a reflection of the underlying reversibility? Well, there's an answer to that. There's a symmetry called CPT, where the different letters stand for different hoped-for symmetries of nature that are all actually violated. C and P and T are things that you might expect to be symmetries but aren't. But the combination of all three of them gets you a good symmetry of nature. So C stands for charge reversal. Basically, the C operation takes a particle and changes it for its antiparticle. So you might think that if you had a collection of particles in a box and you changed all of them for antiparticles, and you didn't let the box interact with the outside world, it would be the same. It's just particles changed for antiparticles. It would weigh the same, it would act the same, and so forth. Turns out that is not true. P stands for parity. This literally means that you flip the orientation. You flip clockwise for counterclockwise. In other words, you hold the experiment up in a mirror. And you might think that if I did an experiment and then did the mirror image of that experiment, I would get the same answer. But the answer is also no. Nature violates parity. T, of course, stands for time reversal. And you would expect maybe that if you did an experiment forward in time and then did it backward in time, it would get you the same answer, but we've just seen from the C.P. Lear experiment that that is violated. So all of these transformations, C, P, and T, are things that you might guess are symmetries. They're things that if you do it once and then do it again, you come back to where you started. If you change particles for antiparticles, and then again, you get back to the original particles. Likewise for taking the mirror image or taking the time reverse. But all of these transformations are individually violated by the actual laws of physics. This by itself was a tremendous discovery back in the 1950s. The old wisdom before 1956 was that C, P, and T are all individually good symmetries. And it was three Chinese-American physicists who proved to us that that was not the case. T.D. Li, C.N. Yang, and C.S. Wu. Li and Yang were theorists, and they went through the literature because they had a sneaking suspicion there was something we didn't understand about the weak interactions. The physics literature, the experiments that they were able to discover that had already been done, showed us that parity, taking the mirror image of a physics experiment, seemed to be experimentally a very good symmetry of the strong interactions, the electromagnetic interactions, and as far as anyone could tell, the gravitational interactions as well. But what Li and Yang realized was that no one had checked the weak interactions. So they went to their colleague, C.S. Wu, who's an experimentalist at Columbia University, and they encouraged her to do an experiment to check whether or not the weak interactions respected parity. It turns out this is one of my favorite stories about experimental physics. C.S. Wu was initially sort of skeptical. This was an interesting thing to do. It would take a lot of time, but her colleagues, Li and Yang, convinced her that she should do it. She started getting very, very excited because she realized that if she actually noticed experimentally that parity was violated, this was a huge result. She and her husband had actually left China 20 years before, in 1936, and for the last 20 years, they had not gone back to their homeland. They had planned a return trip on a cruise liner, and they were ready to go on their trip back to China for the first time in 20 years, when Wu realized that she really needed to stay home and do her experiment. She let her husband go back to China without her. She stayed at home, did an experiment watching the decay of certain atomic nuclei, and she was able to go back over the Christmas holiday to Columbia and report to Li and Yang that she had shown that parity is violated by the weak interactions. This is something that was certainly worth a Nobel Prize, and sadly Li and Yang won the Nobel Prize, but Wu did not. It was absolutely a change in how we think about how the fundamental laws of physics work. Parity, taking the mirror image of something, is something that just seems like it should be a symmetry, but it is not. Now, certain clever people said, well, maybe parity is not a symmetry, and maybe charge conjugation, changing particles for antiparticles, is also not a symmetry, but maybe if you combine them, you get a symmetry. Maybe if you change particles for antiparticles and then take the mirror image, CP would be a good symmetry of the world. Well, you can kind of guess how this is going to go. The answer was no. In 1964, Jim Cronin and Val Fitch did an experiment where they showed that CP was also violated. They also used the kaon system, looking at different decays of neutral kaons. So CP is also not a symmetry of nature. So you might guess, well, what about CPT? What if I take an experiment, change all the particles for antiparticles, take the mirror image, and then run it backwards in time? Maybe that's a symmetry of nature. Now, depending on your level of cynicism, you might say, no, I think that none of these are symmetries of nature. I don't even think that the CPT combination is going to be a good symmetry. It turns out that there is actually a theorem that you can prove that under certain very general assumptions, the combination CPT must be a symmetry of nature. These are not very strong assumptions. Basically, locality, that things that happen here don't instantly affect things that happen there, and invariance under moving at different speeds and moving in different directions. There's certain very basic features of physics that we think are true, and if those features are true, then it must be the case that CPT is a good symmetry of nature. Now, theorems are slippery beasts. It's always easy to convince yourself that their assumptions on which they're based are absolutely true, and then to find out later that they're not. But still, as far as we can tell, experimentally, CPT, that combination, seems to be a perfectly good symmetry of nature. So what that means is, if CP is violated, if you don't get the same answer when you change particles for antiparticles and take the mirror image, but CPT is not violated, then T must be violated, if that makes sense. It's kind of like you're multiplying the violations by each other to cancel out. CP is violated, T is also violated. That's why CPT can be conserved. And this is why nobody expected that CP Lear would not find T violation. We already knew that CP was violated. We have a theorem that says that CPT must be preserved. Therefore, it's an implication that time reversal invariance should not be respected by the weak interactions. That was the prediction of our theory. That's exactly what they showed at the experiment. So the moral of this story is that even though the weak interactions do give you a difference between going forward in time and going backward in time, it's a matter of definition whether or not you want to say what we call in words time reversal is T, or whether what we call in words time reversal is the whole combination, CPT. So if I define what I mean by time reversal to be first change particles with antiparticles, then take the mirror image, then run the movie backward in time, that is a symmetry of nature. And in fact, this is a theorem. If the laws of physics are reversible, if Laplace was right and the information we have about the world now predicts what will happen in the future and retrodicts what happens in the past, there is always some kind of symmetry relating time reversal. There's always some kind of symmetry that says if I do enough to the system, I can run the movie backwards and it will give me the same result as running the movie forwards. So for our purposes in these lectures, the important lesson is that even though there is some technical sense in which the weak interactions violate time reversal invariance, that does not explain the arrow of time. Our macroscopic arrow of time, why we can remember yesterday but not tomorrow, why causes precede effects, why we grow older as time goes on, those are all due to irreversibility. Those are not due to reversible processes like the weak interactions. So if your friends ask you, yes, it's true that the weak interactions of particle physics do tell the difference between moving forward and backward, but no, they don't explain the arrow of time.